Or to be equidistant. Have a good look underneath. If you want, I can voice it, because in Isa they will do equidistant. If you don't. You prefer equidistant? Coverage? You're like plenary? Take single agency and you combine with RCS, you will have. Well, both are good, but speak, let them say.
This.
Okay.
I don't know what happened there, but yeah.
You're very welcome to stay with us. So we start. 1 minute past. We start. Yeah. Okay. So good morning, everyone, and welcome to the Earthquake and Tectonic session. Thanks for coming. There's a very attractive program next door. No, they are here. They cannot leave the room, I think. Okay, so we will have 3 sessions during the conference, and for your questions, we have here people to help you. So there's in the very back Anastasia. So look for her, and here in the front it's Philip with the microphones. They will walk around. It would be very nice if our speakers would be kind of in time that we can have a lot of questions. And without, and I point out, we use this clock, so all our time zone. I think it's like 2 minutes past. But we start with Tim Wright. I'm very happy that he is with us, and we have high-resolution geodetic velocities reveal role of weak faults and deformation of Tibet Plateau.
Yes.
Sorry.
Yes, thank you for being here, particularly people who don't work for me. It's very impressive. You've made it. You're still going strong on Thursday morning. It's a great pleasure to be able to present this work. This is something I've been trying to do since about 2004, and we finally got a velocity field for the Tibetan Plateau. I'm going to talk to you about what it shows and what it means. Why do we care? Well, the India-Asia collision is the biggest zone of tectonic deformation on the planet, and it's also been an area that's been at the kind of core of controversies around how the continents deform. But we'll go back really to the 80s. So back in 1986, we had this continuum model of continental deformation. This is one of the early geodynamic models. This model kind of emphasized how the continents were deforming in response to boundary forces and internal buoyancy forces that build up due to crustal thickening. And the models really emphasized that role of crustal thickening in the deformation. The rheology was viscous, so the continents were flowing in response to this rigid Indian indenter. And in this view of the world, faults are essentially passive markers responding to the underlying velocity field. The alternative model that was very popular at the time was the so-called extrusion models. These were physical models built with a rigid indenter indenting into plasticine. They would basically emphasize the roles of boundary forces. They emphasized eastward motion. In fact, crustal thickening wasn't allowed. There was a perspex sheet on top of that. The rheology was literally plastic. It was plasticine, and faults dominate the deformation field. If you prefer to think in terms of food, then you can think of the continuum models as like this running, oozy French brie, and the extrusion models being more like these brittle English cheddars. The irony, of course, being that the British people preferred the French cheese model and the French preferred the British cheese model. So now we've got this incredible data. I guess the main point of this talk is to think about how the continents really deform. At the same time, we want to think about the rheology, and just to throw even more food analogies into the talk, we've got these different rheological models from the Bergman and Drazen paper, and I want to talk about what the data tell us about the rheology specifically. And then actually, when we take a step back, the real reason we're doing this is that the earthquakes that kill the most people are the earthquakes that happen in the continents. And we want to try and understand how can we use geodesy, the power of instruments like Sentinel-1, to say something about seismic hazard and ultimately to prevent people dying in these earthquakes. Before I go on, I want to acknowledge my collaborators. This is a huge team effort that's taken many years. For this talk, I particularly want to acknowledge Jin Fang and Greg Hausman, who've been the main contributors and done a huge amount of the work that I'm going to show today. But actually, all the people I'm circling in blue have contributed at some point to this work. And of course, I want to acknowledge Sentinel-1 that has really finally been the satellite that's enabled this work to happen. It's been, and in particular, I think two aspects. One is the systematic data acquisitions over the continents, and the second, of course, is the free and open data policy, which means we can process literally millions of interferograms. I'm going to race you through the methodology of what we do. This nice figure comes from a paper that John Elliott's going to talk a lot more about in the next talk, but it's a nice figure summarizing the workflow that we use. So we start by making interferograms. We do those automatically over 250 by 250 kilometer frames using the LIXAR code at the UK Jasmine and Cedar facility. There's more details of this in Milan Lazecki's paper published in 2020. We've just hit a nice arbitrary milestone this week in that we've now just uploaded our 2.5 millionth interferogram on there. Those are all available for anyone to use for any application. You can see from the map that there's been a big focus both on those tectonic areas in the Alpine Himalayan belt, but also on the global volcanic areas. You can go on this, you can get interferograms. Here's just a recent example from the Philippines earthquake from just over a week ago. Once we have the interferograms, we then invert for time series and importantly for this application, average line of sight velocities at 1 kilometer resolution using the LIXPAS code, and you can read about that in Yu Morishita's paper. We now make model-based corrections for a number of things. These are becoming fairly standard, I think, in the community, but the troposphere, ionosphere, solid earth tides, and plate motions. You can see here in this, again, this nice figure from John's paper that the effect those have both on the velocities and on the time series as well. They really kind of tighten up the time series in particular. We also remove co-seismic displacements where the magnitude of the earthquakes is bigger than 6. And for Tibet, that leaves us with about 260 of these 250 by 250 kilometer frames, something like 52,000 overpasses and 200,000 interferograms. So at the end of that, we have line of sight velocities that are independently referenced. So each of these frames has its own reference frame. This is the ascending data. This is the descending data. So you can get hints of the tectonics in this, but it's a little bit hard to actually see what's really going on and really understand the processes we're seeing. In order to do that, we need to tie it to something, and we choose to tie it to the GNSS field. And there's been a lot of work gone into compiling GNSS data. So Chris Rollins, who's at GNS in New Zealand now, did all of this work. He took over 18,000 GNSS velocities from 131 papers, tied all those to a common Eurasian reference frame, filtered, chose the best velocities to give something like 3,142 velocities over this region. That included vertical GNSS from 1,500 sites, and we also had over 6,000 leveling benchmarks that were added into this. So that's basically gives us the backbone that we tie everything to. We then jointly invert the GNSS leveling and INSAR data using an approach that's described in this paper by Wang and Wright from 2012. Essentially what we're doing is we're solving for the 3D velocities on the nodes of a triangular mesh. In this case, we have 0.2 degrees spacing. At the same time, we solve for the reference frame adjustment parameters for the INSAR data, and that's really the key. So this allows us to tie the INSAR to the GPS, but we're also using the GPS, using the INSAR to give us that velocity field, so we're getting a consistent answer. And when we do that, we get velocities, line of sight velocities that make sense. So here are the descending velocities. Blue is motion towards the satellite. And for horizontal motion to the east, which is what you get in South and Central Tibet, you see that you've got that big area of blue. And similarly in the ascending geometry, it's the opposite color, it's red. And you can see things are consistent between those frames, and you can see now, start to see the tectonics coming out. We'd still like to understand that in a more intuitive reference frame. So we decompose the data into east and vertical velocities. To do that, of course, you need an assumption. We've got 2 observations and 3 unknowns. We choose to take the north-south velocities from that smooth interpolated velocity field and assume that those are correct. And then we only solve for the east and the vertical. That method is described in various papers. The vertical velocity field looks like this. I think we've got a plot in the bottom right there, of course, of the correlation with GPS as well. What this largely shows is non-tectonic features. There is some tectonics in here, we think, but it's largely non-tectonic features, and I'm not going to talk about it much in detail in this presentation. What I'm going to focus on is the horizontal field, which really beautifully reveals the tectonics of Tibet. Before we go on, given the discussion this week about how accurate INSAR is, I thought it's worth just thinking a little bit about uncertainties. It's worth saying that I think they're somewhat challenging to estimate theoretically when you're doing a study like this. There's 2 approaches we've been using here that I'm showing. One is to compare to the GNSS field. But of course, we've used the GNSS field to tie the INSAR down, so that's not really fully robust. The other is a kind of leave one out analysis, where we try, for the areas of overlap, we leave out one data set, we predict what that data set should look like and compare it to the observations from the other data. And both of these methods basically suggest that the velocities have an uncertainty that's less than about 2 millimeters per year. So what do they look like? So you get a real clear view of that by looking at these profiles that span the whole plateau. The north-south profiles, I think the thing that leaps out in particular is that every time they cross one of the big faults, you see this step, this change in velocity. But in between those big faults, you've got more smooth deformation. Particularly, you see that in this east-west profile, D to D dash. Really, you can't see individual faults very clearly at all in that profile. So we seem to have 2 kinds of behavior going on that we need to explain. Let me get a little drink. I shouldn't have shouted too much at the football last night. So the clear way of seeing what's going on is to look at the strains. So the strains are really what we care about. That's what causes earthquakes, is the deformation field. So we calculate the strain rate tensors from the velocity gradients of the 1 kilometer velocity grids. We need to filter before we do that because of the noise, and I'm not going to talk much about that, but the results do depend on the choices you make. And care is also needed because of different resolutions of east and north components. Shear strains and horizontal dilatations are the most useful for thinking about the tectonics. But of course, just note that the north-south shear is not as well resolved as east-west shear. But you can see by comparing the GNSS-derived velocities and the INSAR velocities that if you just look at those faults, the INSAR just sharpens up the strain really beautifully. It's really making a big difference. So what does the deformation show us? One thing that leaps out in that shear strain map is we can see past earthquakes, so we're seeing post-seismic responses from those. We're also seeing creep, and notably here around the Shanxue fault in southeast Tibet. But we're also seeing focus strain around all of those faults, whether or not they had an earthquake in the last 30 or 40 years. And those faults that are straining really match very nicely the faults that have been mapped from geomorphology. This is a map from Toponier and Molnar from the 1970s based on optical satellite imagery. And you see the same faults leaping in the modern day strain field, leaping out. Away from those faults, we've got some regions with pretty low strain, these white colors, and other areas with the more kind of smooth background, light blue colors showing distributed strain. The distributed strain is more clear, I think, in the dilatation field. This is telling us about the expansion or contraction of the area. You can see around the Himalayas, you've got contraction, and also in northeast Tibet. So that's suggesting crustal thickening. In south and central Tibet, particularly south of the Kunlun Fault, we're getting dilatation. So the east-west extension is actually outpacing the north-south convergence, which is actually a slightly puzzling thing to be happening in a mountain belt. So how can we build a model that can explain this deformation field? For full details of this, you need to read Jin Fang's paper that was published in JGR in 2024. But we start with this thin viscous shell model. Just as a reminder, this is 2D depth averaged power law rheology. So this is very similar to the models from the 1980s. We've got buoyancy forces that build up from gravitational potential energy, and the boundary conditions are set by the known plate motions. We've got a strong India indenter. And I'm going to show you a series of models. In all of those, we're going to look at the east-west velocity field. So in the top right there, we've got the predicted velocities, and the bottom right's the observation. And there is a number here, in this case, 7.1 millimeters per year. That's telling us the misfit between the two. And so we're fitting with this model at about 7 millimeters per year, but it really doesn't capture, in particular, that eastward motion of south-central Tibet. If we make some strong regions, which we think are there based on the geology and the strain rates, that helps a little bit. But we start to do a bit better by making the thicker areas weaker, which we might expect because there's more weaker crust, and particularly if we make central Tibet even better. So this is about even weaker. So we get to about 5 millimeters misfit, but we're still not really capturing the full velocity field. So the big innovation in Jin's paper was to introduce discontinuities into the continuum model. We do those by adding these major fault zones. These have a shear resistance that's basically proportional to the slip rate, and you can play around with that resistance coefficient. And just by adding that in, you make a big difference. So if you compare the model without the faults with the model with the faults, you're really instantly improving the fit, and the faults are having a big, long wavelength influence over the whole plateau. If we make the plateau weaker and central Tibet even weaker, we can get the best fit. And here we're getting down to about just over 3 millimeter misfit, which isn't so much bigger than the uncertainties in the data. So neither of these cheese models really actually are satisfactory. This is more like the model we would expect here. We need to have models that have these big faults. They probably cut through the lithosphere. And between them, though, we've got more continuous deformation with smaller faults. One question I mentioned, it's surprising that Tibet is dilating. There's a number of models in the literature. I'm not going to spend time talking about why that is. Actually, what we think the reason is you can only do it if you've got a very weak Kunlun fault here, and that allows this whole region to be extending all the way from the Himalayas to the Kunlun fault. And we think that the Kunlun fault was mobilized in the mid-Miocene, so 10 million years or so ago, and that's probably what started this east-west extension. We can also think a little bit about how strong the faults are. I haven't got time to go through the details of this argument, but you can read it in the paper. But you end up needing really, really weak faults, essentially, so with depth average shear stresses of around 2 megapascals. And that's somewhat consistent with this banana split model. So you've got, this model has this weak ice cream between the stronger bananas, and that seems to be a model that perhaps works fairly well for Tibet, although the bananas have to flow as well. So maybe anyway, I'll stop with the food analogies. I think the key is that these faults, the big ones are the ones with the stable geometries. If they're stable, they can develop weak zones cutting through stronger lithosphere, and there are a number of mechanisms for that. In terms of the seismic hazard, I just want to emphasize that we need to think about those smaller faults as well as the major block boundary faults. And there's a number of questions here we've still got in terms of how we do that. And again, I'm running short on time, so I'm going to behave myself as a session chair and drop to my conclusions. So I think we've got this bimodal behavior. The major faults must be really weak, but we also need this flow between them. The dilatation's linked to the Kunlun fault, and seismic hazard must account for all of these. And I think future missions are only going to make this data better. And again, just in light of the discussion we had on Monday, here's a bunch of links to all the data sets that are available for people to use and analyze in different ways, and the codes. So I'll leave it there. Thank you.
Thank you, Tim. Questions for Tim? There we have one question. Philip, right behind you.
Yeah, hi, Tim. Thanks for the interesting talk. Just a quick question regarding the resolution of your 3D velocities.
Yeah.
It's 1 kilometer. Is it so? It looks like you average a lot. I think more than 50 looks or something.
Yeah,
I guess. And is there anything that are you interested in having a better resolution? Would this be in the future? I'm asking although because we are developing the next generation of Sentinels.
Yeah.
And so I think we want to see also what are the key drivers for this application also.
No, absolutely. I think for this big scale tectonics, 1 kilometer is fine. If if we imagined having a 3D GPS every 1 kilometer, we'd be very, very happy with that. I think for some applications, thinking about creeping faults, for example, having the higher resolution is really valuable. I think the other thing that's really valuable is the revisit times of having lots and lots of data. So we actually process this we do the original data at 100 meters and average it down to 1 kilometer just really for convenience. But yes, I think the resolution is more of a driver, I think, for volcanic applications, but there are some tectonic applications where the higher resolution is really useful as well. Yeah, thank you.
We have more questions here from Shimo and then from Falk.
Thanks. Really nice work and presentation. My question is about the time scale. The observation are of 10 years.
Yeah.
And so comparing it to viscous model is not really making justice to either of them.
Yeah.
And so you get emphasis when you compare to short-term the S-wave deformation cycle, which is like maybe 100 years, but you cannot pick up the viscous component because it's a much longer time scale.
I think you can, but I agree it's an important problem. And I think it's one of the questions I skipped over was, are those short-term rates representative of the long-term rates? I think on the longer scale, you need that viscous component. This clearly modulated by earthquake cycle effects, absolutely. And the Kunlun fault, for example, when we're solving for this strength parameter, the area that's failed recently looks weaker than the area that hasn't had an earthquake recently. So there's differences there. So it definitely matters. I think it's a second order effect probably, but definitely more work needed. And I think that's probably the next level where this research is going to go, is thinking about time variation, particularly as now we've got ERS, MVSAT, Sentinel, and when we've got Sentinel-1 next generation, ISAR, etc., we'll be able to really look at those time variations, and I think we'll learn a lot from that. So thank you. It's an important point.
Okay, there's a quick question, quick answer.
Okay.
Yes, so you partly answered my question already. So the post-seismic deformation is not post-seismic slip, was yet now not included in the model?
Yeah, we didn't. We didn't take into account the post-seismic. Yeah, so that's, if you like, it's there in the velocity fields, still showing post-seismic as part of that.
Okay, and then for the Kunlun fault, okay, you also just alluded to it. So the slip rate, what you are having, how does it compare with the long-term slip rate?
You should come to the talk this afternoon where I'll talk all about the Kunlun fault and its long-term slip rate.
Okay, thank you.
Jin Fang's talk. Yeah.
Very good suggestion. Thank you. So we have to stop. Yeah, find Tim in the coffee break. So the next presentation is by John Elliott, and deformation, strains, and velocities for the Alpine Himalayan belt from Transcontinental Sentinel-1, INSAR, and GNSS.
Thank you. Good morning. So this is now part 2. So there's a lot of reiteration of what Tim's just discussed, but a slightly different scale. And this represents a recently published paper that summarizes the sort of last 10 years of trying to do this endeavor. So a big team effort, as Tim's alluded to, working on really expanding these velocity fields to a whole transcontinental scale. So we're grateful to ESA for the invitation to contribute towards this special issue in RSE for this 10 years celebration of Sentinel, which has been really fundamental to be able to do this kind of scale of work. So we want to do this. Our motivation for generating the velocity fields is try and understand what the rates today tell us about the long-term growth of mountains, plate tectonics, and to look at the time-varying behavior of the earthquake cycle. And to do this at a continental scale, so what Tim showed, the distribution across the deformation at depth, and then ultimately to how do these strain rates relate to the seismic hazards. So we're trying to generate the underlying data sets that then can be used to answer some of these questions later on. Now, in terms of our sort of boundary conditions of our tectonic scale, we have the fixed Eurasia plate here, now referenced, and then the tectonics of the region involve the northward motion of these plates, Nubia, Arabia, and India, at varying rates from 5 to 50 millimeters per year going west to east. Now, because of the geological history of this region, that's created quite an asymmetric pattern of deformation where all the distributed deformation occurs north of this boundary zone on a wide two-dimensional array of faults and distribution of earthquakes. And of course, this is where large cities lie along these fault lines. That's why the seismic hazard presents such a large risk as those exposed population. Now, the strain rates have been mapped before at large scales, both at global and continental scale, by compilations of GNSS data to get those velocities that are then converted to those strain rates, those localizations of strain. And that's been done by Korny-Kramer in the global strain rate model from a large compilation of those data sets, and then more recently just published at the end of last year by Nicholas at the Alpine Himalayan scale. Now, what Sentinel has enabled us to do is to do that now with incorporating the INSAR data to do that. And we've been building up over the last 12 years in a project that look inside continents from space, originally devised by Barry Parsons, building up more and more data sets over a countrywide, regional, and now sort of continental scales. So here's Jonathan Rice's data velocities over Turkey, involving this sort of scale of data processing. That was then expanded more than twice the area across Iran, where we see really quite diffuse deformation as in contrast to Turkey, and lots of other signals that are non-tectonic. And then Tim's just summarized what we can do at the sort of scale of the Tibetan Plateau, a long-standing argument about the tectonics there. So I'll just show you then the results, just a visual tour of what this has been done at the Alpine Himalayan belt, going from the GNSS through the INSAR data to the kind of velocities and ultimately the strain rates that we want. That's the hierarchy of our approach in doing this. And the starting point is to take those GNSS data sets, and Chris Rollins did really cleaning, sort of unifying these into a common reference frame for this whole area, quite an endeavor to compile all these from these studies. A ridiculous supplementary table. And in fact, I do ask you to go to the supplementary material for this paper. It's much bigger than the actual main paper and contains all the important results in there. So this is then that compilation at scale. On its own, it's a very useful data set because it has been referenced together. It needs to be really well referenced to avoid anomalous strain rates that you get if there are discrepancies in the velocities. So this is a very clean. This is the view in the International Terrestrial Reference Frame. If we put it in our more common Eurasia fixed reference frame, you can see then that large-scale overall tectonics of the northward motion of all these plates that are causing this deformation across this region. Now, what's important about this is this distribution of GNSS. Now, Italy, you've got over 100 sites per square degree, so this kind of approach is not going to really add value. We wouldn't argue that we're going to tell you anything different about Italy. But you can see in regions that are quite sparse, less than 10 sites per degree, so spacings that are more than 10 kilometers apart, or huge regions with nothing in them at all, this is where the INSAR data, the wide area coverage, is going to add some value to these strain rates. So the INSAR processing is quite an endeavor, a large number of frames, almost 1,000 frames defined across this region on ascending and descending. We did the series of atmospheric corrections to be able to really get down, beat down some of that noise. Even with 10 years of data, it's important to do all these. So I'll show you some of the corrections that we've done, both for the tropospheric water vapor and the ionosphere, as well as solid earth tide and the plate motion corrections that are needed to really get down to this millimeter per year. So we use the GACOS, generic atmospheric correction online service for INSAR, to remove some of the effects of the troposphere, the water vapor, the hydrostatic delay. And this is the overall impact on the time series, the cumulative impact across the Alpine Himalayan belt on ascending and descending. So these are the corrections that are then applied to our time series, being done on an individual epoch basis. But in summary, what that shows you in terms of latitude, colored by latitude, through time, the time series this, for the gradient across the scene, millimeters per kilometer on descending and ascending, you can see the impact of that latitude on those kind of corrections, and the solid earth tide being really quite a small contribution compared to the troposphere. Similarly for the ionosphere, this is the difference, the contrast that you get on descending versus ascending. The ascending later in the day, much greater impact of the ionosphere needs much larger ramp corrections across it. So summarizing that then in terms of our time series, it's all dependent on the solar minimum max Earth 11-year cycle. If we correlate that with the sunspot number as a proxy for the energy of the ionosphere, you can see that it has really quite changed and ramped up towards the end of our time series. We started basically at the beginning of 2016 up to March 2024, and there's a strong latitudinal dependence, and it really does dominate the ascending frames compared to the descending. So that's quite a good summary of the impact of the ionosphere with latitude. So the important thing from that is C-band is still really quite impacted by the ionosphere, and we need to make those corrections to get at these interseismic strain rates. So following on from that, we do a time series approach using LixBus from Yumorishita. So this is the standard workflow. It's been adapted a bit for our needs. And we basically generate maps of velocity, average velocity from the time series. So we've got both those data sets. We're largely working with velocity here, but it's all underpinned by the time series that's in there. So we just take the average rates across the region to produce these maps, which we need to apply these plate motion corrections because of the shifting of the plate motion in the ITRF with respect to these sentinel orbits. So these are the long wavelength ramps that need to be applied to each of those. And as Tim showed, this is the summary then of the order of magnitude corrections that you need to apply to each of these. It's largely a long wavelength sort of correction that you're applying to do this, but it does tighten up the time series as well. So here's then those line of sight velocities at the whole Alpine Himalayan scale. And we want to make use of those by tying them into a common reference frame to generate a self-consistent velocity field. So we do that with the ValMap approach, taking the GNSS, those two line of sight velocities on a mesh, solving for those velocities as Tim showed you. And you go from this line of sight velocity that are all independent of each other to something then that you can see that really large scale eastward motion here in Tibet that Tim showed you, and then the westward motion of Anatolia here in the west. Now, the formal uncertainties we get out of the LixBus approach are really quite formal, small, at the 1 to 2 millimeter per year. So we have to more realistically calculate these uncertainties that tell us that it's more about 2 to 3 millimeters per year uncertainty. So formal ones are definitely too small. This is more realistic as a minimum baseline for the kind of uncertainties that we get in these regions using the overlap in the line of sights. So we do the velocity decomposition from the smooth northward velocity combined with the ascending and descending to give us this eastward velocity and the vertical velocity. It's the two components that we can constrain with the line of sight, the north only really coming from the GNSS. So if we start with that northward velocity, I take a profile through Tibet, right across the whole region, across Tian Shan as well. You can see that smooth profile that's constrained largely by the GNSS. If we now take something that we are providing information about, the eastward motion, right across from Greece all the way to the Sichuan Basin, on that arc, you see it's 8,000 kilometers, really quite a long wavelength now that we're constraining the velocities. We get these nice steps across the faults and that smooth long wavelength signal there that matches quite well. Of course, the GNSS is a constraint, and you can see the scatter in places. It can be quite large, but we do get the overall pattern of behavior. Then on to the verticals. Now, these are something that I would really urge a huge amount of caution in interpreting. So here's a profile across that. These have really quite noisy, that I would not hold much faith in them being incredibly accurate. So we don't want people to overinterpret these. There will be regions of shortening that you will be able to believe in the Zagros, for instance. But the thing to be very cautious about, and it's been shown by other talks yesterday, for instance, is the permafrost-related deformation across the Tibetan Plateau. This correlates very much with the permafrost index and any seasonal behavior of the thaw cycle. So these are quite dangerous to interpret. Short wavelengths, longer wavelengths along the Himalayan arc, you would start to believe some of those uplift rates. But here are these sort of profiles that we've got across this region and its relationship with the permafrost index, so you heed caution in using it. Also, a lot of the vertical is contaminated by large rates attributed to water extraction, land substance from water extraction from aquifers. So here's south of Beijing, a large area of substance related to that. And that's found across the Jungar Basin, northern Tian Shan, across Turkey, over 100 basins in Iran, where we've got time series for that, and we have a portal that shows that data too. So ultimately what we want to get to are the strain rates to inform about the localization. So we have to filter the eastward velocity to be able to do that, to remove some of the short wavelength noise. Otherwise you get spurious high strain rates. But this is then what we calculate from that, the second invariant, or more the norm of the strain rate tensor. And it shows you the heating up where that strain is being localized on the faults that Tim showed you in Eastern Tibet. And it pops out in Pamir, Shaman, and Anatolia. Very well recognized regions of shear due to large strike-slip faults. And that's what really pops out in this. But you have huge regions of relatively low strain rates. So obviously in Europe, as you would expect, Central Anatolia in the east, Northern Arabia, Afghanistan, and across these regions, and bits north of the Tian Shan. So we are getting really quite low. Our sort of noise floor equivalent, I'd argue, is in some places is 20 nanostrain, maybe down to 10 nanostrain per year in regions of good coherence. That's the kind of lowest we can go. There'll still be strain accumulating there, but that's certainly, it's below that sort of order of magnitude, 10 nanostrain per year. So if we compare what the INSAR is adding, we just look at the GNSS, the compilation we've done, what you'd get for that shear, and then what the INSAR adds in. You can see the localization of the shear along the Pamirs, North Anatolian fault, and the faults across the Tibetan Plateau. So that's what it's adding in. And if we look at that difference, that highlights where we're adding those extra bits of information about how tight that strain is. If we compare it to the global strain rate model from Kramer et al., this is then where it's sharpening up the places as well. If I just backwards and forwards, you can see the spurious strain rates you get when there's sort of nearby GNSS sites that are anomalous. They give you high concentrations of strain, so it sort of smooths out some of that. And then the dilatation showing you where there are regions of contraction extension, so along the Himalayan arc, Pamirs, Tian Shan, the Shaman fault round here, Suleiman Ranges, and the Caucasus, regions of contraction versus aerial extension here in Western Turkey and Greece, the Corinth region here, showing that, and a bit along, obviously, the Apennines. So those are those regions. And then the vorticity, looking at that component of it, that shows you the sort of the anti-clockwise rotation of Anatolia and the clockwise rotation around the eastern syntaxis. So you get that large scale sort of rates. The rest are associated with the shear zones, the rotation associated with them. So the important thing, all that data is open. We have an open data repository on Zenodo of the results from the paper. So that's those sort of data sets of velocities and strain rates. And also, very importantly, a massive data set of those underlying time series that really need to be data mined for information. There's so much there that we've not had a chance to actually go through all that data, so it's available there. So just quickly then also in the papers, some discussion of the active tectonics that gets pushed to the back a bit. But in terms of creeping faults, there are a few very good examples of creeping faults that are already known. And we've got those as highlighting as the strain rates here. And we've also got the time series for these creeping zones. But at the scale of the Alpine Himalayan belt, we don't discover lots of creeping. It's actually the ones that are creeping have already been found. So it's not a widespread phenomena of sustained interseismic creep in this region. So it's more anomalous. Similarly, the question about post-seismic deformation. In contrast to the GNSS field, we have not removed that component. So the post-seismic from major earthquakes are in there. So Baluchistan, even as far back as 30 years ago, the Mani earthquake, it's popping up as a post-seismic signal. And we've actually, you can go as far back as 1920 and attribute the kind of rates that you're seeing today to post-seismic deformation tentatively. And also more recently, we've got the time series for smaller earthquakes are in there as well. We've not removed that from our data set. Usually, we've only tried to move the co-seismic effect. So what we want to do is be able to do a sort of correlation exercise. That we would want all the seismicity to line up in the places that are straining. Unfortunately, it's not going to be as easy as doing that. Obviously, regions that are straining do ultimately release that in earthquakes, but there's plenty of regions that are straining quite slowly that will ultimately release it in earthquakes, and with seismicity really quite broadly distributed, so it doesn't just flag up where the earthquake's going to be. Similarly, with the faults, if we look at the maximum shear rate, for instance, and then overlay the active map faults from this compilation by Styron and Paganini, you can see that where it is straining, those are really well recognized faults for a long time, But regions that aren't straining much do have active map faults going right through them as well. So large regions of Iran, Afghanistan here as well, and the Tian Shan. So then to conclude, the findings that we've got from that, Sentinel-1 has really been able to enable us to generate this detailed velocity field at really quite a large transcontinental scale now. So we can get these velocities, move on to the strain rates that will enable us to do further interpretation in the future. So the horizontal motion that we constrain really quite well in the eastward direction is dominated by tectonics. The vertical that we can more easily measure is often aquifer-driven subsidence, and is really quite hard to interpret tectonically often. Now, the strain is localized on major faults, particularly the strike slip faults, but we see really quite diffuse deformation across large regions of this alpine Himalayan belt. And I would argue that the loci of the current strain that we measure, many of them are actually the scars of old earthquake. And the harder that we look, the further back in time we'll think we're recognizing the post-seismic behavior of these earthquakes, potentially well over 100 years, these scars. So it remains a challenge to measure these long wavelength signals and these slow rates. As I say, getting below 1 millimeter per year over the 100 kilometers is a challenge. Getting below 10 nanostrain per year is going to be a challenge, even with ongoing acquisitions, I think, beating down that noise. And the north-south so far has been entirely dependent on GNSS distribution, so our future work will be in trying to improve on that. So, as I said, vertical rates still difficult and unreliable, so please don't overinterpret those. Even though we've made them openly available, there is strong caveats to their use. And it's always going to be a bit of a challenge to do systematic coverage in areas of dense vegetation in the southeast, as we went towards, for instance, Myanmar and southeast China. That's really quite a challenge, along with northern India. But otherwise, it's been able to produce a really quite a beautiful large-scale velocity field that I hope is of use to the community and will be a sort of foundational data set to build on and really quite improve in the next 10 years. Thank you.
Thank you very much. Questions for John? There's a question. Maybe this is a question you had before. It's a difficult area to get to with the mics.
Thanks for your talk. I was wondering, this is a huge amount of data set, temporally and spatially. How far are we predicting large magnitude earthquakes? What needs to be done?
So I certainly wouldn't argue you do it from this. It has presented more of a challenge in that really the zones that are straining fast, we already know about, those major strike slip zones. And the regions, there are plenty of regions that are really quite diffuse in their deformation at the 10 nanostrain per year that will still have significant earthquakes. You know. And by significant, I still mean magnitude 6, 6.5, that can be really quite a large hazard if there are villages and large cities on them. So yes, it's not highlighting exactly where you would need to go to find these biggest earthquakes. So I wouldn't push it too hard.
More questions? There's one, and then there's one. Maybe there's one.
You have some very strong vertical signals that probably do the processes that also contaminate your horizontal velocity field. Did you try to compensate somehow when you try to, I mean, when you have this big subsidence ball, you probably have some horizontal motion also?
Yes, we definitely see that horizontal motion. We've documented that well across all the ones in Iran. So we just threshold that to make sure we've reduced it, but we've not totally eliminated that. So it's just, we make a big enough buffer zone around anything that's subsiding more than 10 millimeters per year to try and alleviate that, but not totally exclude it. So again, we need to be careful interpretation towards some of those bigger, like the Jungar Basin ones. And certainly towards eastern China, it would be good to have a diversity of look directions on there. For a region that's really hosts the largest populations on Earth, there are quite big gaps in some of the Sentinel acquisitions. So it certainly would be nice to be able to recommend greater coverage for areas that have a huge number of people, where there are large signals that are useful both for water subsidence and tectonics. So anything south of Beijing, that'd be great.
Thank you. So there's a question, and there was a question in the back, or is it answered? Then, no, Simon here.
It's a question.
We take this guy. Falk, you ask later.
Yeah, I'm puzzled by the fact that the localization of the deformation is on where you had earthquake in the past. I mean, you still need to load those faults. It's not the earthquake that concentrates the strain, interseismic strain. So, are you missing the long wavelength, or how do you explain that?
Yeah, so it's a great question. So the Altintag fault, that's a good example of shear up against a hard backstop of the Tarim Basin. So there we were measuring quite well. But across the Tian Shan, for instance, that's a really quite broad deformation. It means there isn't yet an established clear shear zone. We're arguing that maybe it's a nascent developing one. But yeah, you need to be able to catch that really long wavelength. So where we can try and improve it is that pinning. Now, we did a lot of effort with the GNSS because you need that to be able to constrain some of that long wavelength. But I think trying to find techniques that can nail that down a bit better to be sure that if there is a broad deformation zone in the mantle lower crust, then you're not losing that in any of these long wavelength corrections that we have to make, for instance, in that VEL map, that sort of adjustments, that there isn't a cumulative impact across that. Now, getting some of that north-south, given this is a north-south convergent zone, getting some of that north-south deformation is going to be important constraints as well. So looking forward to incorporating, for instance, the NISAR data to give the diversity of look directions to be able to solve that, or some of the expansion of the burst overlap interferometry, for instance, will feed into that.
Very good.
Sorry?
It's quite independent from the processing. We see that also on other data sets, so it's quite pleasant
Okay.
in terms of interpretation.
Yeah. Okay.
So I'm enjoying the discussion a lot. So we continue also in the coffee break. So thanks for that, but we have to move on.
Thank you.
Thank you, John. So we have another presentation by Simon Origo, right? And it's about investigating the fault motion of the 24-25. Yeah, we're moving to Ethiopia, and it's a bit volcano-related tectonic activity, right?
Right. Yeah.
Please.
Yeah. Okay. Good morning, everyone. So today I'm going to present about this fault motion during rapid and transient stress changes, in this case caused by the dike intrusions in Ethiopia. And I will be using INSAR observations to track them. So we know that, to put in broader context, the magma intrusions can go laterally and propagate and perturb the stress field of the surrounding crust. And this can cause different seismic and seismic slip in faults in the same place. In the case of Fentale-Dauphin dike intrusions, it's a large-scale dike that release a geodetic moment of equivalent to a magnitude 7.1 earthquake. But unlike tectonic earthquakes, this is released gradually and not in one step as we can see in tectonic environments. So in this case, you can see here a snapshot of the dike intrusion in one of the most active phases of the dike, and overlying a catalog of more than 150 earthquakes relocated using template matching technique by colleagues from IPGP. And these earthquakes are related with normal faulting waveforms, really shallow. So they are not the complete catalog of the earthquakes, but we can use that to track the deformation and try to correlate the seismicity with the INSAR images. So in this case, from this catalog, we have that the total moment released by this earthquake was a 6.4, which differ largely with the geodetic moment from the dike. In this study, we are focusing on an area 15 kilometers of north of the dike, ahead of the dike intrusion, because basically we can separate the signals from the dike intrusion from INSAR and the signals from the earthquakes. And in this area, we see a large seismic moment release from the earthquakes, in 7 earthquakes in roughly 3 months. And they are correlated with the dike phase, the different dike phases But also we see some of these earthquakes when the dike was arresting, which is also interesting. And all of these earthquakes are moderate magnitude earthquakes from 4.5 to 5.7. And it's the place of one of the biggest earthquakes in the sequence, which is this one, the magnitude 5.7 earthquake. So in order to investigate this seismic and seismic slip, we will try to separate the different periods. But one key important thing that we have to care about is the temporal evolution of the deformation. So in this case, you can see here a comparison between the Sentinel-1 acquisitions with the CSK data. And we see that in this panel, the SAR acquisitions times correlated with the earthquakes in the area. So in this case, we see a much more temporal constraint by the CSK data is much better than the Sentinel-1. So in this case, it's a key thing because we can separate the different coseismic periods and also the interseismic periods between these earthquakes. And that is particularly useful to create the time series. But before creating the time series, we have to care about the different problems that we have with the data. One of them is that we have earthquakes producing really complex ruptures in the surface. So that generates phase discontinuities on the original interframes. And these phase discontinuities can generate problems with the unwrapping using the standard approaches. So you can see here the unwrapped phase that we rewrap in this case of the standard approach of using a SNAFU, and the assessment of the loop closure show like big patches of error in the graphing. So we follow the approach about the manually masking the phase discontinuities. This has been tested before by different papers. In this case, we use the phase gradient as base map and manually mask all these high phase gradient lines in this map in the middle. We map these lines, and then we use that as mask of the original interframe. So we mask out all these high phase gradient lines from the original phase interframe. So then, after using that, we produce a re-unwrap of the original interframe, but now with the masked image. And we improve a way better the result from the loop closure assessment, as you can see here. So the total improvement that we have in this case is we assess 170 triplets, and we improve this 52% the RMS of the loop closure in this case. So after having confidence in our surface displacement, we generate the time series, and we correlate each step in the time series with the earthquakes in the catalog of the seismic catalog. So you can see here all of these red vertical bars represent one earthquake in the catalog, and they are correlated with different coseismic signals in this case that you can see here. These are the regraph interframes from the time series incrementals deformation. And also you can see here the time series of the pixel TS in the middle of the surface deformation. And so you can see the different periods that are showing a clear step in some of the earthquakes and also interseismic deformation. So as I said before, we can also separate these periods between earthquakes, and also we got some of these deformation showing like kind of a seismic deformation. For example, in the interframe CD, you can see some of the deformation there. So that's also a clear pattern that we can see in this place that we have a closely related deformation from coseismic and interseismic deformation. So in order to try to understand this behavior, we propose different ways that the fault can behave. The first one is that we have one earthquake, for example, in the same fault, and this is repeating every time in the same asperities. This means that we can have every time this rapid and transient stress from the dike can unclamp the fault, generate one earthquake, then we can also generate another earthquake in the same area, and this can be related with fluid pressures changes, for example, that reduce the effective normal stress, and we unclamp the fault again in the same patches. But also we can have the slip migration along the same fault plane. That is also related with the same dike-induced stress that can put the failure in different asperities in the same fault patch, in the same fault plane, and produce different earthquakes along the strike or along the down dip in this case. But also we have a third hypothesis, which is related with the slip partitioning in different areas. So basically we have subparallel faults going on, one earthquake in one fault and then the other earthquake in the other subparallel fault, and this can be related with the stresses between one earthquake to another, between subparallel faults as well. But also we can see some seismic slip in this case. The seismic slip, it can behave like a typical main shock after slip behavior produced by the dike that produce the co-seismic slip, and then we have after slip up dip in this case. So in order to test the different hypotheses, we first model the earthquakes, the co-seismic periods, and this is the network of the best fit model that we got from the elastic dislocation model. So we use a two-steps approach. First, a non-linear approach to try to constrain the fault parameters. And then we use a linear least square approach to generate the slip distribution in different fault planes. So you can see here one fault, the main fault, number one, is dipping towards the reef axis, and the other one, 2, 3, and 4 are dipping away from the reef axis as well. So here I will show you the different co-seismic slip distribution models for the different earthquakes in the sequence. So first we have the first earthquake in the 13th of December 2024 that ruptured the fault number 4. And the geodetic moment is equivalent to a magnitude 5.2 earthquake, which is correlated really well with the seismic catalog as well. Then we have the biggest earthquake in the sequence that produced the more complex deformation. So you can see here that this is rupturing the fault number 1, but we have some of the residuals in the edge, in the southern edge of the fault 1 that cannot be explained by this model. So we need to add more complexity to this, and we try to add 2 more fault planes in this case that could explain better the observations in this case. So we have this earthquake is rupturing the fault number 1, number 3, and number 4 in this case. But the main seismic moment release was for the main fault, which is the number 1, and it's releasing 73% of the total seismic moment, which is equivalent to magnitude 5.7 earthquake, which also correlates really well with the seismic catalog. Then we have the same fault number 3 producing repeating earthquakes in different areas of the fault. So this is really interesting because we have that the fault number 3 ruptured the earthquake, the biggest earthquake in this area, in the first area of the fault patch. Then it's migrating along the strike to the second earthquake, number C, in the center. You can see the co-seismic slip there. And then the third earthquake 1 month after the number C, the number D, we can see the co-seismic slip going down deep in this case. So this is a clear example of the same fault plane with the slip migration in this case. And then the last earthquake is the letter E, which is rupturing a new fault, the number 2, and it's releasing a geodetic moment of magnitude 5, which also correlates well with the seismic catalog. But also we can try to study the different periods between the earthquakes. So here you can see profiles perpendicular to the best fit fault planes in this case. And the panels here are showing each of the interseismic periods between these earthquakes. So you can see here in the number in the northern area, in the fault number 1, that we have most of the loss displacement generated by a seismic, this is a seismic deformation, by between the period B and C earthquakes in the red profile. So you can see that the deformation, it's showing a clear pattern towards to the fault trace, that it's correlated with a seismic slip, and this can be translated to after slip, for example, in up deep, in the case after the earthquake number B. In the case of the southern area, we have a more complex rupture with 4 different earthquakes, but we don't see a clear deformation between interseismic periods. We don't see this clear offset as we can see in the northern part. So that suggests that either we don't see any after sleep between the earthquakes, or this is really tiny and we are not capturing the after sleep because the level of noise is above this kind of loss displacement deformation. So some of the takeaways about this talk is that we see some evidence of the afterlives in the fault number 1, as you can see before in the profiles. That we have a big earthquake, in this case the earthquake number B, and then after sleep up deep in this case. We don't see a clear evidence of after sleep between the repeating earthquakes in this case, but some of these faults are generating a sleep migration in the same fault plane, which is also interesting. So this is a clear evidence of that we have different heterogeneous properties. In this case, it can be, for example, hydrothermal activity in the southern area, or material properties facilitating, for example, the seismic sleep in the northern area. And more takeaways is that we don't see the repeated rupture of the same fault patch in the sleep distribution, but we see this sleep migration of the earthquakes in the same fault plane. And also we see the sleep partitioning across the fault network. So the next steps will be try to model the static Coulomb stress models from the dike and see if we can correlate that with the failure of this fault network, for example. But also try to test the Coulomb stress change between the faults to see if one earthquake is stressing the other fault and reaching the failure in the other fault and producing another earthquake. So yeah, thanks you for listening, and that's all.
Thank you. And we have time for some questions. Gareth, over here.
So this is cool. I'm wondering if you've looked at slip to length scaling or strain drops or stress drops to see if these are typical for tectonic earthquakes in this region, or the faults are behaving in a different way with different strength.
Yeah, no, I haven't compared you mean the stress slip?
Yeah, so you can take the ratio of slip to length or something like that, and that gives you some kind of proxy for stress drop.
Right. Yeah, no, I haven't done that, but yeah, it could be interesting thing to do.
Because you would think that these mechanically behave differently from regular faults, but I guess that would be my prejudice, not actually, I don't actually know.
Yeah, right. Yes, exactly.
Any other questions? If not, I have a question. Further south, obviously, the faults are very clearly related to the magmatism.
Yeah.
Have you got any evidence for magma in this region, or any signs of that moving this far north?
Yeah, I mean, if you look at for example, this kind of interference, you see like the signal in the corner. That signal is related with the dike. So possibly, yeah, it's reaching the southern area, magma-related fluids is going on through different faults and producing and unclamping the faults more easily. That's my theory, but we will need to test in different ways, like static stress modeling and that kind of things.
Thank you.
Yeah.
Any final questions? If not, let's thank Simon again.
Yep.
And the next talk, I believe, is going to be given by Shimon. And this is going to be on, we're moving to the Caribbean. So over to you.
Okay, thank you. Good morning, everyone. This presentation is work by my postdoc, Michelle Higgins, who couldn't come. So I'll present on his behalf. And it's work that with colleagues in Venezuela, Omar Perez, and my colleague at FIU, Jim Kellogg, and the title is Sentinel-1 INSA reveal complex strain accumulation at the southwestern Caribbean, South America transform plate boundary. So the plate boundary let's shift to the Caribbean plate and the plate boundaries. So Caribbean plate moves eastward with respect to the two plates that are bigger, the North American plate to the north and South American to the south. And these plate boundaries are transform plate boundaries. Later this afternoon, we have a poster about the northern boundary, about post-seismic deformation in Haiti. But now we talk about the southern part, the southern segment of the Caribbean South America plate boundary, which both of them are left lateral boundary, transform plate boundary. So let's zoom over there, and we can see that it's a complex boundaries. They have many faults. We can have, let's see. So that's a pointer? Okay, but we cannot see much. Anyway, so we have several major faults. The most familiar one maybe is El Pilar fault, separating in the eastern part of the plate boundary, and then the complex faults in going into Trinidad and Tobago. But we are focusing on the western part, where we have the San Sebastian fault and the La Victoria fault south of that, and they accommodate, both of them, these faults accommodate about 20 to 22 millimeter per year. If we zoom into that, we see it's further more complex, where we have the two major faults. The San Sebastian fault is offshore, and La Victoria fault has actually two segments. We have the western La Victoria fault and the eastern, and in between there are smaller faults and basin, pull-apart basin. So it's a complex plate boundary when we go into the details. The seismicity is, we can see, mostly in the north, associated with the San Sebastian fault in the offshore. And onshore, we can see some clusters in the region of the West La Victoria fault and a little bit to the east. So the seismicity is associated with also there's some urban area over there, the Caracas and La Victoria is right over there. So there's a seismic hazard associated with that and implication for that. The geology, what we see, the different blocks were accumulated over a long period of convergence. They have the late, if we go from south to north, We have a Jurassic unit to the south with horizontal line, and then there is a Cretaceous unit with a diagonal line, and the vertical line is the more recent that been accumulated over there over the period of the motion of the Caribbean plate. Now, we mentioned the seismicity, so there is the capital of Venezuela is Caracas right over there, and there are at least two major earthquakes that impact that. We can see an image from the 1812, magnitude 7.7, estimated as 7.7, that impact the city, but the most recent one was in 1967, was magnitude 6.7, that caused a lot of damage in Caracas. We study it using INSAR, and the approach that we took is we use the long temporal short perpendicular baseline strategies that it's a paper we published last year, where we use both a short temporal baseline and also very long temporal baselines that enable us to overcome some issue related with unwrapping. This is a very challenging environment because it's a tropics, it's vegetated, and in order to minimize issues related to unwrapping errors, we chose this approach, looking for very long. And when you have a very short perpendicular baseline, less than 5 meters, we can still have good coherence even over 800 days or even more than 1,000 days. So that was proven to be very good, and with that, we were able to show in the papers that we published that we can detect at the level of 2 to 3 millimeters per year. And then we do the time series analysis, looking for the linear plus seasonal and semi-annual patterns. So this is the velocity field. What we can see over here, first, it's patchy because only in certain area we had enough coherence. It's the urban area of Caracas over there and Valencia. These are the two major areas where we are able to see, and some areas that are less vegetated still provide sufficient coherence. So that's the reason for this patchy appearance. And we still see in these areas gradients of the velocity. The velocity is in loss. It's from 0 to 8 millimeters per year. And all the velocity reference to the GNSS station of the university over there in Caracas. The way I'll explain the velocity field going from west to east and explaining each segment what we see. So the first is the western La Victoria segment. Over here we can see a complex pattern of both increase, low velocity, high velocity, and we explained these gradients, high gradients, is because of a complex pattern of fault that generate both compression and extension, push-ups and sag basins, and overall the motion over there estimated to be up to 15, with vertical 15 millimeters per year. And to notice the city of Valencia is right over there, so it's important to understand the potential of seismic hazard. Next segment is the Victoria Basin, pull-apart basin, and the velocities over there going southward in between the Lago de Valencia and the Santa Rosa fault. We see up to 5 millimeters a year, which we explain as subsidence. Next segment is the Eastern La Victoria fault, shown over here. And again, we see a concentration of high loss velocity and It's explaining it as just by a horizontal fault is not enough. So we did an inversion using the Okada 85 dislocation models, and we found that unless we use a vertical or normal fault over there, we cannot reduce the results. So our conclusion was that there is also, besides the horizontal, the strike slip fault, there is a normal fault over there that accommodate about 5 millimeter a year of subsidence over there. The next segment is La Victoria creeping segment farther to the west. And we did some inversion result, and what we found that there is a creeping east of the intersection with the Kata fault, and it's about 5 millimeter a year, accommodating 5 millimeter a year of the Caribbean South American plate boundary, and we see different behavior east and west of the intersection with the Kata fault. The next segment is farther north, is the San Sebastian fault, and it's offshore, so it's we see along what we ever able to observe along the coast, and there's a few GNSS station, and doing an inversion, we found that the western part is locked mostly, and the eastern part of the fault has some movement. The western part is where they estimated to be the 7.8 earthquake around 1900. And so we, based on that and our inversion, we estimate that magnitude 7 and above can be generated over there. The model also requires 8 millimeter a year of reverse motion east of the intersection with El Avila, which is the next segment I'm going to describe over here. And inversion of the velocity field over there revealed that part of the fault is locked and some is moving. Based on our result, we suggest that the 1878 magnitude 6 to 7 that in the past was attributed to La Victoria fault is actually happened over there, and therefore our analysis suggests that it can generate 6.6 magnitude earthquake, and it's right where Caracas is. So it's something to keep in mind. And so based on this, the fault kinematics, we see the different blocks of different terrains that accumulated over time. And so it's the complex plate boundaries that we have the Caribbean plate to the north, but the deformation is accumulated not only on the San Sebastian fault, that's about 17 millimeter, but farther on different faults, as we saw the West La Victoria and the East La Victoria. In between, we have a complex of the basin, and then we have the El Avila fault that also accumulates some of the fault over there, of the motion over there. So basically, we have a complex figure of accumulation, of strain accumulation over here. And to summarize, we see that the western segment of the San Sebastian fault is locked and it can produce a magnitude 7 earthquake. El Avila fault is partially locked and can produce a magnitude 6.7 or similar. And both San Sebastian and El Avila represent grave seismic hazard for the capital city of Caracas. Victoria Basin is a polar part basin, but it's not fully developed. It can express the strain is subsidence about 5 millimeter per year. La Victoria fault creeps at low magnitude seismicity and cuts through high gradient of vertical land motion. And the eastern Cordillera de la Costa, which is the mountains where Caracas over there, is structurally different from the western Cordillera de la Costa. So thank you. And I hope I can answer the question. If not, you need to contact Michel, and he will provide a much better answer than me. Thank you.
Okay, thank you, Shimon. Have we got time for some questions? Gareth.
I may have missed it, but did you try and filter out non-tectonic motion from your data? Because I wonder, most of your coherence is over cities, and those are the places where people pump groundwater, and I wonder how much that might affect the results that you're getting.
Yeah, it's a long debate between Michel and me. How much is tectonic, how much is hydrology? We have to deal with that issue. It's hard to estimate how much of that is associated with the hydrology in the basin over there. I think we have more subsidence than tectonic, but it's very difficult to estimate that.
Well, one way might be to look at the time series, I guess, a little more closely and see if you see like an overprinted, like seasonal.
Yeah, we do the time series. We do actually look for the pattern of the seasonality, and but maybe the magnitude of seasonality that can be key for that.
Great. There's another question just down here.
You use the line of sight velocities, so were you able to combine ascending and descending to better constrain the east-west and vertical velocities?
It's very, I think it's only we used only ascending. I'm not sure, we need to find with Michel. But we couldn't do, it's a loss velocity, it's not, we didn't separate to horizontal and vertical because I'm not sure there is enough observation on both tracks. So there is limitation. Not everywhere we have such a nice coverage with both ascending and descending. So I think it's descending only.
Okay, great. I mean, perhaps another recommendation then to try and get ascending and descending over here as well, if the data don't exist. Any other final questions? If not, let's thank Shimon again.
Thank you.
And we've got one more talk in this session before the coffee break, and that's going to be given by Paul Deron. And it's going to be on, I've lost my notes, triggering of creep on secondary faults. So over to you.
Thank you. Hi, everyone. I'm Paul Deran, and I'm going to discuss about post-seismic creep on secondary faults after large earthquakes. So what you see here are the interferograms from the 2019 Ridgecrest earthquakes, computed by, I took them from a study from Shu and collaborators. The Ridgecrest earthquakes consist in a sequence of two large earthquakes, so magnitude 6.4, followed by 7.1 on a conjugate fault. If we look, so there are a lot of fringes because it's quite large earthquakes rupturing at the surface. But if we look into the detail, we can see that some fringes are slightly offset, and this might correspond to shallow creep on shallow slip, sorry, on secondary faults. To look at this into more in a more systematic way, in the study they had a look at the phase gradient from so they stacked the phase gradient from several coseismic interferograms. And what we see here are like several structures, some of them corresponding to secondary faults. What they later did was use several line of sights and range in azimuth directions to obtain east-west and vertical or north-south relative displacements. So the large structure that you see to the north of the image is the main fault of the 6.4 foreshock. But we also see several secondary faults. Some of them creep in the same sense of motion, and some of them are retrograde, so they slip in the opposite sense of motion compared to like regional tectonics and the main faults. The authors observed that the retrograde faults occurred in places where regions where the Coulomb failure criterion was diminished by static stress changes from the earthquake, while the prograde faults were in areas where stress increased. So they proposed a model where stress decrease on secondary faults that were loaded in seismically take them further away from the rupture, resulting in large wavelength compliant, well, relatively large wavelength compliant deformation. Whereas for the faults that where stress increased, well, it just triggered frictional slip on these structures. We see some shallow creep on secondary faults after several other earthquakes. Another example from the literature is the IT 2021 earthquake, which is magnitude 7 earthquake, which here I show an infogram. So in color you have the phase, and the light intensity shows the gradient of the phase. And these linear features that you see that are labeled correspond to slip on secondary faults. On the same area, Brian Rimbaud and collaborators identified several other faults in a post-seismic time series and found that some of them were right lateral, some of them left lateral, and that you could predict the sense of motion of these faults from the shear stress change caused by the main shock. This suggests that these faults could be frictional faults, and the temporal evolution of slip kind of confirms this hypothesis, as we see that the relative motion decays over time over the course of a few weeks. Given these multiple examples, we may wonder what are the mechanisms of post-seismic slip on secondary faults. So I'm gonna show you a few INSAR time series to see the temporal evolution of slip on these faults. We're also going to compare the motion to the coseismic stress changes. And so one question was whether it was like something specific to Ridgecrest or the IT earthquakes. So we also wanted to have a look at another earthquake, which I'm mostly going to focus on, but I'm also going to come back afterwards to the Ridgecrest case. So this is the region I've been mostly studying during my PhD. So it's the Eastern Anatolian Fault, where the Kahramanmaraş earthquakes occurred in 2023. So this is a doublet of earthquakes consisting in a magnitude 7.8 and a magnitude 7.6 earthquake. So on the two main branches of the main branch and the northern branch of the Eastern Anatolian Fault zone. What you see in color is the line of sight displacement of post-seismic displacement for 2 years from 2023, so just after the earthquake, to late 2024. You see, of course, the large-scale motion associated to viscoelastic relaxation, but you also see some more short-scale, like small-scale, and like some sharper gradients, which are associated to shallow afterslip. I'm going to show a few examples. So the ones that I've encircled here are all the secondary faults that we identified creeping in the post-seismic time period. I'm just going to show a few examples. So this is the eastern part of the seismic rupture of the second earthquake, but we actually see that some of the faults that creep in the post-seismic are not the ones where we observed a lot of slip during the earthquake. So especially the one to the south. This Surgu fault supposedly did not creep so much during the main shocks. We also see like a large amount of creep on the Peturge segment, just to the east of the rupture termination. So the rupture probably ended somewhere here around the the Yarpuzlu double bend, but we see creep further to the east, approximately for like 40 or 50 kilometers. This is a segment that's been creeping in the past, so notably during the interseismic further to the east, but also there has been some post-seismic creep after the 2020 Sivrice earthquake further to the east. But now the biggest motion we see is in the western part of the Puturge segment. If we plot a profile across the segment, so here it's the black rectangle, this is what we obtain. So here I show cumulative displacement as a function of distance to the fault, northwest to the left and southeast to the right. We see the displacement at different dates colored by time. This is the ascending track, and if we subtract motion from both sides of the fault, which is actually quite sharp, so we have approximately 500 meters of the width of the deformation zone, suggested some shallow creep. So we obtain this relative motion as a function of time. We can combine different line of sights to estimate fault parallel motion, which I plot here in blue. So the overall trend is a decay, which we can fit to get an estimate of the relaxation time, approximately here 0.8 years, using the exponential fit. If we look into more detail, we see that this global trend is like made of several bursts of creep. So this is something that has been observed in post-seismic measurements of after-slip, notably in creep metadata. But so it's fun to see it in the INSAR as well. So if we go back to the overall trend, we measured this relaxation times on all the faults we identified, so there are 38 of them. And we see the relaxation times mostly between half a year and 1 year. Okay. We can also compare this to the decay of the aftershock sequence. Here I plot in red the seismicity around the Puturge segment, so it's the same area. And it fits, it compares quite well. For the seismicity of the entire region, it decays a bit faster, but this might be also just because the other faults also mostly creep a little faster. Oh yeah, sorry. The fact that seismicity and creep kind of decay at similar timescales might indicate that they might correspond to, might be due to similar mechanisms. So that's why we wanted to check if they responded accordingly to seismic stress changes. To do so, we're using a seismic slip model that you can see on the left. So it's a static slip model based on geodetic data. And from this, we can predict seismic stress changes. Here I plot Coulomb stress changes and compare it to the total slip on these faults. So when it's positive because these faults are all how do you say? They're all in agreement with the tectonic regional motion. And most of them correspond to positive variations of Coulomb stress change, suggesting that they have been brought closer to failure by coseismic stress changes. For some of them, though, stress changes are almost zero, and this might be the ones that are, that might be because they are further away from the fault. And so over the, like in the far field, the dynamic stress changes are stronger than the static stress changes, and this is mostly what they see. So here I just show one example of these far field faults. It's a place where there is subsidence in a basin just to the east, to the west, sorry, of the city of Kayseri, due to groundwater pumping. And so we observe a seasonal vertical motion due to water retrieval in summer. but it's also somewhere where the fault bounding the eastern side of this basin has shown some normal faulting just after the Kahramanmaraş earthquakes. So we mostly see on the descending track because it's aligned with the sense of motion of this fault. And we see approximately 25 millimeters in line of sight. So this is the plot to the bottom here. And then it gradually decays to join the interseismic trend, which we obtain using flat sim data from French National Space Center. So to give a brief key points of what we saw in the Kahramanmaraş earthquakes, we see post-seismic creep triggered on secondary faults. It's mostly compatible with regional tectonics and mostly also enhanced by static Coulomb stress changes. It decays in time on a yearly scale, like aftershock activity, although this large trend can be composed of several bursts of slip. And depending on how far these faults are from the rupture, we could interpret these as a result of static stress changes or dynamic stress changes. I'm going to show you a little bit of of my work on the Ridgecrest earthquakes as well, but it's a bit more recent, so I haven't went as deep into the analysis. Still, these are the post-seismic 5-year cumulative displacement maps, which have been which come from the Opera framework. So what you see is, of course, mostly the earthquake post-seismic deformation. We also see some subsidence to the north of the rupture, which corresponds to the Koso geothermal field, and you see some mostly seasonal, I believe, motion to the east at the Toronto Salt Lake. Here I overlay in blue the fractures identified by the Xu and collaborators paper that I cited in the introduction. And I added in red the faults that we identified using INSAR time series. So I'm just going to show one example, fault to the north, where we don't see much motion on the ascending track, but we see some in the descending track. So the eastern block is moving towards satellite. And so that means that we have some right lateral motion on this fault. Totally approximately 1 centimeter over the course of half a year or 1 year. We did the same kind of analysis, so we made a static slip model from geodetic data, and from this model we estimate static stress changes. For the Coulomb stress, which I don't plot here, this is a shear stress change. For the Coulomb stress, it's mostly positive, but what's quite fun is that we can kind of see that we can predict the sense of motion of these faults based on the strike slip shear stress changes for the strike slip faults. There are not only strike slip faults, but I only plotted the strike slip ones here. So this kind of recalls the figure I showed from the IT earthquake in the introduction, and suggesting that these faults are just reacting to the coseismic stress changes. So to conclude, we see this shallow creep on secondary faults after both the Ridgecrest and Kahramanmaraş earthquakes. These structures generally slip in the sense of regional tectonics, and they are also promoted by static stress changes from the main shocks. However, some far-field events may not feel these static stress changes as much as the dynamic stress changes. And finally, the decay of slip rates with time indicates a frictional behavior of these secondary faults. That doesn't mean that that doesn't mean that there are no compliant fault zones, of course. It's just that we don't see them because we're not looking at the same time period, as our time series don't include the coseismic interferograms. Thank you.
Thank you. We have time for some questions. John.
Thank you very much. That's a great talk. This is a perfect figure, actually, that the Eastern Turkey is an example. You identified it demonstrates slip pulses in there. You've got the overall decay of about 2/3 of a year as your relaxation time. But if you instead consider it as a summation of those pulses, have their own relaxation of a much shorter time, how would that change your interpretation of the rock rheology and the behavior of the frictional faults? Or is it just a shorter time scale?
That's interesting. Thank you. I think it might be interesting also to consider the interactions with the aftershocks. I tried to look at it a little bit, but it's still in progress, and sometimes it might be worth saying, like, of course, this is one profile, so it's in one point of the fault, but it can be influenced, and there might be some like propagation, or so it might be stuff to look into 2D and also compare with the aftershocks to gain more insights of why does it stop and why does it start again. Thank you.
Another question on the front.
Did you look to see if any of these sections were creeping before the main shock events, or were you entirely focused on the co and post-seismic?
I had a look at the seismic time series from that was provided by the FlatSim French service. And we see actually some creep on the Pütürge segment, so to the east of the main shock for Kahramanmaraş. So there is some creep on this segment. It also further, like we also see, so we see some creep. We also see some afterslip from the previous earthquake in 2020, which is further east, but still we also see it. So. And in this plot, I removed I detrended the data, so you only see the post-seismic motion.
Thank you. Yep, one more question.
Thank you, Paul. Getting back to the aftershock creep interaction, in terms of distribution in depth, is the creep distribution at the same depth as the aftershock, or is it separated? How does it work?
Okay. In terms of depth, well, I'm not exactly sure of how constrained is the depth of the aftershocks. I mean, I'm using a relocated catalog, but still there are some uncertainties. Most of the aftershocks are around 10 kilometers, but it's variable. But the creep is, well, for Pütürge, it could be a bit, it could be in the first few kilometers, I guess. So mostly above, I would think so.
Okay, thank you. One final quick question then.
Yeah, it's about the compliance zones. So in the co-seismic, when you have the retrograde motion, you said that the previous authors had assigned that to compliant deformation. But when it's moving in the right direction, it's probably not only slip, because those faults are probably also compliant. So it's probably a mix of slip and compliant deformation, or just compliant deformation co-seismically. What's your take on this?
I think I agree with you, because it's true that, there's no reason that they would not be compliant if they're in the same kind of medium. And so, yeah, it's probably both. Like in the medium field, we see the compliant deformation, and in the very near field, we would see the creep.
But you didn't see any of these retrograde in the post-seismic?
No. But I guess it's probably because the compliant part of the deformation might be instantaneous. Yeah. So and I don't include co-seismic into my time series. So that's my idea, but that's actually something I should check next.
Yeah, if it's very weak, you could think maybe it has some time constant too, some kind of viscoelastic.
Yeah, I'll definitely have a look at the. Thank you.
Thank you.
Great, thank you. Let's thank Paul again.
Thank you.
And thank all the speakers and everyone for their questions. And do come back. We have 2 more tectonics sessions and a round table and posters, etc. So there's lots more to see. Back in here at 11:10. Thank you.
Hello.
Or not advanced, and this is supposed to be the pointer, but people there's your control. Thanks. Yes. Switch at that one. Yeah.
You're going to present? No, there's somebody else.
I believe so. Apparently everything is uploaded according to Aula, although I think she was talking about the presentation of the other parallel session. She went off to check.
He handed this at the very last minute. According to the wall clock, it is 10 after the hour. I think that means we're supposed to start. Well, I don't know. Shall we wait a minute longer? Who wants us to start? Could we have the first presentation up? Yes. Brilliant. Okay, so let's get going. We're going to start with Hannes Vasiura-Bathka. He's going to talk about slow slip events in the Permian Basin.
Yes, thank you, Gareth, for the introduction. I'm Hannes, I'm with SkyGeo, and I'm going to present a case that we have been working together with one of our clients from the energy industry here on a slow slip event in the Permian Basin. For those people who might not be familiar with where and what the Permian Basin is, I'm showing you here the official and free viewer that SkyGeo provides for everyone to use. The Inside INSAR Permian Basin viewer. We are here in the southwest of the United States. This is the state of Texas. And you see here several tracks of SAR data that we actually update with each incoming acquisition. So this is up to date for most of the tracks in June already. Admittedly, this is downsampled to a lower resolution, but for a first glance of the most exciting features, I would recommend you to check it out and try it out. It's a lot of fun. Yeah, now you know where the Permian Basin is, but probably you might not be knowing what the Permian Basin is. Here that's kind of a schematic view of the geological cross-section of a lot of sedimentary sediment layers that have been deposited throughout the Permian. That's why it's called the Permian Basin, which is a geological time. And you see a lot of different layers here and a lot of text on the slide. The only thing I want you to take away from that is that you have these horizontally deposited layers, all have varying porosity, and the ones with the higher porosity also carry the oil that is being produced by the energy industry. And most of the production wells, which are marked here with black vertical lines, and then they also go horizontally, they are produced from the shallow layers. And these days, a lot of the production needs to be stimulated with additional water. So the produced mixture of fluids is largely consisting of non-oil related products, and they need to be put somewhere. And that's been done by injection wells or saltwater deposit wells that inject into the deeper layers of the Permian Basin. So yeah, that's basically all what I want to say here. Now let's look back to the viewer here. Now we are going to look particularly into the eastern part, the so-called Midland Basin, which is in its particular, it's kind of has the geology that I've been showing before. It's a slightly different, but not that it matters. So now we, for our story here, now there's a lot of things going on. So we zoomed in to that Midland Basin. Here for you, for reference, you have a spatial scale. So you have the orange continuous lines, which these are marking the main frontal thrust of the region, which is southward dipping. So you have a northern branch and a southern branch, and they're separated by approximately 5 kilometers in distance. Then I want to draw your attention to these white circles, which are earthquakes of local magnitude above 1.5. They reach up to 3.9. And then you have also a temporal scale in that slide we are looking at, which is basically from all the beginning of the data time series we show here, which is early 22. The black line marks kind of the primary reference, and the red line marks the secondary reference we use here to produce the spatial map. So we are looking here basically at the pre-event time where not much is going on yet. And I want to focus your attention as well on these smaller circles. Some of them are yellow and some of them are darker blue. These are wells in the region. The yellow ones are those ones that have the shallow production, and the darker ones have the deep injection boreholes. trajectories. And then you see also still these blue circles where I highlighted kind of the temporal time series of our data here that we are going to discuss a little bit more about. So the right one shows this panel and the left one shows the lower panel. And you see already, so at the beginning, okay, it's fairly flat, but then we see, okay, up to January 2023, we have here some interesting signal going on. I just noted that I messed up these arrows. So actually this time series belongs to that lower circle, and this one belongs to the right circle. Sorry for that. And you can see basically, wow, there's an uplifting consistently feature here in the lower left, and a subsidence pattern here to the upper right. So, or not the subsidence, maybe we talk about range increase and range decrease. And then if you continue in time, you see also the earthquakes get more, and but that uplifting lobe of the deformation disappears, and we are mostly seeing only this dominant subsidence, which is due to that production of the hydrocarbonates. One thing I also want to draw your attention to is that all these earthquakes are kind of located north to the frontal thrust here. So now what? Oh no, I pressed the black button. Do not press the black button. Press it again. Oh, yeah, good. Sorry. So what can we do with that? So the hypothesis here, as it is presented in the title as well as in the abstract. So yeah, this might be a slow slip event on a kind of a subhorizontal plane that has been triggered, or let's say is coinciding with our production operations here. It has not been triggered. We cannot say that yet. But we want to know, okay, yeah, what's the orientation of that plane, or the feature where is slipping what? Probably most of you know how these things work. I still want to explain it a little more. So we have the surface deformation going on, and you can determine actually the fault parameters in the subsurface, like the location or the size of the fault plane, the orientation of the fault plane, and the faulting mechanism, and the magnitude of the slip. And actually, we developed a nice tool for that in the last forever years. And I just want to advertise it a little here, take the chance that you can do a lot of that with it. You can use GNSS, you can use INSOR, you can use waveforms, you can use amplitude spectra, you can use onset polarities of seismic data, and this allows you to determine these source mechanisms for a really wide range of earthquake sources, reaching from very small point source approximations of these magnitude 1 earthquakes, going to higher with intermediate range magnitudes where you would use a single fault approximation, as we would be using in the follow of the study, over a single distributed slip or even multiple distributed slip parameterizations when you want to know interseismic locking, as here in the Sea of the Marmara, for example. So yeah, check it out. You have the QR code here. It's basically, you can find everything in pyrocco.org if you are more of the older generation that I am. I would like to type still addresses. So then one thing I want to highlight, because I got reminded of our discussion on Monday on that, where we were saying, yeah, if you give the same data to different groups of people, you end up with different time series of deformation. I got flashbacks of that in the earthquake source inversion community. They have exactly the same debate. And there one a big aspect is that we really need to quantify parameter uncertainties of our parameters to be estimated. Maybe now, for example, earthquake source parameters, or we also estimate parameters of time series of deformation, for example, in PSI. So there are Markov chain Monte Carlo methods where you can basically map in 1D probability distributions, or in 2D even. These probability distributions allow you to investigate trade-offs between those. And that's what I want to show you now. So we did that actually now for that slow slip event. So we first are going to look at a few parameters: the dip, the depth, the width, and the slip on the single fault plane we have been looking at, where darker regions show regions of high probability, and fading regions have low probability of the fault parameter to be like a likely solution. But you see many parameters basically lead to the same, explain the data to the same level of quality, so basically the uncertainty of involved data as well as model uncertainties. So you see typical trade-offs where you have a certain width trading off with the depth, and likewise dip and slip. So you can expand that to all of the model parameters, and you get a better picture of what actually your ensemble of solutions may look like. It's not only the single red dot as we still see in many points, in many papers published and or talks. Still, I show here now one 3D representation of that red dot in 3D here. And we see it's a kind of a northwest-southeast oriented fault plane with with shallow dips between 10 and 30 degrees. And if you were to estimate the moment magnitude of that event, it's fairly large. It's 5.1 to 5.3. So here I'm showing the also the data residuals. Unfortunately, I only had the chance yet to use one data set. Left you see the data, in the middle you see the model, again with the solution plane in the middle, the upper edge marked as black. And in the right, you see residuals and also the histogram of how much of data we explain. So we explain within uncertainties kind of 70% of the data. Now I'm showing you again the solution in 3D together with the seismicity actually. And you see the seismicity is actually far deeper than our imaged fault plane of that to be hypothesized slow slip event. They reach up to 10 kilometers, all up to also shallow 1 kilometer events. Yeah, this is a GIF, it's not going to stop. And we, again, as I said, we have magnitudes ranging from very small to 3.9 local magnitude again. Yeah, basically that's only the repetition. I need to have time in mind. So we have a northwest-southeast striking fault with a fairly large moment magnitude and a swarm of seismicity adjacent to it. So now, do we see that actually elsewhere, not only in the Permian Basin? Yes, we do. Here are 6 other examples of these inferred slow slip events in 2017, 18, 19, 20, 21, 22, 23. So in total, we found 12 of these slow slip events. And all of them are having close by accumulated injection of volumes of considerable size. And also some of them, not all of them, show seismicity. So some of them here marked with those red of these triangles, they show seismicity as well, but many of them actually do not show seismicity at all. Yeah, so here's again a spatial map where does this happen. Now actually here we moved location, we are in the Western Canadian basin, so oil carbon production location, which is basically in the eastern back arc thrust of the Rocky Mountains. And you see they span fairly long latitudes. And if you plot all those inverted moments versus the actual occurring seismicity in that area, so in blue you see the seismicity, the moment, the cumulative moment of that plotted versus the cumulative moment of the inverted slow sleep events. You see that those have a considerably larger accumulated moment compared to what we actually can see with seismic data. So there's a lot going on. We hypothesized that actually all of these events have very shallow angles, so between 0 and 30 degree deep angle, and each of those events has close by saltwater disposal. And we think, or we hypothesize that the shallow slip on the roof of here, in this case, it's the Montley Formation, is being lubricated by the saltwater disposal, and because of the stress field from the western Rocky Mountains, the back arc extension, you allow this lubricated fault to still release slip. Yeah, that's about everything. I want to show you here still again, invite you to that viewer I've been talking about. Here's the web page inside INSAR. You just need to make a small account, and then you're free to browse what's going on in the Permian Basin. Yeah, thank you for your attention.
We have time for a short question or two. There's one, Henrietta at the front. On the way.
Yeah, thanks, Hannes. Did you allow for opening for your slow slip event? You are using just the INSAR data, right?
You only do use INSAR data. I have not shown that here. Indeed, that was also one reviewer comment. Could this be related to horizontal and vertically oriented cracks that are opening indeed? Yeah, unfortunately, I don't have the slide. I can show you later. It does not allow that because we have very asymmetric deformation lobes. So which are then opening with the same amount in both directions, you would also require symmetric deformation lobes in your SAR data, which you cannot explain. So I have run several of those inversions. It's not working.
Great, thank you.
Thank you.
Right, let's move on. Now, our next speaker is Feng-Yin Chan from Leeds. Oh, thank you. From Nanjing, but working with people from Leeds. And he's going to tell us about work he has been doing in the Tian Shan.
Okay, hello everyone, and thanks for the kind introduction. I'm Feng Yan from Nanjing University and the commit at the University of Leeds. And today I will talk about kinematics, dynamics, and the seismic potential of the Tian Shan from Sentinel-1 INSAR and GNSS observations. So I will structure my presentation in 3 parts. The first is using INSAR and GNSS to measure the interseismic deformation and the strain rate, which is the observational foundation of our study. And second, I will use strain rate fields to invert the fault slip density rate and the seismic potential of this area. And finally, I will move from kinematics to dynamics, try to answer what controls the deformation in the Tian Shan. So here is the tectonic background. Why is Tian Shan? We can see this map. Tian Shan is located in the Central Asia, which is affected by the far-field effect of India and Eurasia collision. And now the tectonic active is very active in this area. And the shortening rate is about 20 millimeters per year in the western and the central Tian Shan, which is about half of the plate convergence rate. So Tianshan is also seismically active, and in this area, there are more than 100 moderate to large earthquakes occurred. So study this area also have some society reasons. I mean, which Tianshan, this area, we have a lot of infrastructure such as energy pipelines and the railways, so which is important to this infrastructure stabilities. So we use INSA to measure the surface deformation. We're mainly using LIXA data, which provides the standard INSA interferogram products, and is publicly available on the LIX Comet portal. And for the time series analysis, we use LIXBus, which is just, we can refer to this figure, which is from John Elliott's paper. It's a whole procedure. So actually, the large volume of data is very important for this area because the tectonic deformation rate is relatively small. So we need a long time series to get a high precision of the velocity. And besides from that, we also do a lot of corrections to separate the tectonic signal from noise. So here we can see we correct a troposphere, which is a bit of long wavelengths and also some short wavelengths based on the Geckos data. And we also correct the ionosphere and plate motion, which is long wavelengths and relatively large over this area, which is few millimeters per year. And we also correct solid earth tide, which is long wavelengths, but not doing much. And we can compare figure A and F, which are before and after corrections, which are on the same color scale. And we can see after corrections, we can get a much smoother and more consistent long-term rate. Besides from that, we also correct the co-seismic deformation. Because during the monitoring period from 2014 to 2024, there are several moderate to large earthquakes occurred in this area. So we use two strategies to remove the co-seismic displacement. The first one is fitting a step function pixel by pixel, which is if the earthquake occurred during the middle of the monitoring period, we prefer to use this method. Here, the red line represents our corrections. And obviously, we assume that deformation before and after the earthquake have the same velocity. So, I mean, we ignore any post-seismic deformation signal. And for some earthquakes occurred during the beginning or near the end of our monitoring period, we prefer to truncate the time series. I mean, only using data before or after the earthquake. So here is the comparison of our corrections. The first figure represents the loss velocity before corrections, and the middle one represents after corrections. And we can see after corrections, our velocity, I mean, the long wavelength trend term have been greatly removed after corrections. But now the velocity are still referenced separately, I mean, relative to a stable point or a small region within each frame. So next step, we try to align this velocity to the same reference frame, which is aligned with our GNSS observations. And we can see the GNSS data is inertia fixed reference frame, and we align the long wavelength data between INSA and GNSS. And we also applied a threshold mask to mask some localized deformation associated with, such as here, associated with the groundwater extraction, which is a very extensive area, and the velocity is relatively large. And in the Tarim Basin, there are also some localized uplift or subsidence, which is related to the oil and gas exploration. So here is the GNSS data we used. It's about 1,000 GNSS velocity vectors with respect to the inertia fixed reference frame, and which is also a subset from the AHB dataset compiled from published literatures and conduct a series of iterative corrections and alignments. We interpolated the GNSS velocities using view map method. In this way, GNSS can provide the long wavelength horizontal reference, and the inside can provide the high resolution data. So next is about the velocity decomposition. And to recover the 3D dimension, we use GNSS interpolated noise velocities. In doing so, we projected the velocity to the line of sight direction and remove it from the original inside velocities. And then for each pixel, we can combine ascending and descending to solve for east and vertical components. But we found some problems for the existing decomposition methods. I mean, when we zoom into the overlapping area between different frames, especially in the across-track direction, we found some velocity discontinuities are still remained in the velocity field. I mean, maybe some residues are still remained in our line of sight velocities. So we proposed a method to using spatial weighting to account for such discontinuities. I mean, this figure represents the spatial weight. So the main idea is to try to make sure a smooth transition in the weights rather than a sudden change when we solving for the weighted least square equations. So this map represents our corrections. I mean, after corrections, we can get I mean, the weight is transit smoothly. And for pixels, only with one ascending or descending observations. I mean, in the middle of these frames, we set the spatial weight to 1, which means we do not apply spatial weight. And we combine our spatial weight with the formal uncertainties from LixPath, which is calculated using bootstrapping. And we use the revised weight when we solving for the weighted least square equations. So finally, we can compare the results. I mean, after the spatial weighting, the discontinuities along these boundaries can disappear. So finally, we got the east and the vertical velocities for this area, and which has a spatial resolution of 500 meters and to cover about 2 million kilometers of the Tianshan and surrounding area. And the east velocity show a good agreement with the GPS data with the linear regression coefficient of about 0.9, but the vertical velocity are more difficult to interpret. I mean, it may reflect the non-tectonic deformation. But anyway, in this study, we mainly focus on the horizontal deformation and the strand rate. So we also estimate the uncertainties from redundant observations, which is followed the method proposed by Tim Wright and John Elliott. So in areas with 4 line-of-sight observations, we calculate the east and vertical differences in this diamond-shaped area, and we found the final uncertainties for the east component is about 1.1 millimeters per year, and for the vertical is about 0.9. And we also estimate the line-of-sight uncertainties in the 3 observations area. I mean, finally, we estimate the ascending line of sight is about 0.8 millimeters per year, and the descending is about 1.1 millimeters per year. So the next is about strand rate calculation. I mean, strand rate mainly represents the gradient of the velocity field, which can represent from which we can see where the deformation is concentrated. But and when we calculating the gradients, I mean when we calculating the strand rate, the noise in the velocity field will influence the strand rate calculation. I mean the noise will be amplified when we calculating the gradients. So we proposed a method called refined bilateral filter method. And the main idea is to combine 2 kernels. The first one is spatial kernel, which is considering the distance between, I mean, the spatial distance between different pixels. And another one is we call value kernel, which combines the velocity differences during the filtering. So finally, this method can better recover both magnitude and the spatial localization of the unforced strand rate. And if you are interested in this method, you can come to my poster in this afternoon. So here I compared the INSA-derived strand rate fields with the GNSS-derived strand rate fields, as well as the global strand rate model version 2.1. And we found in the large scale, the different models show similar patterns. I mean, the high strand rates are mainly concentrated in the Pamir frontal fault, as well as the fault thrust belt in the southern Tian Shan. But INSA strand rates reveal much more localized and higher magnitude of strand rate. So now we have these observations, we can try to answer how this strand is related to the active fault. So we use a strand rate-based inversion method, which is proposed by Kai Johnson. The advantage of this method compared to traditional block model is that it doesn't require predefined blocks. So which means because defined blocks in Tian Shan area where active faults are developed very closely spaced, it's very hard. So we use this method, which allow us to systematically invert for sleep deficit rate around this fault. And we compiled the active fault from different databases, and we also collect the earthquake from different catalog, which will be used in the next step when we calculating the seismic moment. So here is the inversion result. Inversion result from which we can see the high resolution INSA data can reveal much more details about the fault sleep deficit rate, and we can see some high sleep deficit rate around the Pamir and also the boundary fault of the basin within the Tian Shan area. And we also compared with other different modeling strategies and the published geological sleep rate, and we found that there is a loose agreement. I mean, the discrepancies may arise from different fault geometry and also the limitations of geological sleep rate measurements. I mean, maybe it's limited on a localized area, and also related to the timescale dependent variations in fault sleep behavior. Another important conclusion is that about 60% of strand rate is accommodated by major fault. I mean, by the interseismic coupling of the active fault, while the remaining part may be explained by the diffused crustal deformation, and also may reflect some inelastic deformation, or may from some unmapped fault or unmodeled fault in this area. So based on this sleep deficit rate inversion result, we estimate the seismic moment accumulation for each fault segment. There are a lot of assumptions. I mean, we assume that the earthquake energy are accumulated since the last major earthquake. I mean, from our earthquake catalog, and for segments without documents, seismic events, we set the accumulation time to 1700, which is the same as the starting time of our earthquake catalog. And for earthquakes lacking precise location constraints, we just associate them to the nearest mapped fault. Absolutely, it will introduce some uncertainties, but it gives us a practical way to measure the seismic moment accumulation. And finally, we found about 20 out of 400 fault segments are capable of generating large earthquakes, which is larger than 7 in this area. And there are also a lot of uncertainties in our inversion and calculation. So the last part of this talk is about the deformation dynamics. We try to answer what controls the present deformation of Tian Shan. So to answer this question, we use a 2D vertically averaged viscous shear model, which allow us to explore the influence of boundary stress and the lithosphere strength on the deformation pattern. So to focus on the Foster order pattern, we downsample our observations to 50 kilometers basin, and we set the boundary conditions for boundary 2, 3, and 4, which is located on stable inertia or far away from the Tian Shan. We just set the velocity to be 0. And for boundaries affected by Tarim, Pamir, and Tajik, we use our velocity field to fit the Euler pole and the rotation rate for this area to constrain these boundaries. And for the boundary one, it's a little complicated because we found our velocity are parallel to this boundary. So we just set the normal velocity to 0 and the tangential force to 0 because the magnitude are also similar in this area. So with these boundary conditions, we set 3 model settings. The case 1 has a uniform lithospheric strength. It can test whether the boundary loading alone can produce the velocities that we observed. So here, the blue arrows represent the observations, I mean the downsampled inside velocities, and the yellow arrow represents our model predictions, and the figure B represents misfit, and the green dots represent the misfit smaller than 2 millimeters per year. I mean, more green dots means the model is better. So in the case 1, the average misfit is about 4.5 millimeters per year, and cannot reproduce the observed velocity very well. And in case 2, we include the laterally variable lithospheric strength. I mean, we use parameter search to search the best parameter combinations, and our best solution gives average misfit of about 2.1 millimeters per year, which means that the lithospheric strength for this area is a key factor that's affecting the deformation pattern we observed. A weak Tianshan lithosphere surrounded by stronger blocks is important to explain the deformation pattern. And in case 3, we further added the fault in this area. I mean, in this area, because our strand rate fields have revealed a very concentrated strand. So we add some faults in the Pamir frontal fault and also the Tajik fault, and it can further reduce the misfit, especially among the Western Tianshan area. So we think the fault may mainly modulate the velocity fields, I mean locally rather than regionally. So here is the comparison of different model settings, and we can also compare with our observations, and we can see for the north component, our best model, case 3, can predict the north component very well, but for the east component, there are still some misfit concentrated in the Pamir and Tajik region. And here is also our best model, and here is the lithosphere strength, which is represented by the effective viscosity. So finally, we conclude the best fitting model shows that the indentation of the Tarim and Pamir, I mean the boundary loading, is the first order driver of the percentile deformation in the Tianshan. And a relatively weaker Tianshan lithosphere is required to reproduce the velocity fields that we observed. And the effective viscosity is 2 to 10 times lower than the surrounding tectonic units. And actually, I also try to include the buoyancy force from gravity potential energy, try to see whether the GPE can have some effect. But I found the misfits are increased when we add the GPE effect. So I think from the preliminary result, I think GPE, I guess, is not the necessary condition to explain the deformation pattern we observed. And the large misfits are around the Pamir and the Tajik region, so which may be related to the plate convergence in this area. So in the future, maybe we can consider to add the basal traction to the model to try to fit this area. I mean, the main misfits are around this area. And in the future, we can also try to increase the model complexity and the resolution, try to constrain the lithosphere differences within the Tianshan area. So here are the 3 main messages that I want to convey. Due to the time limit, I will leave here, and thanks for your attention. By the way, I'm also actively looking for a postdoctoral position, so potentially start from October of this year. So if you are, I would be very happy to discuss any possible opportunities. Yeah, thank you very much.
Any questions or postdoc offers? Is someone at the back? Anyone? JD?
Sorry, not a postdoc offer, but thank you for your talk. Very wonderful work. I'm just curious if, based on your fault modeling, I guess you could call it, will it be possible to extrapolate uplift rates on, or at least uplift rates on individual faults? Yeah, I guess that's my question.
I mean, you mean which modeling? The sleep deficit rate?
Yeah, yeah, the sleep deficit rates.
Actually, I mean, we only using strain rate to invert the sleep deficit rate. So strain rate is calculated based on the horizontal velocities. So we didn't consider any vertical components of our velocity fields. And actually, we can see our three-dimensional deformation. We can see the vertical velocity here, which is largely contaminated by non-tectonic deformation. So it's really hard to say such deformation pattern is controlled by a major fault or something like this. And besides from that, the velocity fields here are also suppressed when we align our inside velocities with the GPS data. I mean, when we calculating the referencing surface, we only considering the horizontal component of GPS data. So finally, the result show that the vertical component. So I think it might be not true, because when we compare with GPS data, it's only zero. I mean, no clear correlation between these two components. So we didn't use vertical components in the modeling, but maybe in future we can improve it.
Okay, thank you.
Yeah, thank you very much.
I have a question regarding the model that you described, the different strengths.
Yeah.
If you can show the slide.
Different, you mean?
No, with different strengths, one uniform strength and the other with variable strength and then with faults.
I see, yeah.
Yeah, over here. So adding the faults didn't improve much the RMS. There's not much difference between.
Yeah, between.
Yeah, so maybe there is a hidden fault that you don't account for that maybe you need to find another fault that.
Yeah. Yeah, actually, we can compare these two figures. I mean, the least sphere strengths for these two settings are the same. So we can see the misfits reduced are mainly concentrated in the western Tianshan area. I mean, in this area. So I guess that the affected range of the fault is only regional. I mean, maybe proportional to the length of the fault rather than the regional. I mean, we also got some misfits around this area. The fault and the thrust belt developed in the Tianshan. I mean, the Kashi, Keping, and Kuka, and also Manas fault and thrust belt, where a lot of closely spaced fault and thrust belt are developed. So in this small area, we can try to use more, add more fault to further reduce the misfits. But actually within the Pamir and the Tajik region, it's really hard. Maybe the reasons are more complicated, so we need to refine it. Yep.
Okay, thank you.
Thank you very much.
More questions?
I just want, again, really impressive work. No doubt we'll see it again. But just wanted to comment on that Tajik area. It's an area we know that there's a lot of basal shear happening, and I wonder if you account for that, that slow basal shear deformation, you could resolve those remaining issues.
Yeah, I guess I can try. Yep, actually, there are also some other reasons that we have misfits around here. We can see the strain rate map, because here there are also closely spaced fault developed. So we can also try to incorporate more faults in this area, but I mean, we want to keep our model as simple we want to use the most simple model to explain our observations. So it still needs further investigations.
Okay. Other questions? Okay, thank you.
Thank you very much.
We just discovered there was a scheduling issue, and we have actually extra time because they scheduled only 4 instead of 5 presentations for this session. So Gareth can spend a little bit more time.
Oh, you'll wish you hadn't said that. Hi, everyone. So I'm going to talk about a different style of scale of movement, I guess, looking at one of the largest earthquakes that's happened during the INSAR era, I think the second largest, the Kamchatka earthquake of 2025. And I'm going to make the case that perhaps, even though it was a huge earthquake, it wasn't the big one on that subduction zone. This is work I've been doing with my postdoc, Axel Periola, at UCR. Okay, so subduction zone earthquakes are really the main game in town when you're talking about seismic moment release. I updated the classic pie chart of total global seismic moment release that was originally made by Chuck Ammon after the Sumatra earthquake. And what you see basically is that 7 earthquakes count for almost half of the global seismic moment release since 1900. And Chile 1960 is still a colossal beast. That's a quarter of all the recorded seismic moment that's ever been recorded on instruments. I'm going to talk about Kamchatka, though. Kamchatka, there's 2 earthquakes that happened there, one in 1952 and one in 2025. Between them are about 5% of the global seismic moment release, and they're both located up here on this peninsula. And 1952 was the first magnitude 9 earthquake recorded on instruments, and it was a great earthquake. It happened during the time of Stalin. There's not an awful lot of information you can get officially on what happened there, but there are some pictures of the damage to a particular town. Here is on one of the northern Kuril Islands, some tsunami damage. This event destroyed the town of Severokurilsk, which is what I'm showing you here, with about estimated 15-meter local run-up. And there are estimates of run-up from various other places, including 6 meters in Hawaii, 4 meters in Japan, 2 meters in New Zealand. This was a big tele-tsunami. This has inspired people to go and map tsunami run-up in Kamchatka and the Kuril Islands. Bree McInnes did this work in collaboration with some Russian people, and they found sediment run-up of up to 18 meters. And that town I just showed you was located right here. And of course, there was another earthquake and another tsunami, and this is the Severokurilsk contemporary town, 2025. They moved most of the town inland, so it didn't get destroyed again, but the port facility obviously got inundated with water. And I played around in Google Earth, and you can more or less find where this is, and you can kind of map out what the elevation of various parts of the land was, and toggle back and forth, and see, well, yeah, probably 4 meters of run up here in this particular tsunami, so smaller. And the smaller tsunami in general, there are some still high local run-ups, but across the Pacific Basin, generally speaking, the tsunami was smaller. This was an earthquake that happened now in the time of modern tsunami monitoring. We were able to actually issue warnings ahead of time to places, and luckily, most of the time, the warnings were of a smaller tsunami, and much less damage was done. So 1.7 meters instead of 6 in Hawaii, 1.3 meters instead of 4 in Japan, and so on. Anyway, the questions I want to answer in this talk are, can we identify the source regions of these potential earthquakes using geodetic data before they happen? What do geodetic data tell us about this particular earthquake? And geodetic, in this case, is Sentinel-1 INSAR. And then this question of whether either of these earthquakes actually was the big one in this area. And I'm going to say they probably were not, which is unfortunate, I guess, if you are worried about seismic hazard from this area. but maybe it'll be a few hundred years before we get the next one. Okay, so how can we identify potential earthquake source regions objectively with geodetic data? Unfortunately, this is not an INSAR-based assessment. We're going to use this GPS data set here that was compiled by Steblov and Bergman et al. This is interseismic campaign GPS, and it's still, unfortunately, the best interseismic deformation field we have. I tried to process in Sentinel-1 time series over here. It's forests and snowy. It's really not a good place for Sentinel-1, although maybe one day we will have a good NISAR data set of this. But anyway, what we want to know, of course, is how much of this subduction zone is locked and how that locking is manifest in the interseismic geodetic deformation. And the first person to really bite into this deeply was Roland Bergman, and he published a paper 20 years ago showing that you could fit the interseismic GPS using a kinematic model. And the real novelty actually, because lots of people do this kind of thing, you just solve for the slip on every element, but he went one step further and used a boundary element model in which you can specify which elements of the fault are fully locked, and then assume that the rest of the fault is creeping, and then basically calculate how much of the fault needs to be locked, given that everything will move around it to fit the data. So this gives you a map of where the fully coupled areas of the subduction zone might be, and you can use that as a basis to estimate the seismic potential and the sort of the loading on the subduction megathrust interface. The details of how this is done in this scheme, you backslip each of the locked elements, and you allow the rest of the fault to sort of freely slip associated with that, and then you add the slip back, and then basically the areas that you were backslipping tend to zero, and then the rest of the interface is creeping at various speeds. And it's that distribution of creep that's mostly providing the displacements or the velocities that you're trying to match. Anyway, one thing you identified from this is that only a small proportion of the elements actually need to be locked in order to fit the data. And the other thing is, I should have said, that the way that they actually chose which of these elements were the locked ones, they started out with a model of what they thought, or a kind of vague distribution of where they thought the earthquake was in the previous event, the 1952 event, and then just shrank the asperity down until it kind of fit the data. They didn't have a very objective way of fitting that. So I asked, is there an objective way to fit these data? Not assume that you know whether it's going to fit where the last earthquake was. And so we developed such a thing. It's based on a Metropolis Hastings algorithm, so an MCMC type approach, in which basically you start with a random lock distribution of elements. You have a few choices of actions that the algorithm can do. It can add a new element. It can take an element away. It can add an element as a neighbor of an existing element. And you run this. You calculate the misfit of the model. You see whether or not the misfit is improved. If the misfit is improved, then you take that step. If the misfit is not improved, then there's a probabilistic test you apply to see whether or not you accept that model, and you either do or you don't, and then you do this lots and lots and lots of times. In our case, we run this now for about 10,000 iterations, to which point the model has evolved to some kind of end state, which is a configuration of potential locking on the subduction zone, and then you run 1 million of those. So we run lots of forward models to do this. And so the details of how we do this are maybe beyond the scope of this talk, but they are soon to come out in a GRL paper led by Axel. And we use the TriBEM boundary element model code that's pretty fast. We backslip our locked elements at 80 millimeters a year, which is the plate rate at this location. We use triangular element Green's functions to calculate the actual effect of the slip on the land where we have data. And as I said, we generate 1 million different realizations of a locking model, and this is like one example of one, starting with like a handful of locked elements, and over time they kind of accumulate in places where and those are the black elements, the ones in the places where you think you need them, or the model thinks it needs them to fit the data. So yeah, what we look at is 1 million of these. I mean, you average the locking state. Basically, each locking vector is either 1 or 0, 1 for locked, 0 for not locked. So you take the average of 1 million realizations for each element, and you'll get a probability of locking for each of those elements. Shown here, the redder colors are the ones that are highly probable to be locked, and the blue are highly probable to not be locked. And we get this big blob, cluster number 1 of potentially locked elements. And we have to specify some kind of boundary to this. We choose 0.45 probability of locking as that boundary, because we did the calculation that if you use the plate rate for the number of years since 1952, then the moment stored is equal to the moment released in the 2025 earthquake. Both epicenters of the 1952 and 2025 earthquakes occur within that boundary, and this is most likely the zone in which both those earthquakes occurred. Okay, so we did this, and we did this last summer, and we were going to present this anyway at AGU, and the day before the AGU deadline, this earthquake happened. It could really have waited another year. It would have been great, so we could have published our prediction before the earthquake happened. But you can see, the question is now, like, what do the data tell us about this earthquake? Magnitude 8.8. You don't get to study one of those very often, especially not in a place you've actually already been looking. So this is covered very well by Sentinel. Obviously, we're at high latitudes, so there's good overlap between all the tracks. And I processed pretty much everything that you can find here with Sentinel-1. Actually, I had much more trouble with ALOS-2 data. You would think that Sentinel-1 might decorrelate, but ALOS-2 has obnoxiously high ionosphere signals, and it's very hard to remove them. So we're going to go with Sentinel-1. We use the ICE2 software to process these. We try to use the shortest coseismic interval possible for all of them. So most of the tracks, that's a 12-day pair. We apply GACOS corrections for the long wavelength troposphere. We apply ionosphere corrections. It doesn't actually make a huge difference to the C-band data, not like the L-band. We mask out things that didn't unwrap properly, and we downsample them using a quadri decomposition. And the data look a bit like this. And these are double fringes. I realized, just so you can see them, this is 4 pi per fringe, or 5.6 centimeters. And you get good coherence, surprisingly. But I was surprised because my attempts to make longer time series really were not successful. But there is good coherence over 12-day periods, at least in the summer. And one thing to point out, I think that is important, is that if you look really closely at the fringes in this area, there is a rotation of the direction of the phase gradient. So you can see, that it's going that way, then that way, then that way. And by the time you get to this island down here, the fringes actually, the gradient is increasing to the northeast, suggesting that the end of the rupture is somewhere in here. And that's a helpful constraint for trying to figure out what's going on. Also, I want to point out that up here, there's a lot of excitement. Maybe you saw Paul Lundgren talked about this yesterday, but Krasheninnikov volcano, a few days after the earthquake started erupting, and this had never erupted in like the time that people had been looking at it. You can constrain the start of the eruption to basically the 1st of August, which is like 2 days after the earthquake. I'm not showing all of the data we have of this. There is a poster by Rekha Weber that will show you that. It's in the second room, not the not the first one. I don't know which one's what. The one without the booths. It's in there somewhere. And yeah, you can see that this started off with a deeper dike and then a shallower one. And it's quite cool to look at all the details of that. But not my story today either. So this is the unwrapped data. I did my best to try and stitch the data together across the islands. You can do that where there are fringes that are continuous. You have to kind of estimate what went on down here because it's quite separated from everything else. But this is the data we're trying to model, and we downsampled it. And we use the same mesh that we used for our interseismic deformation to model this, and we used the same Bruins functions that we used. We used Laplacian smoothing and all the good things, a positively constrained least squares inversion, and we fixed the rate to the direction of the plate motion. We modeled 3 scenarios, one which the slip is just uniform within the zone that we consider locked, one where we allow the variable slip, but only within that locked area, and one where we allow the whole thing to slip, and see how we do. Okay, so the first case, uniform slip on the whole locked zone. There's the whole uniform slip thing. It has a terrible residual, doesn't fit the data at all well, so we don't like this one. We thought that maybe, given that the probability of locking was higher in this area, we could try modeling just that, see if it did better. It does not. It does worse. So we don't like that model either. Now we start to get good models when we allow the slip to vary. And in this case, you see, I should have said, these are data model residual. So you can see where we fit the data well and where we don't fit it quite as well. But in general, this is for something with so much displacement, a residual of like 3 centimeters isn't too bad. And this model is the first one that fits somewhat well, magnitude 8.82. So we like that one. And then, of course, if you let the whole thing slip, then of course, it will fit better, and it does. RMS of 2.3 centimeters and a reasonable residual, but there's still some things we're not fitting. Magnitude 8.88. So yes, slightly larger seismic moment, fits the data well. So which of these do we prefer? I prefer the one which confines the slip to the area of our locking. In some cases, you could make the case that this explains both the interseismic and the coseismic data. And then other features of it, but the difference between this one and this one is that the more restrained model has less shallow slip on the megathrust. This might be consistent with the slightly smaller tsunami associated with this earthquake compared to previously. The more shallow slip you have, the more tsunami that implies. Anyway, so we're going to go with this one, and we're going to compare this to what we saw from what we can infer about the 1952 earthquake. And ask this question, was either of these actually the biggest earthquake you might expect on this subduction zone? And I don't think so. Okay, one thing that you can note, and I didn't really emphasize much yet, is that at 80 millimeters a year and a separation of about 73 years, that would imply an accumulation of about just under 6 meters of stored elastic strain to be released in this earthquake. Our model predicts 12, which is a lot more than 6. So, okay. So that kind of makes the suggestion that something interesting has happened here, and that meant that the earthquake got to be larger than it might have otherwise been if 1952 was a full rupture of the subduction zone. So you would have to have very rapid relocking of the subduction zone in a very short space of time. Potentially that's testable. I haven't showed it here, made any slides, but there's about 10 centimeters of post-seismic line of sight displacement since this earthquake from like July to October. Not super fast, not a super huge signal. So I think that's unlikely. The other possibility is that there's actually unreleased slip deficit from the previous earthquake cycle that was released this time, which means that, of course, that the 1952 earthquake wouldn't have been the big rupture because it didn't release all the strain. All right, that's the argument. Anyway, so you can look at what people think about the slip of the 1952 earthquake. This is all from tsunami run-up data by Bree McInnes. She came up with 5 plausible models that seem to fit her run-up data reasonably well. You can compare all those and see features like they mostly slip to the trench, and they mostly slip quite a lot in the southwest, and some of them in other places, and they are all bigger, and they're all like 8.9 or 9 in magnitude. If you throw on our model at the end here, you'll see that the slip is somewhat deeper than most of these, so there's less shallow trenchwood slip and less seismic moment in general. So of course the 2025 one is not the big one either, and they are somewhat complementary, although I think there's a lot of non-uniqueness in the tsunami models. Anyway, my thinking is that probably the 1952 earthquake slipped different portions of the megathrust to the 2025 one, and the 2025 earthquake released strain that was not released in the 1952 earthquake, and it's quite likely that neither of them actually ruptured the whole thing. So if 1952 wasn't the big one, what was? And you can go deep into the literature now and find traveler reports from Russian explorers and the like in the Aleutian Islands and the Kuril Islands. And this one quote from this compilation of Alaska tsunami observations of half-rotten driftwood piled up on the shore of Amchitka Island in the Aleutians. In some places 40 and 50 feet above the watermark. So there's about 15 meters of run-up in the Aleutians, which is attributed by natives to the terrible earthquake of 1737, which shook Kamchatka and the Kuril Islands. Okay, so that's my working hypothesis now. 1737 was the big one. This was a place, Amchitka Island, where the nearby run-up on nearby islands was more like 1 meter in both of the 1952 and 2025 earthquakes. So this is clearly a much different beast with a much bigger run-up. So that's my goal. That's my candidate. So that's what I've got. 2025 earthquake has a smaller tsunami and a smaller magnitude than 1952. We identify a region that's likely locked from GNSS using our Markov chain Monte Carlo modeling scheme. We can produce a model that agrees with both the interseismic and the coseismic data and models, but when we do that, we find that double the slip in the earthquake that we would have expected from the amount of strain that would have accumulated since the last earthquake. So our thought is that there was slip left over from 1952, and it wasn't the big one. Thank you.
Thank you. Any questions?
Thank you for your presentation. It's very interesting result. I think in your coseismic slip model, that's a uniform space, half space solution.
That's right.
Yeah, I think it's when we estimate the earthquake magnitude for seismology community, they use layered Earth green function. But for subduction zone, the rigidity variation along dipping is quite large, right? For the shallow part of the sediments, it's just nearly 16 gigabyte Pascal. But do you think it would introduce some bias in your slip model?
So we use a rigidity that's much higher than we would normally use for a continental earthquake for this case, and we actually tried a bunch of different ones. Yes, we use a 50 gigapascal rigidity because we're thinking that the main control is the slab and which will be stronger than regular continental crust. And yeah, you're right. We should probably do a lot more. Yeah. It gets difficult to model those things with more the complexity, but yes, I would imagine there could be ways of doing that more accurately.
Yeah, because from SWOT constrained model, the issue is a nearly trench breaching event, right?
Right, but not with a lot of slip. It's quite the slip went to the trench, but not like 15 to 20 meters, more like 5.
Yeah, in your slip model is more deeper than theirs, and it's some difference, right? But I think, did you think your model can explain the DART or the other tidal gauge observations?
It's close. It's not perfect. I haven't tried.
Okay.
I do not know how.
Thank you.
Over here.
Hi, Gareth. Thank you very much. Nice talk. I'm curious about I guess I can call it a locking inversion method. Does it consider the degree? Is it already considering like the degree of coupling on patches, or?
Well, it's a binary model, so we either an element is locked or it's freely sliding. One thing I didn't say because I had limited time is that you see in say the Bergman model where you had a lock patch, the patches around it were creeping at a greatly reduced rate. And if you go to elements immediately next to the lock zone, they're not moving at all interseismically, but that's because they are next to something which is locked. So there is a kind of a kinematic style of locking, which you might consider the partially coupled zone. That's absolutely built into the model. That you get that when you run this. That you will see that areas surrounding locked areas are behaving like they're partially locked.
Yeah, because I'm wondering if the, I guess, less the slip models from the co-seismic data showing less than what you expect from your locking models, could it be explained by partial coupling in some parts of the subduction zone?
Yeah, I think so. I mean, my expectation is that we'll see those areas slip more in the years to come in those areas surrounding the asperities. Unfortunately, in the mid-October, Sentinel-1 coherence is gone, so we have to wait either to make summer-to-summer pairs spanning years, or we have to wait for NISAR data to be released before we can say really what the amount of afterslip is for the earthquake in those zones.
Okay, sorry, last one. Could the locking probability be related to degree of coupling?
No, or at least not in this framework. It's kind of the average of lots of possible behaviors, right? So really what it is, when you see like a high blocking probability, that means that most of the models had locking in that area. And it seems that almost that there is a non-uniqueness problem in that, you need some amount of locking in some parts of the model to make the data fit, but there's not a very strong spatial constraint on where that has to be. So yeah, you can identify zones where some of those, if you call that partial coupling, I don't know, some zones where there has to be some locking and you can't very, very definitely say where.
Yeah, Gareth, thank you for your talk. It was very stimulating. I have more kind of a methodological question.
Oh, yeah.
So in that area where you have actually your very high slip of that 12 meters, I think that was more or less related to few patches in the southwest,
right,
where you also are very close to that unconnected islands.
It's closest to the connected islands.
And we know also from other inversions with in Tohoku, right, where there's a lot of trade-off between slip patch size and peak slip on those segments. And then there you also hear now of fairly far away from those closest islands. Have you looked into like in sensitivity or trade-offs between slip patch size and also your peak slip?
I have not, is the short answer. But you can see, okay, so these are the nearest Kuril Islands, and this is the one with the reverse gradient down here. So it is, and here you do see the strongest phase gradients, I think. So I think, yeah, this is, INSAR is making this slip the most. There is a constraint on it, and then down here, you're in the zone where you've passed the end of the rupture and it's dying off. Yeah, I don't have much constraint on what's going on up here from INSAR, obviously, and that's where the questions about modeling dart buoys and the SWOT data and things, if I knew how to do any of that, would help the model probably a lot.
Thank you.
I think we need to move on. So thank you for filling the gap.
You're welcome.
And the last presentation of the session, Andy Hooper is not here, but it will be presented by Mohamed.
Pick up visualize for Andy's not here because his flight canceled yesterday. Therefore, he will be here tomorrow. And so you can catch him until afternoon tomorrow. So yeah, I didn't prepare myself a lot because Andy said yesterday night, like, could you give a talk for me? I say yes, but sorry for if I'm a bit excited, but I'll try my best. So the idea is I'm Mohamed from University of Leeds, and then supervised from Andy Hooper and Tim Wright, and then I'll give you about the information, improved 3D cosmic deformation from increased burst overlap interferometry coverage. The idea is exactly the same. The methodology is from, if you attend the Ingvar talk in the Monday morning, is the extended BOI, is like, rather than the burst overlap, we can focus the data and then get much more coverage of the overlap region. So yeah, before that, what is the subSWOT and burst overlap interferometry? Actually, if the literature, we are SI guy, and then if you, in the literature, if you hear about the spectral diversity and spectral diversity for the co-registration, the idea is the burst overlap and subSWOT burst overlap is same. Like in the TOPS mode, we take the data is the burst by burst, and then to make the data is avoid the incomplete image, the TOPS is overlap between the bursts. So if in there is some spectral diversity, is nature spectral diversity. So if we apply there is double difference interferogram before and after an earthquake, for example, and then we have is there like backward and forward looking, and then applying a double difference interferogram, you can use this one is to extract the along track displacement, because double differencing is remove the other component like vertical. So yeah, in here like you see is the green point, normal burst overlap interferometry, and then if you use the red and blue, we call it subSWOT burst overlap, but its literature is also is burst overlap. So is exactly this precision is regarding this timing. So think about like in the first burst is taking, and then is going to the second burst, is second subSWOT, and then take it another burst, and going like taking a burst, and then second subSWOT, one burst, and third subSWOT, another burst, and then come back to the first subSWOT, and is taking is second burst of the first subSWOT. So is created different precision. So backward and forward, for example, is timing is opposite. Therefore, when you look at the phase information, you see the backward is blue, while is forward looking is red. So when you need to calculate that to change to radian to meter. So yeah, another problem is unwrapping. Okay, when you have the data, is burst overlap has some emptiness between the bursts. So it's like 17 kilometer empty, and then 1.5 kilometer data is another 17 is empty. So when you do the unwrapping, is there a struggle? Is convenient snap doesn't work there? One way you can do the unwrap it doing each burst separately, but is the referencing is become a problem, or you need to use something as a guidance. So in here we use the azimuth offset. So is in the azimuth offset, what we use is like, firstly, we filter the azimuth offset in an advanced median filter to detect where is the gradients change a lot. And then decide there is the near field mask is the yellow one in the. Yep, oops. Sorry. How do people make it? Ah, okay. It's a bit hard. Okay. Yellow one. Maybe can use it. Yeah, that one is our near field. You can detect from azimuth offset. And then we make it the histogram median filter is different sizes. For example, in the near fold is 32 candle size. In the far is the 96. Because we need to do it, because if you keep it like too big candle, you can lose the information in the near fold. After that, after the filtering the azimuth offset tracking, you can make use this as a guidance, because you don't need to unwrap the azimuth offset, and then you can make it radian and then wrap it, and then directly you can make the difference between the wrap BOI and then calculate the 2 pi step to guide the azimuth offset to unwrap the BOI, and then this unwrap BOI is here. We start from here and then end up with there. So, but you can say, okay, azimuth offset is low precision, but why we use this as a guidance? Is a good thing in the BOI data is the precision is a bit lower than the standard line of sight INSA. Therefore, the phase wrap is every 0.7 meter is phase cycle. Therefore, we need the like centimeter level of step of the unwrapping. Therefore, azimuth offset is quite enough to unwrap the data. Yeah, in here you see for the Kahramanmaraş example is the 1 for 1 track and is unwrapped data. and then is in here like for is it ascending? Therefore, is red one is showing the northward movement, while is a -1 is the southward. And then you can directly compare with the GNSS data in the along track projection, and then it's doing really quite well job. And then if you have a chance to look at this the C-band data for the dead earthquakes, as you can see the near fault is exactly big phase gradient and there's no signal is decorrelated, but the BOI low precision can help you to go in much more in detail in the near fault to understand how the phases jump there. So you can read more about our last year paper from the JGR. So yeah, it's like when you combine the BOI data with range offset and azimuth offset tracking, you can do the 3D composition easily. The idea in here, if you have a 1 pixel and then look at their like one ascending, one descending line of sight plus azimuth offset or BOI, you can decompose line of sight and along track projection to the ENU component is exactly real deformation from the earthquakes. So in the middle, you can see there is some line. And why? Because it's coming from BOI pixel. And then because the BOI is precise than azimuth offset, and then is observed more better. So you can compare the GNSS, everything is fit well. So yeah, it's like why BOI is important, because such a kind of information, when you put in the slip model, you can see some improvement. It's a bit hard to understand, but is just the uncertainty of the slip model, and then we try different combination. So green is good, yellow is bad. So if you combine only range and azimuth, yellow is much more. When you put the BOI data, green is getting increased, especially in the mono segment, which exactly north-south deformation is main component in there, because when you're going to up, its track is changing, and then east-west is getting higher. That's the idea. So if you have much more data, like from BOI, and then you can improve your 3D decomposition, and then the other slip and the model solution. But yeah, it's also like not only cosmic, like for example from Chaos Soji, like they're doing a really good job on the DATSI, like to catch the interseismic. Also, like you can do it with the post-seismic. After the earthquakes, we have like 2-3 years data, and then we process with the Comet leak system, and then I have another talk, and after the lunchtime, I'll tell you much more about the methodology, how I improve the LeakSAR and LeakSPAS for the BOI processing. But the idea in here, okay, we make the time series of the cosmic deformation of the Kahramanmaraş earthquakes, and then you can see in here how the ascending and descending BOI data from multiple frames show the deformation magnitude. So when you decompose with the line of sight this data of the Kahramanmaraş earthquakes, you can see north deformation in there from the BOI, and then it's exactly really good data to complement with the east component, because generally Feng give really good talk. For example, they say like they use the GNSS data to interpolate the VN N component, and then think the rest of the model. But we can use the BOI data and then help to maybe interpolation or directly use this data, because loss of model, you don't use the grid data, you just downsample. So this data is already a bit downsampled, so you can use it to make it your model well. So anyway, like the problem is still is when you do ascending and descending, still there is emptiness, and how can we make this emptiness much better, much it's standard spatial coverage like standard INSAR. So the idea is from Yangwar for DLR, or like processing is so easy diagram, but a bit hard for me to explain and to put it, but I try my best. So X diagram is like show the azimuth time, and then Y is the Doppler frequency in azimuth. So in top spot, there's a sweeping angle, is exactly because of this also backward and forward is created. But when this as in the azimuth angle make a sweeping, this make the change in the Doppler frequency in azimuth time. So this is all Doppler frequency change from the data, the sweep along to azimuth time. So that one, which exactly normally what we use as a maximum Doppler spectrum, and then light one we chop because this one is low, is not maximum, is getting in the edge. So when we standard BOI using, we use exactly overlap on the maximum Doppler spectrum overlap. But the idea, Yingvar is explained, is extended BOI. We use all possible area and also that light chop edge before. So we start from the routed product from Sentinel-1 and then focusing ourselves and then continue with this focus SLC to create standard interferogram and double differencing to calculate the burst overlap. So here we go, is left side for the Myanmar earthquake, standard BOI, one track. A long track is combined from different frame. And then when you plot with the grid, it's really hard to understand what is that. But in the right-hand side is extended BOI data. Is doing a really good job. Is almost 60% is covered. So you can directly with eyes, without doing any plotting in the GMT, you can directly see what's going on there. But we need to unwrap it, and then I unwrapped during the yesterday. Probably you see me in the exhibition room. I'm doing something like that. I'm doing that one. So it's unwrapped data in there, and then is ascending. Therefore, that one is going north, and then here is going south. So and then we can make some quick profile what's going on there when we're going a bit in detail. In the left-hand side, you can see azimuth offset tracking. And then when you make the profile azimuth offset BOI and SBOI to show how they good. So is the black one is azimuth offset is noisy. Therefore we don't want it because we need to make some filtering to make it like it's a line. But when you do the filtering, you lose the information in the near fall. But it's the blue and red is BOI and SBOI data. And then the important is how the data is coverage is very good, and then they really sweet well. So when we look at the corners, is a bit hard to see, but if you check the corner, is we lose the precision. Therefore is we need to check how much the coherence loss happen when we extend it, because it's not the maximum Doppler is just that light blue is make some azimuth loose. So when we look at that, and then you can see clearly some decrease in the coherence. Oh my God, I already updated, but last time we didn't see that, but here is the R coherence, y-axis is coherence 0 to 1, and then when you go into the corner, you see the coherence is getting drop, but we can say like 3.5 kilometer to 3.5 kilometer, in total 7 kilometer we can use is all information along track, while normally it's just 1 to 0.5 to 0.1 BOI is coverage. So the idea in here, like when we use the extended BOI data, we can exactly increase the burst overlap 5 or 6 times in azimuth. In the past, it was just 1.5 kilometer, but currently is getting 8 kilometer. And in range, normally 1 SWAT is 80 kilometer, but thanks to that is going to do 120 kilometer. So when you use ascending and descending and another ascending, like ascending and descending, you can exactly make the coverage around 100%. So it can be new observation for in the future earthquakes or from the Sentinel-1 data archive to process everything from zero to make the extended BOI and then put your modeling result. And that's all. Thanks so much.
Questions, please.
Yeah, thank you very much. Very interesting talk. I'm just curious about like it improves, like it reduces the noise, but it's still that directional thing, right? Like we say that the sensitivity is lower in the north-south because of this polar orbit, but it's still the same direction, right?
What you mean, like, is exactly the old theory, like what you exactly extract from standard BOI is a along track.
Yeah,
From that method is still in the along track.
Yeah.
Is if the answer of the question.
So yeah, I mean how it improves the north-south.
Is data itself improve the north-south, but I mean BOI, and then when you say extended BOI doesn't improve precision of the north-south, but we only increase the coverage. So when you increase the coverage, you don't need to make any interpolation or any guessing because it's directly coming from data. But when you're going to the edge, you don't lose the precision, you don't lose the resolution. Like is your data coherence is getting dropped, and then you don't the pixel is getting noisy, so you get much more noisy. But still is unit of the north effect in the along track is same. I hope is
Okay, and is it available? Like we could do it? Is a code or something to like?
Actually, yes, we just collaborate with the Ingmar, and then Ingmar help us a lot last couple of weeks. And yeah, I try to is GAFA is called as the software is GAFA. He shared with us the beta version. I'm not sure it will be publicly available. In the beginning, it was like that, but yeah, we need to ask the Ingmar, or probably he update on Monday. But I was in the flight. Yeah, is there's some software to focus yourself, but after that, you need to find any gamma. Normally we use gamma or any instant processing tools to focus SLCs to make the interferogram yourself. Yeah.
Thank you. Thank you very much.
Yeah, thank you. Maybe you have answered the question. So you've this data is from very recently, because I was wondering, so this is more a question maybe to the whole leads group.
Yep.
So for the Tian Shan, for instance, most of the deformation is north-south,
Yes.
right? And in some areas, there's not so much GNSS coverage.
Yes.
And in the very first presentation, we have
Mhm.
seen how important it was for INSA to really concentrate the strain.
That's a very good question, actually. Data is so new, but the point is the original data is not new. That's the many important things, because it's a Sentinel-1 data we use. So even if we don't do final data, we can use all archive, like from the 2014. So for the Tian Shan, the problem, when you look at the interseismic, we need to is mounting, is like compression. So there is not any big strike slip like in the Dead Sea or is Myanmar or Chaman or San Andres. Therefore, we look at the compression, and then this north-south deformation is a little bit distributed in the broad zone. Normally, I look at when I started my PhD, my study area was the Tian Shan. I spent almost 1 year, and then BOI is getting a bit problematic in there because of low coherence, and then this distribution characteristic of the deformation. But if you look at the Dead Sea, everything works so perfect because coherence is high, and then the north-south is only on the one fold. So with that method, can we make it better? I need to try and then tell it more, but if the coherence is high, and if the deformation a little bit much more localized, I believe BOI or extended BOI doing a really good job from my expertise.
Because you should also get then a better estimate on the vertical, right? If you have the north-south a bit better, even if it's distributed and not super concentrated on the fault lines, and we would expect then in the shortening that we would have uplift, right, around the faults or vertical motion.
I didn't understand how the effect of the. Could you?
Well, I was just, so if we don't have the north component,
Yes.
or if we just have it very smooth, then and we do the east-west vertical projection,
Yes.
then we are wrong on the vertical to some extent.
Exactly, like if you don't have enough geometry, your decomposition leakage, like for example, if you don't constrain the north well, this unconstrained leak to east, but generally going to the vertical. And then therefore, if you have really good north, like along track deformation, line of sight, along track, make the all three component much better. That's the main point. Yeah, exactly. Yeah.
Just
want to comment on the data. So the raw data is available, as you said, in the ESA archive. So basically, it requires a reprocessing to, but it's a custom processing. So this is a development by Norse, this experimental GAFA processor. It's not an ESA processor. So, and I think that's why it's not publicly available so far as I understand. I mean.
Yeah, Tim tried to say something, but yeah, maybe he answered that.
Yeah, I don't know whether Ingvar is in the room, but my understanding is the intention is to make it open source. He is in the room. Where is he?
In there, yeah. Thanks, Ingvar, you saved me.
Is that correct, Ingvar? It's open source, or it will be open source?
1 second, the microphone is going.
Okay, I think, yeah. I'm going to say that again with I can say it for you. You say it.
Yeah, I can. It will be, you can consider the beta version that Mohammed has as open source is already with the license. We haven't put it out for public distribution yet, but we are preparing the documentation and the pip install machinery and all that. So it will be out very soon. It will be in the ESA public license.
I guess I had a question, maybe actually it was maybe for cheeky one for Dirk, but if we wanted to, and there was a discussion after Ingvar's talk about whether this should be done as a one-off, people reprocessing their own data, or whether, given ESA are about to do a full reprocessing of the SLCs, whether it would just make sense to extend all the bursts and give us, and do that now. And whether ESA could do that for us. Because I think for earthquakes, it's fine, right? It's one-off processing, it's a few pairs. But if we want to get the long-term deformation of something like the Tian Shan, where the rates are slow, then it would be, thousands, well, whatever it is, hundreds of SLCs, thousands of SLCs that would need reprocessing. So it'd be good to understand whether it's even worth making that as a recommendation or whether it's just absolutely no chance.
One mission manager over there, where you can answer it. But I think I understand the problem or the recommendation. Okay, that's something because I think it's a recent development. I mean, this additional use of this additional burst part of the burst for this particular case. And that's very specific to the tops only, obviously. And so it's a question of, for some, yeah, maybe you can make a recommendation and discuss it on Friday. But yeah, I understand if you want to build up a time series of data and you don't want to do it yourself, then maybe there's something that can be arranged. Or I don't know. Yeah, I don't know if Nuno wants to comment on this.
I have a question.
Yes, sure.
Very impressive. But it seems like you have different quality of data, or when you do the coverage, the coherence shows variability. What is the detection threshold for the?
I didn't do any detection of threshold, therefore, like when we look at that, but I need to test first, and maybe is generally, like for example, for normal BOI data, I can say more. Like I do, if the coherence is getting then 0.3, I ignore it. But maybe we can do same thing, and then we don't need to go all the corner, like because is all extension is 10 kilometer, but is whereas the coherence is drop quickly, we can use 4 to for like total in 8 kilometer. So and therefore, like even by eyes, we can see like whereas the coherence is so low, so we don't need to use it a lot. But yeah. It would be like 0.3 or 0.4. Is there some diagram like if you go coherence? Yeah.
What would be the displacement that you can detect?
For displacement, what? Like
the equivalent. How much of movement you can detect?
Yeah, it's like for the cosmic, if the deformation is bigger than 0.7, is wrapped, is getting the wrapped. So in here you can see like is wrapped. So like red to red is around 1.4 meter in the for BOI. So you need to unwrap it in the cosmic deformation if the deformation is in total offset is exceed like 1.4 meter. But in interseismic cosmic we don't expect kind of big signal. Therefore, for the time series of the BOI, good things. We don't need unwrapping step. Therefore, it make everything is much easier. Yeah. Is it? Yeah.
All right, thank you. And I think
Tim say something, I guess, quickly.
So maybe it's related because the burst overlap is only 2%, or it's about 2% of the area that you can use. If you would have a slightly larger overlap, then you wouldn't need to do this spagat in terms of doing this extra part of the processing. So it's related to how the timing works in the processing, but maybe it's also a recommendation for future systems to have a larger burst overlap in case this could be exploited.
Could be what?
Yeah, then you wouldn't need this. I mean, if you have a larger burst overlap in azimuth, then you wouldn't give you those gaps. And
yeah. Tim say something.
Yeah, no, I think it would be great to have this on future missions and tune them so we have 100% coverage on the north-south. Just in terms of the precision, Mohammed's right, you need this large amount of displacement for a single fringe, but because you're essentially looking through the same troposphere, you don't have that level of noise, so they're much more precise. I don't know, Mohammed, maybe you could say, what's the smallest displacement you think you could measure with BOI?
For cosmic or for?
Well, for anything. I guess you're measuring these long-term post-seismic.
If you stop in my poster during the
there we go.
I check like Chaman Westlut, for example, one of the hardest one, Westlut, because a little bit deformation, a little bit distributed in couple of fold. Even in there, I catch the 5 millimeter year velocity. So is millimeter scale. We can catch with the BOI if the coherence is high by doing time series analysis. Yep.
All right. Thank you for the presenters, and thank you everybody for coming for this session. And we'll continue in the afternoon. And don't forget to come.
Yeah. I'll get my laptop.
Yeah, speaker is here.
You were the first one?
Yeah.
Look forward to it.
Mm-hmm.
Thanks for
Officially.
So 5 presentations. Aula.
Yes. Yes. I just got back from the uploading area. They're all 6 there. Well, I'm good. Cecilia is here. Thank you for accepting that.
Yeah, I'm going.
You can see it from there, and then you have your mics. Will be activated by the well, yeah, he kind of he handles them when he sees somebody needs to go. He activates them. Yeah, it's
So, hello everybody. Let's welcome to the third part of the earthquake and tectonic session. We have 6 presentations followed by discussion, and then there are many posters later on, so don't miss those either. So we will start with Yihong Liu. He's going to give us a talk on interplate rheological contrast revealed by asymmetric deformation after the 2023 Kahramanmaraş earthquakes. So,
Okay.
floor is yours.
Thanks, Ronnie, for introduction, and thanks to the audience. I really appreciate you are here after this such a short, long time. I think you really love my presentation. And okay, today I will talk about the post-seismic deformation after the 2023 Turkey earthquake. And I'm Ji Hong. And after an earthquake, there will usually following by some post-seismic process. For example, there are some after-sleep on or around the co-seismic zone, or some poroelastic rebound within the shallow crust, or some viscoelastic relaxation in the deeper depths. So all these three processes will result in the surface deformation, and our INSAR can capture this kind of deformation. And if our INSAR captures the very precise deformation, then we will provide a very key insight into the elastic and viscoelastic property of the crust and the mantle underground. However, our INSAR can only capture the deformation combination of all these three processes. It has been long question, like how can we distinguish between different processes with our INSAR data? Okay, and come back to our INSAR data. Usually we will take the advantage of the spatial capability of our INSAR data, because it can provide very spatial details of the surface deformation. But with the increasing data set of our INSAR data, like the Sentinel or the NISA, like this kind of satellite, it will let us be able to capture the post-seismic deformation in a full-dimensional manner. That means, in addition to the spatial pattern, like we usually use our INSAR capability, and we can also capture the temporal evolution of the post-seismic deformation. And even we can capture it in the three-dimensional, that is east-west, north-south, and vertical. Okay, given these advantages, what will happen if the post-seismic processes meet this INSAR full-dimensional displacement? Here I list the sensitivity of post-seismic processes to the full-dimensional displacement. Like in the traditional, like our idea, like the INSAR can provide a spatial deformation in the very details, but all these three processes, it can happen in the larger area. So if we add the temporal information, like the after sleep, it is we can consider it as an elastic process. It will happen at the same time across the fault. That means both sides of the fault will sleep at the same time. That means the temporal behavior across the fault is symmetric. But for the viscoelastic, if there are different viscosities across the fault, the temporal behavior will be asymmetric. And if we have the three-dimensional deformations, for example, the after sleep and the viscoelastic, for a strict sleep deformation, the post-seismic deformation will be likely to similar with the co-seismic pattern of the surface deformation, and will be dominated by the horizontal deformation. But for the poroelastic process, the dominant component will be the vertical deformation, and the deformation direction is reversed to the co-seismic deformation. So based on these different sensitivities of post-seismic to the four-dimensional displacement, we may be potentially be able to distinguish between different processes. Okay, if we keep this like different sensitivities in mind, let's come to the 2023 Turkey earthquake. This earthquake included two large earthquakes that occurred around the East Anatolia Fault. And this earthquake is because of the westernward movement of the Anatolia plate from the complex tectonic background. And if we see this topographic map, we can see the quite contrasted geological setting across the East Anatolia Fault. So, given that such a large earthquake and such a complex background, it will be followed by highly complex post-seismic deformation. So here we use 2 years Sentinel-Y post-seismic data to get the displacement. Here we collect the 6 tracks of Sentinel-1 data, with each track include 4 to 5 frames. And first, we using the INSAR technology to process the data to get the line of sight deformation. As we can see, the major deformation is across the East Anatolia Fault. And we all know that the INSAR line of sight deformation is more sensitive to the east-west and the vertical component deformation. So in the other hand, we also use the burst overlap interferometry to get the azimuth direction deformation. This kind of deformation observation is much sensitive to the north-south component of deformation. Although this kind of technology can only get the burst overlap observations, but we can still capture the general deformation pattern of the post-seismic deformation around the study area. So this is the post-seismic deformation, and as we learned from this morning's presentation, we know there are also very strong interseismic deformation. So I also processed the interseismic deformation before the earthquake, and to get the INSAR line of sight deformation as well as the burst overlap azimuth deformation. And I corrected the post-seismic deformation by this interseismic rate result. So for now, we have 4 observations with distinct geometry. So we can use the observations to get the time series of 3-dimensional post-seismic displacement. That's what we called in the beginning the 4-dimensional displacement. As we can see from this 3-dimensional results, and the blue means the westward, southward, and the subsidence, and the red is the other direction. So we can see it's mainly across the East Anatolia Fault to get the contrast deformation across the fault. And to be more clear, I select a profile across the East Anatolia Fault. And we can see in the Arabia side is the south side, the maximum deformation is 8 centimeters in the 2 years. But in the Anatolia side, it can be double of the magnitude. So we call this is the spatial asymmetry. And besides of the spatial pattern, I also select a point pair, BB pair, to see its temporal behavior. And the dot is our observation. The dashed line is the model, the fitting model with a log function. And we can see the time constant of the log function is quite different in the 2 sides of the fault on the 2 plates. And we also estimated the whole field of the time constant across the fault. As we can see in the northern part is generally 0.1 year. And in the southern part is 0.3. So we call this kind of contrast is the temporal asymmetry. So this led me to think what results in this kind of asymmetry. Usually we will consider the after sleep. The after sleep happened on like a non-vertical fault or the heterogeneous property of the lower crust may result in the may result in the asymmetry. But the after sleep, it is elastic. That means the deformation is happened at the same time. At the same time may result in their temporal behavior should be similar. That means it can result in spatial asymmetry, but no temporal asymmetry. In the other hand, it may be the viscoelastic relaxation. If we have different viscosity of the lower crust or the upper mantle, we can result in both the different magnitude and the temporal decay of the deformation across the fault. So based on this analysis, we would say like the viscoelastic relaxation is the major process rather than the after sleep. And let's see if there are some shallow after sleep, we can see across the fault there are generally smooth transition across the fault, except for the northeastern of the major fault, there are some shallow sleep signature as this morning's presentation. So this will say like there are negligible contributions from the shallow after sleep and support like our point like the viscoelastic is the major relaxation. Let's back to the vertical observation. From the vertical observation, we can see there are significant vertical deformations. If this kind of deformation comes from the after sleep, we know it is like left lateral track sleep. This one will experience extension and compression in this zone. And in this situation, if it is after sleep, it should be subsidence here, uplift here. But this analysis is different from our observation. So the after sleep should not be responsible for this observation. In the other hand, if the vertical is from the poroelastic rebound, in the post-seismic process, the fluid will flow back in this zone and will flow away in this zone. So will result in uplift here, subsidence here. So this is consistent with our observations. So besides, we also have two GNSS points in these two zones. We can see in the first several months, it's very fast deformation, but afterward it becomes slow. So this is aligned with the fast post-earthquake fluid migration during the first several months. So based on this analysis, I would say the viscoelastic relaxation and the poroelastic rebound should be the major process for our INSAR observations. And in the following, I will try to model these two kind of processes. First, for the viscoelastic modeling, I will first using a Berger model to model each part of the lower crust and the upper mantle. And I use a grid search to get the optimal parameters. And each part of this section, I searched for the optimal parameters independently. And we can see our information is less sensitive to the lower crust, more sensitive to the upper mantle. Based on this result, we can get the parameters of different parts of the section underground and can review the asymmetric interplate structure and structure. Like here, the layers are asymmetry and the parameters are also asymmetry. In the Anatoly plate is much lower viscosity to the Arabia side. And this also consistent with our observation. Like in the northern part, large magnitude and more concentrated deformation. In the southern part is the different pattern. So to show how the model fit with the observation, here we can see the horizontal is generally fit with the model, but the vertical have some misfit. We show some profiles to see they are consistent between the model and the observations, and some point to show their temporal behavior consistent. And we can show that the good fit to the horizontal observation, but poor fit to the vertical component. But our viscoelastic model can cancel out some far-field vertical deformations and make the residual vertical deformation more concentrated to the fault zone, more close to the fault. So we further model the vertical deformation with the pore-elastic rebound modeling. Like we use the coseismic slip model with different Poisson's ratio to get the differences between these two vertical results to get the pore-elastic rebound vertical deformation. And we also use the grid search to get the Poisson's ratio change in two sides of the fault. And we can see the Poisson's ratio change as large as 0.1. And its typical value is only half of the here. So we will say the asymmetric and significant change of the intraplate crust material properties. But after the viscoelastic modeling and the pore-elastic modeling, how about the aftersleep? And from a numerical side, like we can model the aftersleep and the viscoelastic, just use a mathematical model to fit the observations. So here I force the fast aftersleep model to fit the observation. But here we can see like there are sleeps in the depth as much as 50 kilometers. This is physically unreasonable to such a depth of the aftersleep. And in the other hand, in the viscoelastic modeling, we can use the viscoelastic model like the post-seismic process below 20 kilometers to fit the observation. That means the most post-seismic process is happened below the 20 kilometers. So for this is from the numerical set, like we can use this model to fit. But for the lower crust, there may be some elastic aftersleep, but it's hard to distinguish between them. So here I just want to distinguish what's the contribution between the 20 kilometers to 40 kilometers and below the 40 kilometers. So here, here is the contribution from the lower crust, that is this part of depth. And here is the upmental contribution, is the below 40 kilometers contribution. We can find like the lower crust contribution is far smaller than the upper contribution. So even if that lower crust contribution is all from the aftersleep, it is still lower than the upper mental viscoelastic contribution. So this will support our conclusion that the viscoelastic is the major mechanism. Okay, here comes the conclusion, like we use the four-dimensional deformation to get the post-seismic deformation of the Turkey earthquake. And the temporal asymmetry will help us to identify between the viscoelastic and after-sleep contributions. Okay, here is all my presentation. Thank you.
Okay, we have time for one quick question. Thank you. Who's it? Quick question.
quick. So just the big sort of elephant in the room in your modeling is the fact that you're trying to model two different earthquakes assuming they're the one slip behavior. And the two different earthquakes, one had shorter rupture, higher slip, so then long rupture, average lower slip. What complication do you think that has in the modeling assumptions that you're doing?
Yes, that's a good question. But to be honest, I didn't consider in the modeling of such short term differences between these two earthquakes because our INSAR, we have several 12 days revisit time. So for now, I think in this study, we cannot consider this. Yeah.
Okay, thank you very much.
Thank you.
Move to the next presentation, which is long-lived post-seismic deformation and rheology following the 2001 Kokosili earthquake, constrained by decadal geodetic observations. And that's going to be given by Tim Wright.
Yeah, thank you. And Jin apologizes for not being here. He wasn't able to get a visa in time. So actually, if we could put on the recommendation list offer letters or talk offers letters to come out quicker, that would help, I think, with some of our colleagues to ensure they could come. What you saw in this morning's presentation about the whole Tibetan velocity field, which is shown in the background here, is that there is a component of long-lived post-seismic deformation that is visible in those fields. And so we wanted to explore that a little bit and see what we could learn about rheology from that. You can see that here we now have these very large velocity fields, Tibetan Plateau on the left and the Alpine Himalayan Belt field on the right. If you weren't here at 9 o'clock this morning, which I can understand, then I recommend going back and you can look at those presentations online later, particularly John's, I would say. We take those velocity fields and we're typically treating them when we're thinking about what they mean as if they're steady state long-term velocity fields. And this was a point raised by Shimon in his comment and his question. And I think we want to think about whether that is a realistic assumption or not. We can see in the velocity field for Tibet that we can see, for example, the Kunlun fault here, which failed in 2001, the Manyi earthquake here that failed in 1997. We've had some earthquakes also around Yuqian in that area. And so those are areas where we're seeing elevated strains compared to the background. So we'd like to just think about those a little bit more and what we can learn from them. How do the strain rates vary through the earthquake cycle? What's that tell us about rheology? I should have said that these are Jin's slides, but I take all responsibility for any mistakes I make. I think we know that strain rate is time dependent. These were some nice figures from a paper by Vladimirova, published a couple of years ago, showing kind of evolving views of the earthquake cycle from this simple view that we probably had before we started getting really good geodetic data to this kind of more still simple but model that probably is in it's probably still where I'm at, or to something that might be more realistic. But of course, we only have observations for very short periods of time. The inter-event time for many earthquakes is hundreds, if not thousands of years, particularly in the continental interiors. And we've got geodetic snapshots that, if we're lucky, last decades. So what can we learn from those places that are at the key points in this graph? And those key points are around when we have the earthquake. So the data before the earthquake and the data immediately after the earthquake. And they're the bits of data we can learn the most from. We had a go at this in a paper by Akbal Hussain, who's in the audience, for the North Anatolian fault, which was published in 2018. In this case, we've got three different kinds of data that are being used. We had INSAR derived velocities. Now, the trick here was we imagined the whole North Anatolian fault, which failed at different times, as if it was one system. So we can make different observations in space, and the last earthquake was further and further apart, further and further ago in the past. So back to the 1939 earthquake. And what we essentially saw for the North Anatolian fault, that within errors, the strain rate was constant. We also had this really nice observation that was made before some big earthquakes in 1999 at the western end of the North Anatolian Fault from GPS. So we had a key strain rate observation here that was also pretty much the same strain rate. Note the log scale, which hides a lot of sins in this case, but yeah, essentially the same strain rate. The exception then is this post-seismic period, which lasted last maybe 20 years or so for this particular case. So in this, for the North Anatolian Fault, the strain rates seem to decay to a steady state after that sort of decadal post-seismic transient. I want to emphasize again that that key constraint here really is that one measurement here that was made just before the earthquake. So we've said 240 years since the previous earthquake, but essentially this was actually, if we put it in its real place, it will be here. But can we come up with models that try and explain all of these observations? How unusual is this kind of situation we had on the North Anatolian Fault? Do all earthquakes decay to earthquake faults decay to a steady state strain rate? We can also look at other earthquakes and post-seismic patterns. This was data collected by, compiled by Tom Ingleby, who's also at this meeting somewhere. And he showed that actually, if you looked at all the post-seismic records that existed in 2017, they seem to also follow this 1/t decay in terms of the velocity. Again, note the log-log plots, that's hiding some scatter, but actually a relatively simple pattern when you look at the largest post-seismic signals from all these earthquakes. And then this figure this compilation came from a paper by John Elliott in 2016, also in the audience. What he showed here, or what we showed, I think I was an author on this too, was just at that point we had, I think, 4 earthquakes where there were measurements of post-seismic strain rates and measurements of interseismic strain rate before the earthquake. And with a very simplistic earthquake cycle, viscoelastic earthquake cycle model, you essentially, to fit these relatively elevated, focused interseismic strain rates that are seen very commonly around faults, you needed to have something with a relaxation time on the order of the inter-event time or larger. So effectively, that's quite a high viscosity. So if you've got an inter-event time of a couple of 100 years, that gives you a viscosity minimum of about 10 to the 20 Pascal seconds. ESA's 30-year SAR archive, of course, offers us an opportunity to capture the evolution of strain rates. So just can we come up with some more places where we've got these post-seismic observations and the late-stage interseismic observations? And this is work we've just started being led by Jin. And we've gone back to the 2001 Kokoksili earthquake in Tibet, which is one of the largest earthquakes that happened just at the sort of end of the ERS era. Some really beautiful work by Cecile, who's here on the stage as well, looked at the coseismic deformation around this fault. Quite challenging in those days with ERS to get the data to start with and unwrap it. But this was a significant earthquake, rupturing over 350 kilometers of fault and with slip in places exceeding 6 meters. So a very significant earthquake. And it's one that we still see in the Sentinel present-day deformation field, as I showed. So we have a rich multi-decadal SAR and GNSS dataset from ERS, ENVISAT, and Sentinel. There are some gaps. The GNSS coverage is sparse, but a lot of these older data haven't been reanalyzed with modern techniques. So that's one of the aims of what we're looking at. And then the hope is that by looking at these longer time series, we can get more tighter constraints on those post-seismic processes that are only just starting for earthquakes like the Turkey earthquake that we saw in the last talk. When we go back to ERS, of course, we end up having some challenges that we'd sort of put out of our minds. Those of us who did PhDs in this era break out in cold sweat thinking about some of these things. But there were limited acquisitions in time. I think for a lot of the Kunlun fault, there wasn't any data at all before the 1995 or something like that. The coverage was narrower. We weren't getting data every time the satellite went over, so we took what we could get. There were big errors in the orbits. So we have got better methods now, but we are still limited by the data that was available. So actually, we benefit from old school approaches. So I think some of us old dogs are still useful at times. So here's an example of one of the ERS networks for one track. So this is a baseline time plot, so these large baselines. We also had to worry in the two, after the Dopplers, the gyros failed on ERS2, or ERS1, wasn't it? Anyway, whatever, ERS1, the gyros failed, so we then had to look for pairs with similar Dopplers, but you can't form all the interferograms. There aren't that many acquisitions, but Jin's gone back and processed as much as we could. What you end up with, he's looked at 5 tracks. The results are fairly noisy, but actually quite encouraging in a way, better than I thought they might be. One of the tricks, one of the old school tricks, because we don't know the orbits and also we don't really have any much GPS anyway to tie this to before the earthquake, we can't just use the frames that the data come in, the 100-kilometer frames. So we've tied, Jin's tied those frames together and then processed the data as longer strips, all as a single interferogram. So that means if you make an orbital error on this southern frame, then that would also be propagated through. You can see there are some long wavelength signals in here. The fault's not entirely obvious where it is. If I think it's this one, yeah, this one, Jin has then flattened these interferograms. And again, the scale is plus or minus 15 millimeters. And if it's horizontal motion, if it was going at 10 millimeters per year, we'd only see about 4 or 5 millimeters in the line of sight. So we're not expecting a huge signal here, but by looking at some profiles, you do start to see something that looks like what you might expect. Here we fixed the locking depth at 15 kilometers, which is based on kind of a modern understanding of what we think the locking depth is. There are some big uncertainties. If you allow the locking depth also to vary, that really impacts the uncertainties on these slip rates. But you are seeing something that kind of makes sense. It's quite variable from location to location. So Jin's done a sort of profile fit through half of each data set and kind of averaged everything down. So we've got some that are as 3 or so, some are as high as 10. So it does depend on where you are. This is all of those slip rate estimates. I guess the parsimonious kind of approach is to say it's all going at the same slip rate. These are all noisy estimates of a single slip rate. If that was the case, and it was consistent with that locking depth of 10 kilometers, we'd end up with a slip rate of 4 plus or minus, the scatter there is plus or minus 3. If these are independent observations, that will give you an uncertainty of about 1. But I think these are very preliminary results at the moment, but it's encouraging that we're seeing something, and it's definitely lower than what we see at the moment. Yeah, so that gives strain rates of something like 1 to 7 times 10 to the minus 8 per year. If we move on to MVSAT, we get more data, more precision in our observations, but also a bigger signal because we're now into that post-seismic period. So we're seeing very clearly now this signal around the Kokoxili earthquake, and a lot less jiggery-pokery needed there. We did work on this back more than a decade ago with Matt Garthwaite, and what you can see here is that his profile, which is very consistent with the new results that Jin has got, so getting something more like 10 millimeters per year. Interestingly here, the GPS profile was measured before the earthquake, and again, you're seeing a lower rate of deformation before the earthquake than we are in that post-seismic period. And then I showed the sentinel velocity field this morning. Again, we're still seeing this very large step across the fault. If we look at all of those on the same color scale, this is essentially what we see. We see a relatively small signal for ERS, pretty big signal for MVSAT, and that's decaying away a little bit for Sentinel-1, but it's still pretty much going pretty quickly. We can look at those profiles together. There's ERS, there's MVSAT, and there's Sentinel. So we're getting consistent results, but actually that post-seismic transient seems to be lasting a long time. If we put those on this plot from John's paper, this one here on the right is the ERS result. So it's a bit lower. I'd say it's not as clearly focused strain as we have in some of these other faults. The post-seismic from MVSAT and then Sentinel are up here, so they're very much in the rapid post-seismic box. We also have some GNSS data that is rather sparse in places. There are some continuous sites, but mostly there are many campaign sites. But some big signals here. This site is just one measured here. And if you kind of stitch all those together, you're getting something that's consistent with that kind of logarithmic type decay. So I think the key observations here, we've got strong temporal variability, we've got long-lived post-seismic signals, not yet approaching steady state. There seems to be some spatial contrasts both in different places, but also across the fault potentially. There's low, but potentially focused pre-earthquake strain rates and a relatively low slip rate compared to what you would estimate if you ignored the post-seismic today. So if it is focused, then that does imply this strong substrate. I think there's more work to be done really just to nail down this modeling. Just in terms of future work, what we want to be looking at is a sort of model agnostic approach. Mohammed's going to also mention this approach, but this is based on work. This is work done by Jonathan Weiss, published in 2019. But the idea here is that you can, if you can invert the strain in cuboids, you can estimate the stress changes caused by the earthquake and also by the ongoing post-seismic deformation. You can then estimate both the afterslip and the temporal evolution of the viscosity in different places, and you can get up pictures like this. So the idea is that strain rate history and stress evolution will in the end give you the spatial and temporal distribution of rheology in a way without having to sort of do these sort of grid search type approaches where you're using relatively simplified rheologies. Jin has started this. It's very much early days for this earthquake, but this is where he's going. This is some early results from just some forward models and some synthetics. But it does seem you can pull out the viscosity variations. So I'm going to end it there. I think I've run out of time. Large-scale velocity fields are not steady state. And I think the jury remains out about whether they do decay to, whether rates decay to a steady state rate over these big faults. Post-seismic deformations do persist for decades. Trying to make these measurements before earthquakes is really important. Rheology varies in space and time, and we'd like to be able to constrain that. And hopefully, I think that's the next frontier. We've got these steady state average velocity fields. I think the real exciting thing over the next decade is how that varies in time and in space and what that means. So I will leave it there. Thank you.
Thank you. Nice to see some old ERS friends on the screen. We have time for 1 or 2 questions. Yeah. Yes.
Who was first?
One tool that I found useful for extending the sort of aftershock decay rate is repeating earthquakes, sort of small asperities that they're much more sensitive. Have you considered adding something like that in to try to extend the seismic side?
Yeah, that would be great to do. I don't know what data are available for this earthquake, but I think if there are people in the audience who know, I think that would be an exciting thing to include. Great suggestion. Thank you. I think there was one further back first, wasn't there?
Yeah. One up.
Thank you very much, team. I may miss that, but
The question is about when you mentioned a strain rate history or variation. The question is if there is uncertainty in the measurements, either GNSS or either INSOR, it comes to a strain or a strain rate, and then it comes also to the window that we are measuring, and then these uncertainties, it comes also to the history. Can you comment on that, please?
Yeah, I think you have to try and characterize your uncertainties as best as you can. The older data, the uncertainties are going to be bigger. And I think pragmatic approaches, doing multiple tracks, looking at consistencies between data are ways you can kind of analyze those. And then it's really not trying to squeeze just the right amount of information out of your data, I think is the trick. Right, so.
Thank you. I think we need to move on. The next presentation is going to be three-dimensional post-seismic deformation following the Kahramanmaraş earthquakes revealed by integrated observations by, there you go, Mohammed, yes, the last name, Nergisi.
Thanks for a good introduction. Oops, is that mine? Is yours? Is yours? Is that mine?
It's mine.
Ah.
Oh, it's incorrect. You need number 3. We need presentation number 3. Who is in charge? Oh, somebody runs outside. Oh, there we go.
Yeah, this is me, yeah. So, yeah, I'm gonna talk to you about the three-dimensional cosmic deformation time series from Kahramanmaraş earthquakes using GNSS, INSAR, and BOI data. First of all, I really thanks to Jihong Liu first talk, because he gave exactly the real motivation why we need the cosmic deformation of the Kahramanmaraş, and then from the BOI, also I'm using that. And second one, really thanks to Tim, he's exactly explained about the earthquake cycle, and then he say, geodetic snapshot is really good definition for like why is the main motivation of the cosmic deformation method. In the right hand side you can see the earthquake deformation cycle easily like 100 years, centuries, like in the fault strain is accumulated, and then in second is earthquakes happen, we call it a cosmic displacement. After that the crust is moving, like is a cosmic decay, and then is speed is logarithmically decaying. So if we catch that deformation as well, and we can say about how the crust and upper mantle react to the stress, and it give us to understand rheological structure and then lithosphere of that area, and we need 3D deformation. So yeah, before going to the cosmic deformation, I want to quickly say something about what happened 6 February 2023 in Turkey. And yeah, it's the Narla fault is 7.8 magnitude earthquake is initiated, but the main point is not is just the branch. Is even people discuss about is it Dead Sea branch or East Anatolian fault on branch, but this small trigger is affected 350 kilometer rupture along to East Anatolian fault is multiple cascading segment rupture is Amanos, Pazarcık, and Ergenek. And then after 9 hours later, this stress change triggered another earthquakes with 7.5 magnitude is rupture extrally 150 kilometer in the north part of the first epicenter. So key characteristic of these two earthquakes is both of them is happen on the left lateral structure lip, and then we expect to see horizontal dominated deformation along the broad zone. So to catch this cosmic deformation, we process 2 ascending and 2 descending comet frame, and then for each frame we use the range offset, azimuth offset tracking, and burst envelope interferogram data set to catch the 3D deformation of the cosmic displacement. So the idea is the same, like I said before in the early talk, like if you have a 1 pixel, and then this pixel, if you see the 1 ascending range offset, 1 descending line to range offset, and then 1 BOI or azimuth offset, you can use this 3 geometry to decompose the E and U component of the deformation. So in the G matrix, you see the first one is the just line of sight projection of the from the heading and incidence angle, P and theta, and the second line is just the along track projection. So even if you put the quickly like Sentinel-1C values for there, -10 and 35 degree for incidence angle, you can see red one for line of sight, 0.1 N, like which is meaning line of sight is not sensitive to north-south component, while BOI is highly sensitive. Almost everything is going from N to along track displacement, and there is small effect from east, while vertical is exactly cancel out. So yeah, it's like we decompose the cosmic deformation, and then you can see from here horizontal dominated deformation happen, and what we expect from there, we expect big cosmic deformation followed by big cosmic deformation. So what we did is like we processed the 29 comet frame, 16 ascending and 13 descending to cover the big area to go to find the 0 point region. For that, we process multiple frames, so all of them is internal reference. Therefore, we need to make them to common reference system. So for that, for the interseismically, we use the compiled GNSS from John Elliott. He's processed from the Chris Rollins, our New Zealand colleagues. And then for the GNSS data, we use 100 continuous cosmic GNSS from the Duza active station. They are continuous right after the earthquakes, the end of the earthquakes, the end of the 2025. So I need to take a water first. So for that. Yes, for the cosmic deformation analysis, the processing workflow, we do it the three system. Like first one is the interferogram generation. For the interferogram generation, we just during that project we use the BOI generation to the put to the LIXAR system, and then this one is you see like how the BOI created with the LIXAR. So when you define a frame, you create the BOI and then a GNSS data, and then in here, like one of the example of the descending frame of the interferogram. The second one is we make the time series analysis. So the GNSS analysis, we use we have the GNSS data, but we need to do the the post-processing stuff. So first we remove the interseismic removal and then make the seasonal removal. After that, we make the downsample to 12 days interval. So you can see quickly in here, if you have if you have the data, GNSS data before the earthquake, we make some linear trend of the interseismic and then remove from the cosmic data to get the pure cosmic data. And after that, like, okay, it's just 2 years, but we need to remove some seasonality. Therefore, like, we make the logarithmic term with this annual and semi-annual correction. Then is the green one we remove from the cosmic data to make the data dump sample scatter is a bit better in the third section. So finally is the daily GNSS. Therefore, we make the daily GNSS every 12 days because this is the Sentinel-1 acquisition time is after the Sentinel v that. And then like this, we use this every 12 days, a common epoch to make each track to integrate it there to make the deformation field. So yeah, BOI and along track time series, during that project, we improved the LIXPath to allow the BOI processing. So after the LIXPath, it gives us to along track velocity field and cumulative displacement. So during that, we removed some effect like atmospheric, ionospheric, and tidal removal, and plate motion correction, and also interseismic removing is exactly what we do in the GNSS data. Then resulting, like we have line of sight, BOI cumulative displacement, and GNSS cumulative displacement. So next step is referencing and decomposition. For the referencing, yes, is all of them internal reference, both line of sight and BOI. And then for each epoch, we reference our internal cumulative displacement, GNSS, to using the WellMap strategy. And then in the top, you can see like how the data in the beginning, like you can see the frame boundary there, like is all of them is internally. After that, correct them with the reference them with the GNSS data. In the bottom row, you can see ascending and descending referencing and then BOI referencing. Then final step, we use this reference BOI in the line of sight to decompose to every 12 days. Then this provides us the 3D cosmic deformation through the time. So if the data is here, like you can see east, north, and vertical component is varied every 12 days, and then you can understand how the cosmic deformation is evaluated during the time. And then when you make a profile, you can see is all three components is in the Anatolia and Arabia. So if we look at a little bit much more detail into what's going on there, like every 12 days cumulative deformation increase. So you can see like how the deformation evolve in the time, like it's from the first 2 months to end of the 600 days. First one east and then north, and then also like you can see the vertical deformation is how the variate is exactly Jihong show. Is the last epoch is you can see the fourth quadrant there. And also a bit detail, like if you look at the window, rather than cumulative displacement or difference between the window, you can see like how the deformation is decaying during the time. Like 30% of the total deformation is happened first 2 months, and then is next 2 months is getting to the 20%, and the rest of that is decaying, so on and so on. So same story for the north component. While is vertical doesn't decay like that, it shows some seasonal pattern. Probably it's because of the unmodeled seasonal non-tectonic effect. So we have the data, and then we compare with the GNSS data, and then with the like, how many is a couple of them is being to same amount of the far field, the far, and then the fold, both in Arabia and Anatolia, and then you can see how they fit well is ENU component. So, but some of them is like, for example, for up component for that frame, and then in here there is some discrepancy, but this is because of the some cosmic deformation is can acceptable, but there's it should be unmodeled stuff. So if we look at the spatial profiles and the deformation, and then in here we can see like east component is exactly looks like same profile, like it's similar profile with the Jihong in the B is maximum in there, but our deformation a bit different, like maybe because of the different referencing strategy or our GNSS much more dense, and then our maxima is reaching in the east component 150 kilometer in Anatolia, while is 100 millimeter for Arabia. But same trend, like same similar trend. In the Anatolia, we catch the deformation is much more localized in the near, but Arabia is a little bit smooth in the variate, but in here you can catch the maxima. For the north component is maximum deformation in C profile to support the left lateral movement after the cosmic, and then you can understand like it's going worse that ways and that ways. So it's vertical, it's same 4 quadrants in there, and then uplifting in Anatolia is cross the profile, cross the fold, eastern fold, and then you see the Arabia, there's a downward subsidence, and then the other uplifting and subsidence in there. But it's really good, like different institute catch this, so similar data results, so we're doing, I guess, is something's correct. So it's finally like, is it data result, like we can say, like we produced one of the most complete 3D cosmic time space in the literature, and is really good to understand what's going on the continental strike slip fold, and then rheology structure of the between Arabia and Anatolia, and then it can be highlighted, open the new gate about the understanding plate tectonic and cosmic deformation mechanism. But the problem to understand, okay, this is the deformation, but what is the mechanism? Like it should be 3 different mechanisms, like kinematic afterslip, viscoelastic relaxation, or fluid stuff. So we start with every good cosmic modeling, start with the good afterslip. So we make it like going to 0 to 40 kilometers to understand the afterslip modeling. Okay, east and north is suited well in the near locally, but it's not so much the long wavelength in there, but is vertical is exactly going to the residual. There is no any vertical fit. So is afterslip doesn't explain the vertical deformation. So if we're going to do viscoelastic model, simplistic model using relax, just to make a two-layer, like upper crust is elastic and then down there is some viscoelastic structure, and then make the grid research. So you can see like kind of homogeneous ways doesn't explain the Arabia and Anatolia heterogeneity, and then it should be Arabia much more rigid, because such a kind of viscosity, Arabia should overestimate while Anatolia is underestimate. So the point, even from this simple model, Anatolia should be weaker than Arabia. And vertical, you see, it doesn't fit well with kind of model. But if you put another upper mantle, lower crust in upper mantle, and then research a grid research, and then you can see much moderate, much better vertical fitting, and then our model is getting better and better. And then if you cheat from some seismic research from the area, like the wavelength, and then make some lithospheric thickness around the Anatolia and Arabia, is vertical is getting better. And then when you compare with the observation as a profile, and then is getting is closer. So kind of model like lower crust viscous model is explain the deformation well. But kind of viscoelastic model reproduce broad similar trend ENU component, but not explain everything well. Therefore, we need something to solve everything in together rather than solving after slip, viscoelastic, poroelastic rebound separately. We need something to solve in model in together, and then find the all three observation is going well. So what we're doing in here, like as the team mentioned, is cuboid solution, is the inelastic volumetric strain, is developed from Swan Barbot, the algorithm. So is there like kind of kinematic after slip? This time we make some cuboid beneath the after slip zone, and then solve each cuboid for strain component. And then this strain component transform later to stress and strain rate change, and then we can go directly effective viscosity. These are so fresh output from the different time window. And then in here, like you can see like how the stress variate during the time, and then second column is how the strain rate variate during the time, and then last one is how the viscoelastic effective viscosity is change. Each cuboid is from the first month to 600 days. So this is also our after slip deformation, after slip result from different time window when we saw in same time, and then you can clearly see how the after slip accumulator is end of the 600 days. So yeah, everything is sweet well now, like is north and vertical component with the after slip and viscoelastic solution, but still is ongoing. Like we need to find kind of model explain everything, but it would be new start. So as a summary, like we produce really good 4D cosmic deformation using Sentinel-1 line of sight and BOI data with the GNSS time series. And simple model explains some signal, but not full deformation field. And cuboid inversion help the distribution required by the data. And yeah, that's all.
Okay, thank you. So we have time for questions.
Hi, it's a very interesting talk, and I just have one question. That's when you perform the strain inversion, you know, there are 6 components, right?
Yes.
And if you ignore the isotropic stress component, and you can actually, honestly, I think you can fit everything.
Yeah, that's therefore is ongoing progress. Like it can be to everything, and then it looks like all like 3D is fit well, but it's not meaning of the model is correct. So we do some penalty in there, like make the isotropic almost 0, and then make only like the volumetric is 0, and then everything is coming from deviatoric stress.
Yes.
But there is not any common method, like maybe we can use Bayesian solution and rather than penalties, but is currently we try to solve which penalties is much more physical, and then fit also our model result.
Yeah, another suggestion is from the viscosity pattern, I think it may be related to power law. Yeah, for the larger stress area, the viscosity is quite low. And far field, the stress magnitude is not that high, and the viscosity pattern shows quite large value.
Yeah,
Do you think?
It's maybe because of when I define the background stress and strain, maybe therefore, but also would be some data downsampling, because I selected downsampling a bit much more around the fault, and then that one there would be reason. And yeah, I need to investigate more about the volumetric, because it's fresh method like Jonathan Mays and Sven Barbo, Jonathan Mays, Zhang Zhu is applied, but there is no any like so much things to in the literature. I'm just researching also. You did something really good job in the interseismic.
Yes.
So yeah, I'm
last
checking.
question.
Yeah.
That's do you think there are any poroelastic response?
Yes, I would be, but I don't expect kind of big poroelastic is broad zone, because they already did, and then it's already explained something. But in the poroelastic, I'm not sure how it's extend, like almost more than 100 kilometers from the near fault, and then it's consistent along the time, like after the 600. Because in the poroelastic in the literature generally takes month and then decade, but it looks like still there when we look at the cumulative. Therefore, yeah, maybe we can end up with as well with the poroelastic, but we have really good data as a cumulative, not only one day. So I need to find a way, make the poroelastic different window. I don't know how can I do. Maybe I need to ask Soji a lot. Yeah.
Okay, no more question. Very quick, yeah, Paul.
Thanks, Cecily.
Thank you very much for this really nice talk.
Yeah.
I just wanted to ask you, do you know if it would be like feasible to, like in the end you showed some viscosity contrasts between Arabia and Anatolia, and it might also be a question for Jehong as well, since. I was wondering, given the structural asymmetry between the Proturge segment, for instance, and the western part of the East Anatolian fault, could there be some northeast to southwest rheological contrasts as well? And would this be possible to model somehow?
Yeah, we used some seismic wave information from Delft or like the Karabulut, and they exactly say there is some heterogeneity between Arabia and Anatolia. And then even like in our model, we put kind of heterogeneity in as a lithospheric thickness different from between Anatolia and Arabia, and then make the much more weaker Anatolia, and then it's give much better result. But the kind of forward model need time. We need to, there are lots of different combination, and then you need to research everything. But it's end up with like going everywhere. So I don't know how can I finalize and then make simple model to explain everything. So yes, thank you.
Okay, well, thank you. We'll move to the next speaker, which is actually Shani Johnson, and he's going to talk about earthquake factory.
Yes, I changed hats from being a chair to a speaker. So first I want to acknowledge my co-workers, especially Ji Hong, who spoke earlier, and Bo Lee, who did bulk of the work I'm presenting today. So I'm going to tell you two stories about how INSAR has helped us to understand some new things, perhaps, regarding earthquake processes. And one might try to, for example, start with maybe a provocative question. Are paleoseismological results systematically biased? What do I mean? Well, in paleoseismology, a large part of it deals with looking at fault slip rates. So you go and you geomorphologically map offset stream channels, for example, you try to date them and you get long-term slip rates. And this is quite important because we don't have any earthquakes from many active faults, and faults that are not super active, we can get rates, and therefore this information provides crucial points into earthquake hazard assessments around the world. So are these rates that we get from these kind of observations systematically underestimated or overestimated? And I want to a little bit look into that, and I go back, like several speakers here, to the earthquakes in Turkey. I'm not going to talk about the background much here. We have heard about that. But these had combined rupture length of about about 500 kilometers. So here are multiple co-seismic data sets of this event from ALOS 2 and Sentinel, from different types of processing strategies. INSAR provides good information in the far field, offset tracking, crucial information in the near field, and then you can take all this information and invert for the east-west, north-south, and to the right you see the vertical along with the horizontal vectors. So you take that and you look into the fault parallel component. So locally along the fault parallel component of the deformation, you can see quite large offsets up to about ±4 meters, so 8 meters across the fault plane. And generally speaking, you see displacements increase towards the fault, as you expect, until you reach the offset, and there you have the step. But when you look into the details, you see sometimes that it doesn't always increase towards the fault. You see in some places that it starts to decrease again. So somewhat unexpectedly. You can try to look at this systematically just by looking at the fault parallel motions along these profiles, and you slide that profile here along the fault, and you see in many locations it sort of dips instead of following what we would expect from like elastic prediction. Now, this is not a result of filtering or the pixel offset window size reaching on both sides of the fault. We take care of that here especially because we want to capture this in detail. It also extends several kilometers away from the fault, so it's not a processing artifact. Now, we want to try to quantify this deformation. We can call it missing surface displacement. It both has a magnitude and it has a width, so the area from which the deformation appears to deviate from the elastic prediction. So we get that information by thinking that the plates in long term should move like blocks, and then we have it mostly combined interseismic deformation and co-seismic deformation. And if you add the two, you get this block motion. So from the co-seismic motion, you can try to fit the far field and then see what is the missing part here, the missing displacement, and then you can estimate the width of the missing part where you start to deviate from the elastic prediction, as well as the magnitude. And it can be different from the two sides of the fault, both the width and the magnitude. And you can map it along the entire fault zone, and you see it reaches in some places as much as 2 meters. Another term to call it is absent surface displacements, or ASD. So that's what is sort of missing. Now, using the absolute values is maybe not so good because sometimes you have 8 meters of fault slip, in other places only 2 meters. So taking a ratio is maybe a little bit better quantity to work with. So here you have the ratio of this ASD value mapped along the fault, and it has a different width, a different ratio sometimes across the fault. On average, it's about 33%, and can reach on average something like 5 kilometers away from the fault. It's a big range. Sometimes it's smaller, sometimes it's more, sometimes it's almost 100%, because towards the end of the fault you have fault slip at depth, but nothing at the surface, for example. And you can also see, if you look here, that it reflects the segmentation of the fault. So where you have geometrical complexities, like a kink in the fault or a step over, you get more distributed deformation, and you have stronger ASD in these locations of complexity, while straight fault sections along the fault have less of this. So the average value is a little bit here on the lower side, so usually the more straight sections. Now, if you take data that show this kind of dip in displacement towards the fault and you estimate the fault slip, so this is a model, you get reduction of fault slip towards the surface, a term which has been called shallow slip deficit. Here are multiple normalized profiles showing that here at the surface you have less slip than at 5 kilometers depth. And this has been seen in many, many earthquakes. And people have been wondering, okay, what do we do with this part? Because the fault is moving here, we can maybe have here some kind of a post-seismic processes taking care of the deeper part, but the shallow part, what is happening there? How do we expect the fault to, in the long term, to move as two different blocks? So you have to sort of compensate for this shallow slip deficit with either post-seismic shallow slip or interseismic or transient creep during the interseismic time. Now, looking at interseismic rates from before, of course, we don't have the entire interseismic period, the hundreds of years. There is very little evidence for interseismic fault creep in this area. And you learned from Paul Durand this morning in detail, we also don't see any significant post-seismic slip except in a couple of small places, and it's only at the centimeter scale, maybe 10 centimeters, far too little to catch up the meter scale absent surface displacement. So here are some profiles. It's relatively smooth across these profiles. So we don't see this shallow after slip taking place. We don't see interseismic creep. So what's happening? We think it's due to damage. So you actually get permanent damage of fault close to the surface rupture when you have a catastrophic fault failure like here. And if you look at ALOS data, you can see some of that. You see lots of small fractures happening close to the fault rupture. You see something that appears like plastic deformation in the near field. So we believe that this offfault damage, which we call permanent offfault damage, is responsible for this absent surface displacement. And you actually never catch up the two plate rate. And the shallow slip deficit is real, and it means that we have more slip on the fault at depth than we have at surface. So these are some implications because the faults on the blocks, they move less at the surface than the tectonic plate rate. Therefore, paleoseismological rates would tend to be systematically underestimated because we are looking here at offset stream channels. But are they underestimated by 35%, which is sort of our mean value of the absent surface displacement? Well, no, probably it's less, because when we look at the straight fault sections, and if you're a paleoseismologist, you like to go to sections of the fault that is relatively straight and easy to work with. The straight fault sections should have less absent surface displacement. It would be more like 0 to 20%. Bottom line is that we think they are sort of systematically underestimated. And now we have to start to compare this on a global scale where we kind of know what the tectonic block rate is and compare it with these results. I think it will be interesting. Now, I want to start small, another story, and again, I start with the provocative questions. Is the seismic gap hypothesis dead? What do I mean? Seismic gaps are portions of active faults which have not experienced large earthquake compared to its neighbors for a long time. Here is the Himalayan front, for example. You have here seismic gaps, no earthquakes for about 500 years, and in between there are source areas of earthquakes that occurred maybe 200 years ago. So they are very important, these seismic gaps. They provide locations and approximate size of the next major earthquakes. So that's sort of the hypothesis, that we can use these seismic gaps for tell us about pending earthquake hazard, while we don't expect earthquakes in the zones between because they have only accumulated something like 100 or 200 years of interseismic strain. So we move to another earthquake that we studied recently, which is the Mandalay earthquake in Myanmar, where you have I don't know why it's so low resolution, but it's the Saigang fault that is in Myanmar. It takes up the transfer motion of the oblique conversion between the Indian plate and the Southeast Asia. So here you have SAR image offsets. It's an interesting earthquake, somewhat unusual. The fault appears to be very simple. It does have complexities. It's just so long that you don't really see any geometrical complexities at this scale. It's very long, 460 kilometers. It sort of maps off some of the scaling relationships just because how long and narrow it is. Another thing is that back protection methods seem to indicate that most of the surface rupture was at super shear. Well, it started in the north and it ruptured towards the south at a super shear speed, so it was very rapidly progressed almost throughout the entire rupture length. So while some things were unexpected, other things were expected. For example, it occurred in a seismic gap. If you look at this long fault, you have had earthquakes about 80 years ago, 100 years ago for parts of the fault, and there's a seismic gap in which the earthquake occurred. So it was expected. Last earthquake there was about 200 years ago, and so it was definitely not a surprise. However, what was interesting is that it went way beyond the gap. And it became almost twice as large as expected. So how could that happen? So we expected an earthquake that was maybe 7.5, but it went to 7.7, twice as large as expected. Was there something in the rupture process that helped it to grow this large? Was the fact that it was progressing at a super shear velocity that helped it to go so far beyond the seismic gap? This is something we wanted to look into. So we used the deformation data along with teleseismic data to get a kinematic fault slip model. So they're a very long fault showing this rapid progression. The INSAR data here are really critical to determine where on the fault and by how much the fault slipped. And here it's about 4 meters at the most. And you can try to see how it fits to the data and so on, so standard things. Then we also built a dynamic rupture model that by prescribing the stress on the fault, its geometry and the frictional parameters, and then you initiate a rupture in the north, and then you propagate this rupture here, and you can see in the right how the wave field is propagated away from the earthquake. And we try to adjust the parameters such that the rupture process and the fault displacement match what we see from the data, or what we estimate from the data in the inversion. So there's no data here, but together they match roughly. They both show this super shear rupture speed. The slit distribution is at the first order similar. On the bottom right, you have moment rate functions that in the two cases are also broadly similar. So why do we do this? Well, we do this to study what we can adjust in the dynamical setting to look into details of the rupture process and try to ask the question, why did it grow so large? And you can basically set up this model, and then you can start to play with the boundary between the seismic gap and the neighboring fault sections and see how strong that barrier had to be. And then you can change that strength of the barrier to see how strong does it have to be to completely stop the rupture. And you can do that. Here are some rupture simulations at the bottom. And the bottom line is that to keep the super shear rupture velocity through the entire rupture, you need to have the barrier very weak. If you make it stronger, it will slow down the rupture, which did not happen. Or if it's very strong, it will even stop the rupture. And the bottom line here is that the super shear velocity actually is not very efficient in crossing boundaries because a lot of the energy goes into wave propagation and less into kind of the dynamically onto the rupture front. So slow ruptures, and we did that. We now twisted the frictional parameters that made ruptures that were traveling at less than super shear, and they were more efficient in progressing across the boundary. So definitely it's not the super shear velocity. What is critical is where the initiation of rupture is. So the fact that it started Faye in the north and then ruptured toward the south, you have sort of dynamic stress loading in front of the rupture tip, and that helps it to cross the boundary and go into an area where we did not expect any rupture for another 100 years. We did have about 80 years of interseismic stress loading there, so there was something in the system, but we didn't really expect any earthquakes. So these have some implications because seismic gaps do not necessarily reflect the size of future earthquakes. They may cascade into adjacent fault sections. If you think about the Himalayas, you have had seismic gaps. If you would start on one end and you go here, you have 200 years of interseismic loading here, so maybe it just goes across and produces a much larger earthquake. North Anatolian fault is another case. You have a seismic gap here in the middle, you have an earthquake here in the recent earthquake. Maybe it loaded in particular the western end of this gap. If you have a rupture towards the west, you have 100 years of interseismic loading here. In the Llanos, maybe it just ruptures off the map. Something to think about. So in conclusion, 2 take-home points. Large earthquakes produce a lot of off-fault damage beyond sometimes 5 kilometers. This has implication for paleoseismological rates, which I would think tend to underestimate seismic hazard. And then we have to regard seismic gaps with cautions because they don't necessarily reflect the size of future earthquakes. So with that, I want to acknowledge Bo Ji-hong, who spoke here earlier, and Bo Lee, who did the bulk of this work. This has already been published in 2 papers. I put the 3rd paper here, which is the one Ji-hong talked about earlier in the session, in case you want to learn something more. And as a final point, come to IGARS next year in Reykjavik.
Okay, thank you.
I went over time, sorry.
Yeah, actually, you're a little bit late, but maybe if there is a quick question, yeah, Garrett. Yeah. Garrett.
This is cool. Yeah, so Dave Jackson at UCLA, the late Dave Jackson, used to like to point out that California's paleoseismic sites, 12 out of 13 of the major faults, they had exceeded their standard recurrence time. If what you're saying is true, then doesn't that make that problem even worse? If the faults are going slower than their true slip rates?
Yeah, well, I don't know California in detail, but I mean, you have the southern end of the southern part of the San Andreas Fault sort of ready to go. And then you don't think that the northern part is ready to go, but it still has over 100 years of interseismic loading. So if it gets triggered from the south, you might have some, ignoring the Parkfield segment. It's maybe a good thing for California to keep these things separate. I don't know.
Yeah.
I think the paleoseismicity gave us also the frequency of earthquakes, and in California they say it's 150 plus minus 50 years. It's not so much of the offsets over there, but the frequency of the earthquake. So that's, in that sense, it's still valid.
Okay, and okay, go, yeah, and then.
Johnny, I wonder if you could connect both of your stories together with a question, in the sense that you showed that in the Kahramanmaraş earthquake, you have this absent surface deformation, and you said that simple segments have 20%-ish.
Yes.
Do you see that same 20% in the
I was going to mention,
Myanmar earthquake?
I mean, we don't have a lot of great detail in the near field, but no, there happens to be very little absent surface deformation in the case of Mandalay earthquake.
So could you comment on why you think that's the case?
Well-developed faults that are geometrically simple. Yeah, something about the lithologies. Geologists
there should be damage due to the supershear, no? Oh.
The supershear, yeah, maybe. Yeah, I actually don't know. Yeah. So, yeah, I think there is a lot to learn.
Okay, well, thank you. So we're going to change area. We're going to move to the balcony and look at that at the big picture.
So hello everyone, I'm Emin Meridi, a third-year PhD student at the University of Lyon, with Cécile Lasserre, which is present in front of you, and Marianne Métois. And today I will present you my work, which aims to measure surface deformation at regional scales across the Balkans Peninsula, using INSAR, Sentinel-1 INSAR data. So our study focuses on an intracontinental area located at the transition between the Hellenic subduction zone and the Alpine collision front. There are several plates which are interacting in this area, and which are connected with through major active tectonic structures like North Anatolian Fault at the east, and the Hellenic subduction zone on the Alpine and Apennine collision front. This active tectonic crossroads leads to high seismicity by interacting between different tectonic domains and a complex geodynamic frame. So based on the available GNSS dataset, we know that this region is slowly straining. So there I show you the present day deformation from Piña Valdez et al. 2022. And you can see that velocities ranges from nearly 0 to 3 millimeter years with respect to a Raja fixed frame. You can see also a special pattern of velocities direction that follows a clockwise rotation around the North Albania. And based on the GNSS station, despite their presence, it remains very sparse and unevenly distributed, which limits our capability to measure correctly a long fault deformation and well-constrained geodynamic and kinematic and geodynamic models. So in this study, I'm taking advantage of Sentinel-1 INSAR data, which are provided by the French FlatSim service, that which Brian Rimbaud presented 2 days ago. So I will not diving into details in the next slide. But the key advantage there is that we cover the spatial extent of the Balkan Peninsula with ascending and descending tracks to try to respond to the question if INSAR can provide new information in such a low strain area, even at long spatial wavelengths. So before discussing the method, a brief recap of what is FlatSim service. It's a French national service that aims to compute massively and automatically Sentinel-1 data. The main advantage of this processing is that we get user-oriented products at the final step of this processing, along wrapped and unwrapped interferogram, linear velocity maps, and phase displacement time series that we used in this study. Also, benefit from this processing that consistent processing is performed along such long tracks, around 600 to 7 kilometers, that limits processing error. So concerning the Balkans dataset from FlatSim, we can see that we have 8 ascending tracks and 6 descending tracks with a 240 pixel resolution with time series spanning from 2014 to 2021. So the question there is that INSAR FlatSim dataset can reveal low strain velocities in this area. So to do that, to answer this question, before answer this question, we have to perform 2 major steps. The first one is to extract the linear trend from our time series, supposed to be the interseismic velocities, from other components as coseismic and seasonal signals. Secondly, we need to fix the INSAR time series into a known reference frame, as INSAR time series are relative in time but also in space. So without diving into details, we take care of that by adapting the approach proposed by Lemrabet et al. That aims to an absolute referencing with minimal adjustment to GNSS. And now we have line of sight velocity maps, and we can see them to see the deformation. So let's see these maps. So there you have the high resolution mosaics on Balkans Peninsula for ascending tracks there and descending tracks, both in ITRF reference frame and in the line of sight of each satellite. So you can see that velocity spanning from 0 to 2 and -2 centimeter years for ascending and descending tracks. They reveal large-scale plate motion, but also much smaller wavelength signals that cannot be caught by GNSS network alone. So we compare these high-resolution maps with GNSS dataset after referencing. So we reproject the GNSS velocities, the 2D GNSS velocities used into line of sight of each satellite in descending and ascending data. And we can see on this scatter plot that it's aligned very well with, we cannot weighted root mean square error below 1 millimeter error after referencing between the both data set. So we are quite satisfied with that. So now we are here with 1D line of sight velocities. So the next step to explore further the insight into deformation pattern is to decompose them into horizontal and vertical components. So for the assumption, we didn't fix the north, but we make the assumption that horizontal motion is parallel to the direction given by the 2D GNSS velocity fields. So you have this GNSS velocity fields in the inset with respect to a Eurasia fixed frame, and you have the result for the decomposition, the horizontal velocity map and the vertical velocity map. So the first one, you can see that is very dominated by tectonic motion, especially in Greece. But we will see that other lower contrast can also be highlighted. For the vertical velocity map, it's more patchy, and as you can accept, it's largely related to non-tectonic motion. But if we draw source-north profile in these maps, we see interesting things. So we did that from South Peloponnese to Eastern Serbia, and we represent the INSAR velocities as a function of the profile distance on this figure. So you can see INSAR data in gray and blue, and GNSS dots represented, GNSS velocities are represented by red dots. So the first thing that you can see, it's the tectonic uplift at the level of the red stars. The tectonic uplift of the southern side of the Gulf of Corinth that is catched by INSAR data, relatively consistent with GNSS and the known kinematic models of the southern Gulf of Corinth. On the second start, in the Thessaloniki coastal plain, you can see negative INSAR velocities, which ranges from 5 to 10 millimeter years, likely related to anthropogenic processes. So vertical INSAR are largely dominated by non-tectonic motion, but we do retrieve some tectonic signals. Now we are getting into horizontal velocity maps. So to ease further the visualization, we take just the east terms and north terms to represent these maps. So there we're focusing only on the east component. So that is the result for the east velocity maps. What we can see with the color bar that yellowish tones indicate westward motion, while greenish tones indicate eastward motion. The first thing that you can remark, it's the divergence limit in the albanide is clearly refined by the INSAR data, and also a large shear zone already known in continental Greece. We can see also smaller scale processes in this east-west maps, east-west velocity maps. An example for the Katuna Stamna deformation, you can see with the contrast the interseismic loading across this fault, and we can also see some smaller scales gravitational features. We didn't show it there in this presentation. So we draw the same profile as earlier for the south-north from South Peloponnese, to Eastern Serbia to see the continental shear grace zone. We can see that this gradient is of large amplitude, more than 2 centimeters, which are distributed over more than 250 kilometer long wavelengths that can be linked by lithospheric scale processes. We do the same thing with profiles in the transtensional zone in albanide, and even if the amplitude is smaller, we can clearly see the deformation and the gradient of this divergence distributed over 80 kilometers with an amplitude of 3 to 4 millimeter. So INSAR can catch a wide range of velocities gradients at different wavelengths. So now let's focus on the dynarides. So there we reprojected our velocities perpendicularly to the dynaride belt to try to explore compressional motion. So you have the profile. In blue, you have the 35 reprojected velocities, and the parallel one to the mountain in gray. We can see a long wavelength gradient of 5 millimeters on a range perpendicular components, suggesting low compressional motion between dynaride coastline and their hinterland. The signal is weaker for the coast, and it decreases nearly to zero into the hinterland, possibly linked to coupling, to subduction coupling or rotational velocities. For the vertical velocity, we do see in the southern dynarides some potential uplift with brackets for about 1 to 1.5 millimeter along the southern coast. So last but not least, I'm not English native. So you can see the focus on the Gulf of Corinth. It's often stated that Sentinel-1 data are insensitive to north-south-like deformation, along track deformation. And we tested this statement by reprojected the velocities into the rifting opening direction of the Gulf of Corinth, which is approximately 190 degrees. And there you have the 4 profiles represented on these maps. As you can see on the most west profiles, the rift-like deformation pattern with a beautiful semi-arc tangent shape north of the Gulf of Corinth for PC1 and PC2, which are encouraging to take care. Also on the PC3, you can see more localized deformation between fault and between basins, which can be highlighted. This and good consistency with GNSS provide us a good hint to say that there is some capability to capture a long track deformation at intermediate wavelengths. For the vertical maps, we do the same, and like the most westward profiles, the PC1 and PC2, where the tectonic activity is focused, you can see a large subsidence activity related to the active faulting of the Gulf of Corinth at the westward part, at the western part. You can also see lateral variation of vertical velocities and some discrepancies with GNSS vertical velocities near Gulf of Corinth. So it raises the question: does the discrepancies between GNSS and INSAR velocities are random? So we plot the residual between GNSS and INSAR. So the 2D GNSS were projected in loss confronted to the INSAR in loss. And we see that in Gulf of Corinth, Thessaloniki Basin, we have such high residuals. We have also big residuals in Pannonian Basin, but that's where the line of sight estimation have to be caught cautiously because due to unwrapping error or potential biases. So the question is, it's random. It seems to not, because we see when we plot this residual versus the INSAR vertical velocities, we see clearly a systematic GNSS discrepancies where INSAR vertical deformation dominates, which are encouraging to take into account this INSAR vertical velocity from these maps. So in a nutshell, we presented high-resolution referenced interseismic INSAR velocities for the Balkans Peninsula, where the challenge were big, with low deformation rate, a lot of potential biases with vegetation, and co-seismic signals. We do show that a wide range of velocity gradients from few millimeter to centimeter years can be highlighted from different processes, either tectonic and not tectonic origin. And we presented in the last slide the added value in the area of high vertical motion. We have started to integrate these input maps into new strain rate calculation. And all this work presented is in final review stage, and I hope it will be published very soon. And it will be accessible from an easy data portal for the scientific community. So take that afterward. And to conclude my presentation, I'm also here for the poster presentation. I presented another work on the 6.3 Durech earthquake in Albania using the same data set. So feel free to discuss with me after the coffee break. And thank you for your attention.
Thank you. Thank you, Emile. Okay, so we'll take a few questions. I can't ask any, so. Yeah, John.
Thank you for that. That's a great set of work and some brilliant interpretations. I think actually your last slide answers my question, but I was a bit concerned at first. It's a great idea to be able to solve for the horizontal and vertical by picking the horizontal direction, but obviously in the Eurasia fixed reference frame, it's near zero and ill-defined in your area, but actually did you do everything in the ITRF reference frame when you were defining those directions?
And basically, to reference our dataset, we use ITRF GNSS 2D GNSS dataset, and we estimate plane to mimic the large-scale plate motion on GNSS and on INSAR, and we compare them in this. Oh no, I have additional slide, but just there, we are comparing INSAR ramp rates and GNSS ramp rates, and we showed that in range direction there is a correlation between them. So we did just adjust an azimuthal ramp correction, but not a range. So yes, it might be the GNSS can influence along track results in our horizontal vertical decomposition, but for the range we are quite confident with that.
Brilliant. Thank you very much.
Thank you.
Another question? Otherwise, we'll switch to the last talk from Henriette Sudhaus. She's going to talk about underground mining-induced earthquakes.
Yeah, thank you. Before I start, I would like to also acknowledge my co-author, Wojciech. He's here in the room, and he's from Krakow University. So this is kind of a coincidence. We met at Living Planet in Milano, and this started this whole project. So maybe my recommendation at ESA, keep up these nice conferences. Quite affordable, sponsored completely. They do stimulate cooperations. So, so with that, I'm going to probably the smallest earthquake that we have seen so far. So we move a bit closer to where we are. So you can see Krakow is here, and we move to the Legnica Glogov copper district. This is where we mine copper, and this induced seismicity, and this is what we are I'm talking about. If we are looking at where this copper is, we can draw a profile, and we have this is stable continent of Europe, and we have thick neogene sediments, and due to some previous tectonic motions, we have an inclination of sediment layers, and the copper here is on top of this very red Zechstein layer. So mining takes place at 500 to 1,000 meter depth. For reference. Okay. Now we are moving into the region. First of all, copper is mined here in the so-called room and pillar strategy. So you drive in tunnels, you drive cross tunnels, and then you increase the space. You take out as much copper ore as you can. Copper is very important for our electric future, and we are very greedy with that. And you can see there are some pillars left standing. Of course, we form free surfaces, and we change the stress in the subground, and we induce earthquakes. Okay, so this is the seismicity map. This is a catalog from 11 years of earthquakes, and well, we have a lot of them, and we are concerned here with the larger ones. We have many earthquakes per year that reach magnitudes larger than 3, so they are felt in the region, and we have also several even larger than 3.7. So this is quite large. So I'm not sure if something like this would be possible in Germany, to be honest. And these are the earthquakes that we will look at. Maybe I point out some landmarks that we will see on the later maps. So there is this very big tailing pond that you can see here, where wastewater is put up and left out to dry. And then we have here the town of Polkowice that is very close also to the seismicity. Of course, this region also experiences subsidence, and I'm showing you here our standard European ground motion map, where everything is green, then it's stable, but when it gets yellow, we have several millimeters per year of subsidence already, and this reaches here up to 50 millimeters. This is quite a lot. And we can also see on this map that in some places, particularly in the southeast of Polkowice, the maximum values are close to where we lose the signal. This is time series data. We have we lose some stable pixels when we have strong displacement, unsteady displacement, but also forest and farmland. But if you look at the map before, you can see that this is also where we have some seismicity nests because there is active mining going on. I can also demonstrate this with GNSS data. You see here southeast of Polkowice a GNSS station marked with this half circle. And here's a time series of 2 years. This is not public data, unfortunately, but you can see time series from 23 and 24. And you can see that in 23, we have a displacement rate of 200 millimeters per year, approximately. This picks up in 24 to 350 millimeters even, and in the beginning of 25, you can see there's an offset. This is one of these large earthquakes that make earthquake in strong signal in one go. Mining took place relatively beneath this GNSS station. And came closer. Okay, so what I'm looking at, I like to know what is the source process. These large earthquakes, they are unwanted. So we are mining. Seismicity is something that you cannot really avoid, but these large earthquakes, they do damage to the structure. And actually there's some engineering processes like de-stressing drilling that is done, but it's not completely successful. We still have these large earthquakes. And we are trying to find out if with the combination of INSAR and seismic data, we can somehow learn more about the source process. Maybe this helps to find out why they still happen. So again, we have this room and pillar mining scheme. We have a steady subsidence usually, and we think that we have sometimes these larger earthquakes where we have roof collapsing and shear failure. And maybe this is something that we can get from our observations, the mechanisms of these earthquakes. Okay, I will show you some interferograms now. So this is a zoom into the region. We have on the left side Polkowice, a relatively new highway, as Wojciech told me, that is meant to withstand all the subsidence and also shaking from earthquakes. And we have then on the right side this big tailing pond. This is quite large, and of course this should also be an infrastructure that is not failing. There's a lot of very dirty water in there. So here, this is an example, an earthquake in February 22, and you can nicely see a subsidence bowl with a diameter of 1 kilometer approximately, and you can see there's one fringe of displacement. This earthquake was given in the catalog of the catalog of the local network with a magnitude 3.8 and at a depth of 700 meters. Then just 2 months later, we have an earthquake that is relatively close to the town of Polkowice, magnitude 3.7, depth 700 meters, and we can clearly see these nice 3 fringes, 10 centimeters of displacement in the line of sight. 20 days later, another large earthquake here, relatively close to the tailing pond. Yeah, we can make those 1, 2 fringes. But there's also some decorrelation, of course, so the signal is not perfect. Then here in 23 in summer, signal quality is relatively poor. So there has been an earthquake here in July that is here east of this highway. You can just make out where it is here in this filter data. There's some gradient, so maybe we can say where it was and not exactly what the surface displacement is. For that, the coherence is not good enough. We can also see a signal close to the tailing pond on the west side of it. There's no larger earthquake in the catalog that is connected to this subsidence, so it could be aseismic, I don't know. So here just a last example. This is from September 23, 2 earthquakes within 1 interferogram with magnitudes 3.5 and 3.9 and some 700 meters depth, 800 meter depth. So these are earthquakes that we are investigating. Some of them have like several or 2 large earthquakes in a very small time interval that will be both then in our interferograms. So these are earthquakes I'm not taking here for our first results. We need to model them in a different way because now we use point sources to analyze these events. When we look up into literature how these mining seismicity is interpreted, we have something like this. So you can imagine you have here from the roof you have extension because you have a free surface. You take away quite a lot of material, so you also have kind of less mass on the floor. So there's also thought that the floor is reacting to losing mass, and then we have, of course, the increased stress in the pillars that could cause shear failure or also tensile cracks. Well, these mechanisms, first of all, I mean, we are here in earthquake sessions. I will show plots in this kind of Hudson diagram. Here we cannot just see, like with a moment tensors, what direction and shear failure mechanisms we have, but we can also sort in this diagram isotropic components on the vertical axis. So if we have something where volume is increasing or volume is decreasing. On the horizontal axis, we would have a 0 net volume change, but we have these compensated linear vector dipoles. So this is pure shear without, as I said, net volumetric components. And there's just some examples for those who are not very familiar with these Hudson plots, what it could be. So this would be a pure explosion, and this would be here a negative, pure shear donut kind of event. So for these mechanisms here with room and pillars within the pillar, we would not get earthquakes magnitude 3.5. We have to expect that a larger structure is affected. Yeah. So for this, just a few tens of meters, we would get smaller magnitudes, but with 3.5 and larger, we have to expect that a larger volume is affected in the mine. So several pillars, several rooms, maybe. Okay, so I'm going back to this April 7 event in 2022. And we are using, together with the INSA data that I showed you, also waveform data from the local network that I've showed you. So here you can see seismograms. So this is just this Z component, vertical component sorted by distance. The amplitude is normalized What you can see is that you have a relatively low frequent ringing here in these. So it's very almost periodic signal that we have. This is quite interesting. So the frequency content of these earthquake is quite low frequent. So this is something that we also have to investigate further. So I'm going directly to results for this earthquake. So you can see on the left-hand side a map that shows an ensemble. We are doing a Bayesian inversion, you can see where we locate the earthquake with a cloud of possible models. Here 0, 0, the origin here would be the catalog location. We are locating this earthquake slightly more south, and we can locate it within a few hundred meters. So this is quite pleasing. On the right side, you can see now our mechanism. For us, this earthquake looks like an implosion. Yes, the largest component is an isotropic component, and we have a small shear component as well. We are not sure how stable this shear component is. So this is something that has to be investigated further. We get a magnitude of 4.2, so this is larger than before. So this is our data. You have seen the interferogram. We unwrap the interferogram. We subsample the unwrapped interferogram. This is the usual way. We have to mask out quite some parts because of decorrelation. But still, we can fit the data to quite a pleasing extent here with this joint model. We can also fit the waveform data reasonably well. We get a nice fit to amplitude and frequency for here just examples. So we're using all the waveforms I showed you before, and we have here P wave fits on the left and S wave fits on the right, which is important when we want to get the mechanism right. And we are not just fitting the waveforms in time domain. This is something that we have also seen in previous presentations. We also fit the spectrum. So this makes us a bit more stable when it comes to the frequency content of our waveforms. Okay, so this is something that we do for 4 of the events that I showed you interferograms before. And this is a compilation of the 4 results I trust so far. In these Hudson plots, and we can see that we have a lot of this isotropic component. This is what you would expect. We have a mine, we have strong earthquakes, likely something fall in. Yeah, we have a caving in of the mine. Interesting is maybe if we can do later on something with the remaining shear failures, if we can see some preferred directions and so on, and what it would mean in combination with what is going on in the mine. We have no information from the mine itself. We hope that we have some cooperations in the future. Let's see. So these are the mechanisms now for depth. I'm showing here some results. You see a box plot that shows the statistics of our model ensembles. This red area marks the depth of the copper horizon based on boreholes that are close by. And the blue star is the catalog location. And you can see that for the earthquake on the left and for the earthquake on the right, there's a good agreement with all of that. So we map the earthquake in the mine where it's likely to take place, and we have also agreement with former solutions. Then we have for the other earthquakes, we have quite some spread with the depth, and sometimes we also think the earthquake is deeper than it was given in the catalog. But we also have a strong, as you can imagine, maybe a trade-off with magnitude. So I'm showing you also the magnitudes that we estimate, and we are with all our magnitudes higher than in the local, so official catalog from the mine by quite some bit. So we are usually above 4, and they are usually below 4. I don't know if there's something like a permission threshold. Right, and for some of these earthquakes, we have a trade-off between magnitude and depth. Okay, so basically, that's it. We like to find out about these large earthquakes, as I said, because they are unwanted. And some of these earthquakes happen not shortly after blasting takes place in the mine, so then also people are really at danger in the mine. There are sometimes injured people and also fatalities in the mine. So this is maybe a motivation also of our work. So we get quite a good fit with some of the data that we have and also with previous studies. If we would do this static only, so just the INSA, we would get very much shallower results. We have shown this also in a previous study. So it's important to take also waveforms into account. What we would like to do is, maybe also start with more complex patterns when we have several large earthquakes short after each other in time. And maybe we can also resolve finiteness of the fault because we are very close to these events. So this is something that we will work on in the future. And of course, we would also like to study more earthquakes. Thank you very much.
Questions for Henriette? Yep. Garrett.
Hi, these are really great. I like small earthquakes. I never see them with INSAR. I'm wondering about the depth problem. And there are two issues potentially I can think of. One is how good is your seismic velocity model? And the other is what's your elastic structure? And can you find a combination of tweaking both of those that make the source locations agree?
That's a very good question. So we're using the same velocity structure that the mine is using. I've shown you that the layers are inclined and we are using a horizontal velocity model, so there could be some bias, I think, in location. It's a purely elastic model. And this is an interesting suggestion. But what is also interesting is that some of these earthquakes do not destroy the mine, so they're actually happening above or below the mine. So this is still possible. So I'm not sure how much we can constrain where the earthquake really was. But this is a good suggestion to tweak the elasticity parameters a bit to find out what happens.
Thanks, really great talk. So those moment differences are huge. It's a factor of 2, right? So I wondered, I mean, obviously the things Gareth suggested could also play into moment, but whether there's any aseismic deformation so I don't know whether you've tried to look at ongoing time series. I mean, these are tiny, but...
Yeah. So when there's some GNSS data also that is not public and that we will try to use more, where you see that after these jumps, you have also some post-seismic subsidence. So we could have more static signal than we have in the waveforms. This could be, and this could increase the moment. I've looked at the European earthquake catalog. Some of these earthquakes are in there, and they have also larger magnitudes. I need to look into that. So they are even higher as our magnitude. So I think it's something with velocity structure and with medium structure that we can talk about. But I would, maybe I'm too suspicious. But large magnitudes is no good news for mine.
Just to add on to Gareth's comment, are there any seismometers in the mine itself? Because that would pretty well solve it.
Don't know of any, but this is something. So this is kind of a closed shop. When it comes to more data, there's some accelerometer data, but only just at the surface from that I know. But we are seeking contact with the research units of the mine, and maybe we can work something out.
Yeah, and also the depth uncertainty is probably a lot due to the emergent nature of the P waves in these arrivals.
Mm-hmm.
So you had triaxial implosion as a likely source. Have you looked at uniaxial? And I'm a little bit surprised that there's no sign of this in the mine. It looks like the mine is collapsing. But
Yeah. Uniaxial. So we have the full moment tensor solution. So we would be open to have also this solution. Not a single force. But full moment tensor is included basically, and this is what is often seen for the smaller earthquakes, that we have these cracks and dipoles and CLVDs purely. For the large ones, it seems really to be falling in, and then we have to see if we have stable enough information of the remaining part of the moment tensor, of CLVD part or shear failure part. So far, we have to look how stable it is for interpretation.
Okay, thank you. So that concludes the oral part of the session. Now it's our favorite part, which is the discussion with you. I invite the conveners to come back on stage. We are not extremely well organized with seat questions, so this is therefore your chance to have real influence, because ISA does listen to these recommendations that we end up writing down. So if you don't come up with recommendations now, we will have a beer later on and come up with them ourselves, and that could quickly go astray. So I think we, while you're sitting down here, should we just open the floor? Yes. Yes. So I think we open the floor. Please raise your hands. Otherwise, we will just sort of, I will pass the microphone around here among the chairs to sort of tell something about what they saw today, or if the presentations reminded them of something that could be included in the recommendations. So if I don't see any hands, Falk?
Yes, so after seeing Shimon's talk, of course, I'm wondering how come we're having only one viewing direction there. So it's something what I think we discussed it 10 years ago, and after that we didn't really press for it anymore. We just should have everywhere 12, both viewing direction.
I think what we are seeing here is that people are starting to see deformation in areas which are deforming slowly, maybe slower than we thought we could actually resolve, and also areas which are heavily vegetated, areas which have been of sort of secondary importance until now. And this is completely correct. This really is a good recommendation to try to accommodate for more observations from both look directions in these areas, which have been now, until now, on a sort of a secondary importance. Yes, and also because we are more and more seeing the importance of separating the vertical signals, which are due to a range of mostly human activities. It's important to have both directions to be able to separate these better. Well.
Just going to echo that a little bit before I ask my question. I think it's not a surprise that the best advances have been in the dry areas of the world. And I think if we're looking towards understanding hazard to risk is often concentrated in other areas around the world. So extending these observations, whether it's prioritizing repeat in those vegetated areas in Southeast Asia or South America, would be really valuable to really extend our understanding. So because there are very big faults out there that we're not looking at. And the question, to link some of the comments around what Tim and the others are talking about, are we ready now to understand the impact of the magnitude of an event on the long-term rheology? Because you merge a few earthquakes together, but they're all different magnitudes in different areas. So are we now ready to say a magnitude of this size event in these particular regions has this impact on the short-term rheology?
Oh, it's very late in the day for a question like that, Iqbal. I think the short answer is no. We're not ready. But the plot I showed it's from John's paper. They are not. There's an attempt to normalize them by the rate, the long-term geological rate, but obviously that's uncertain. Perhaps it's systematically biased. So I think that's a challenge. Just in terms of ascending, descending, 6-day coverage, etc. One thing we discussed at Living Planet but haven't done is maybe forming some kind of working group to make a recommendation. I think ISA prefer it if there is a sort of an organized collection of people with one view rather than receiving individual views from lots of people. So I don't know how we organize that, but we can make a recommendation that is organized. It's probably up to us.
Yes. So are you getting for the Alpine Himalaya belt and for Tibet, are we getting every 6 days or every 12 days?
Every 12 days, except for the European bits. See, they're 6 days. I think there is. It sounded like there was a little bit of extra capacity might be there. Obviously, we're going to get more capacity with NISAR, but with Roselle coming up as well. But there's not a huge. My understanding, I don't think we've got Nuno. Nuno in the room, yeah, I don't think there's a huge volume of capacity there waiting for us to. So it might be a case of. Yeah.
Yes. So should we consider to scaling down to the noise goes with 1 over square root of n, and now we're not going to increase very much the signal with time. So maybe we should put emphasis to other parts in the world.
Yeah. Well, noise doesn't go with 1 over square root of n within, so I don't think it goes anyway. But that's because it also depends on the length of the time series. But you're right. You could reduce you could go for 24-day coverage, for example. That's probably more complicated for programming, but it would free up capacity in more coherent areas. But then we'd moan when there was an earthquake and we had to wait 13 days till we got a post-seismic image. So I'm not sure. So I think this is what a longer discussion would be useful, I think, amongst a group where we sort of can try and tense all those things against each other.
So I think, so my view was many things from Sentinel are now kind of settled and the capacity is not increasing very much. But if we have more capacity, so what I was looking, and the slides, we have a larger duty cycle, so there will be really more observations with Roselle and coming missions. And then I think it would be exactly, so where do we need ascending and descending, and where do we like really increase coverage even more with at least one look direction to discover the undiscovered ground or something like this. But this needs a group because it needs to be also a bit organized with the other missions, right? So, but I think this would be great. So coverage is our wish as always.
I wrote a long list as we've been going through the day of all the things that people have suggested, so we could work our way through those. So I think we've mentioned. I think a big important one was the coverage of look directions. I think we've then had this discussion on these extended BOIs, which is relevant for both Sentinel-1, but also for future missions. So there was a brief discussion we had after Mohammed's presentation about whether we should recommend to ESA that when they do the repro, that they do it with the extended bursts. I suspect we're not going to get that, but would we want that? Should we put that down?
Yeah, we can even have that for a few regions. I would put that down.
Yeah.
We see what we get.
I'm not seeing anyone saying, no, don't do it. We always want more, right, as a community. Yeah.
What do extended bursts come at the cost of? Do we nothing?
It's just a bit of processing power and storage. I think they'll be slightly bigger. The processing is very simple. You pad out the raw data with zeros, and then when you process it, you get a bigger area. It's not complicated.
Gotcha. So it doesn't come at the expense of burst width, for example.
Yeah. So you end up with these bigger SLCs. Yeah. But
yeah, just about this idea of compromising between all our SLC everywhere and maybe choosing some sites. Clearly for interseismic, we would like to have north-south everywhere, but I guess we should just target the north-south faults, and that would be already great, actually. So, yeah.
I would like to mention one thing about this. The point that you mentioned about Mohammed is if you look at some data in, for instance, South America, you have this IPF issue. So many Sentinel data needed to be reprocessed because when you start to create SLCs, there is a burst mismatch and a lot of phase issue. So Duza removed all those Sentinel data, and they promised to give us the new Sentinel SLC focus, but it never happened. So maybe this new processor helps. And other issue I can say is the ESA for South America in particular, they planned the SLC's frame, and then they changed it by time. So you don't have the largest stack of SLC for a specific location. So you have time series for 2 or 3 years, and then they change the frame, and this is a problematic thing I can say.
I guess there are ways, obviously, of stitching together bursts in different ways. So I think there are tools that you can get around the frame issues. We can discuss later if you want. But I think, yes, consistency is really important. And we want these very long stacks, very boring stacks acquired in the same way over long periods of time. And that's very valuable. Yeah. Volk.
Okay. Yes, thinking about it, let me say one more thing about the coverage. I think for those areas where we have only one viewing geometry, even if we only get something every 36 days or so, we saw lots of good ERS results. If we start acquiring this now, it will be pretty useful in a couple of years. Yeah. It doesn't cost too much resources.
Yeah, I think that's right. I think that ESA have been reluctant in the past to change, have different things on different cycles. They'd like to always just sort of increase coverage, but we can still make it a recommendation. Yeah. Akbar.
I know we're in a earthquakes and tectonic session, but the most common hazard most countries face are landslides. And I think there's a way we can optimize the coverage as well to make sure we cover those hazards in many ways, particularly across Africa, where and a lot of the look directions aren't even fully covered. So I think we can recommend, well, obviously not Sentinel, but Sentinel Next Generation could think about optimizing locations where these other processes are more common. That would be great. Another comment on that is around the Harmony plans, where they were going to do bistatic, they said, over just the volcanic areas, which is true. Volcanoes deform and the elevations change, but landslides are the most common sources of elevation change. And whether actually can we extend those bistatic regions to cover, why not cover all the mountainous areas or any slope above 5 degrees around the world to make sure we capture all those?
We'll write that down, but I think that's probably worth you bringing to the landslide session tomorrow as well, and getting it put down in multiple sessions.
I have maybe a question and comment. Isn't Roselle and Next Generation Sentinel-1 doing ScanSAR and we are losing the burst overlaps? Is that right? No? It's all tops?
No.
But we are still overlaps?
I think, yeah, there'll be somebody who knows more in the room, but I think Next Generation Sentinel-1 is still tops, and Roselle is ScanSAR but with overlap.
Yeah, actually, I had a talk on Monday just about the overlaps in Roselle. We have enough bandwidth in Roselle to have overlaps. We can even increase them, so we can have 100% overlap, so that we can have 2 looks for all the points. I'm not sure about Next Generation. I think it's also ScanSAR, but maybe better to verify with ESA directly. But yeah, there's definitely the chance of also using the overlaps in Roselle. That's how much I can say for sure. It's then a matter of how much bandwidth is going to be given to the end user. But this is, again, something that has to be done with ESA. Yeah.
Perhaps there is a question about data formats. We talked a little bit about burst coverages, and that's one thing. But when you download an SLC, you get all the polarizations, whether you want them or not. And if you are studying tectonics, you only want VV most of the time. And having to download twice as much data that you actually want is a waste of bandwidth and your hard drive. Could there be a call for like slightly smarter packaging of data? Like just the bursts you want, just the polarization you want. I think that might be helpful. Hard drives are expensive right now because of AI.
Yeah, I've written that down. I've got a feeling that they did release something where you could download individual bursts. Anyone? Yeah, I'm getting a nod from Erwan.
For volcanoes, no, at least, I don't know, but yeah, I think Raphaël Grandin, he did something about that. I think it's...
Okay, there we go.
Yeah, both ASF and CDSE now have a burst extractor, so you can download just individual bursts for just your individual polarizations. We have a tool to synthetically pack multiple bursts into a synthetic safe, so you get a safe product and works with all of your tools. So some of that's coming, and then if you've looked at the ZAR repackaging, the bursts are individual objects. It should be straightforward to get a URL directly to the individual bursts with the ZAR packaging as well. So I think that's largely already being tackled by ESA.
Thank you. I think we all like to extend our appreciation for all the work you do at ASF on this. It's fantastic. Thank you.
I brought this up in a different session because I'm passionate about it. And so I still feel like the missions, and we saw this in several presentations, the ERS and Envisat data are still useful, especially for tectonics with the long time spans that you're looking for. And I feel like those data are not as available as they could be. And I want to encourage ESA to potentially think about just processing all the ERS data, for instance, to SLCs and co-locating them in a place where they're easier to discover. Same for Envisat. I don't think it's a huge expense or effort. The data volumes are comparably small compared to the modern sensors, but I think would make these data sets much more visible and encourage more work on combining this very long C-band record that ESA has created.
Completely agree, yes.
Download speed. I want to second what Falk said the other day about the speed of downloads. The servers seem to be like from the time that the data was collected. I tried, it took me an hour to download a single SLC, or longer, maybe 1 to 2 hours per image. It was just painful. I don't know.
Yeah, well, we sometimes get it from these guys faster than we get it from ESA, which is kind of crazy, but there we go. Sami?
I want to emphasize a little bit on this extended burst overlap. It was mainly discussed in this session on tectonics, but because the burst overlap is really limited and with tectonics is really main added value. But if it is extended more, then a lot of other applications can see this north-south direction, and it's not only particularly for tectonics. So of course this is tectonic session, but if you make recommendation, this increasing burst overlaps really is something that for lots of other applications can be used.
Yeah, I think another point actually on it is something again that emphasizes the value of keeping the raw data. I know a lot of new missions are thinking about like edge processing and just giving us the process data, but actually ideas and techniques develop, so having access to go back and being able to reprocess right from the raw data is extremely valuable. So I think ESA are pretty good at keeping that, but worth writing down. Yeah. What else is on my list? I think we've covered most of them. I mentioned there's visa letters going out earlier, I think is important. There's been a number of these big scale velocities from different groups, FlatSim, the Comet ones, there's DLR have things. So there's a number of groups. So is it time finally to actually commit ourselves to doing a proper intercomparison exercise? be.
I think we heard that before, for sure, in former fringes. But yeah, I guess actually now I think with the open access data, we see that all our results now are in some of the other platforms. So I guess it will come also for the publication. But yeah, we should do that, yeah, definitely. We probably do that also sometimes in small areas. So yeah, we could maybe make it more systematic or, yeah.
And I think there's probably a value rather than, because all those data, you say the data are now public. So if we just don't do it ourselves, then somebody who doesn't understand the data might do it. And then we run the risk of the kinds of things that have happened with this letter to Science, etc., or the article in Science and the problems with the subsidence community. So I think having some kind of community effort where I think this has worked well. Gareth, maybe you can comment on how it's worked in the States.
Yeah, so I was involved in a project with the Southern California Earthquake Center that was called the Community Geodetic Model. And the idea was we took 2 tracks ascending and descending over Southern California, and about 6 different groups with different methods processed the same interferograms on the same days and tried to make time series analyses. And it was very instructive. We started off by just processing interferograms and identified that there were actually issues with GMT-SAR focusing, or the range correction or something like that. And so those got fixed. And then we moved on to time series and velocities. And yeah, I think we gained a lot of insight into various things, including uncertainties, the various assumptions that different time series methods made and how they impacted the time series. But amazingly, even though people were using extremely different approaches, the velocities that we came up with were almost the same from all the methods. So that also provided us with pretty great confidence that we were seeing real signals. And I think we will finish that paper one day. The data are all available. So the big push we were under was to release all the products. So there are basically 6 different time series realizations for all of the tracks and velocities, and a combination product, which is basically the average of all of those, which is even more robust than any of the individual ones. Yeah, and then, you know, we didn't finish the paper, but because that's mostly because of NISAR and like Katia Timofeeva being extremely like distracted. But I think we will come back to that soon, and it would be a good model to follow for some of these other efforts. And I'd be happy to be involved, even though I haven't done any large-scale things in Asia.
I think there are groups in the States who have done things in Asia using the same tools. So I know people at JPL have done Tibet, etc. So I think there are
At least the same approach, let's say. There can be some subtleties, but should compare that. Maybe I can add something also. So we could compare the line of sight velocities, but I think that we see more and more papers using that to do strain rate maps. And I think like the GNSS community, we are definitely at the point where we should also compare the results in terms of strain rate maps, because now in the publications, you always see strain rate maps and some are really noisy. So recently there have been some efforts in the GNSS community to intercompare various approaches. That it's really interesting to see what can they catch. They can catch different things, but it's not to say one is good, one is bad, but it's a very interesting exercise, and I think we could do that also for INSAR now, yeah.
That was also part of the SCEC effort. There was a first generation which was just making strain rate maps, and there's going to be another one which is to try and turn these velocity fields that we have made into those, and GPS and INSAR people working together in harmony.
great. So that sounds like an action for us as a community, not for ESA. Another thing we were asked to comment on way back on day one was how we want Sentinel-1 Next Generation and Rose-L to fly. The basic choice is that we could have them in so-called convoy mode, where I think Rose-L is very shortly behind Sentinel. So basically we'd get both of them every 6 days, or whether we spread them out so they're every 3 days. I suggest that if there are people with strong views, they speak, and then maybe we have a show of hands and maybe it's 50-50. I've got a mediumly strong view. which is for event response. If we're responding to earthquakes, it's better if they're evenly spread out. That's my mediumly strong view. But it'd be good if somebody has a strong view in the opposite direction. It'd be good to hear that. Otherwise, I've completely biased the audience. Folk has a strong view in the opposite direction. Very good.
Yeah, I think it would be great if there's very little delay between them. There are still lots of signals in both, well, in the C-band data for sure, which we don't understand. In the L-band data, okay, we don't know yet because we don't have the NISA data yet very much. But okay, if we have both almost acquired at the same time, we're going to learn lots of new things on the radar side.
Maybe we could use the experiment of NISA for that. There is S-band and L-band on the same mission. It's not C-band for sure, but I mean, you have two different frequencies. You might be able to see frequency-dependent effects. And then maybe we can make our minds up after a couple of years of that. They're not acquiring S-band everywhere, unfortunately, only over India and maybe a few select friendly places. California is one of those. But we might learn quite a lot from the comparisons there and maybe use that as a means of guidance.
I was wondering if there's really these two options, like convoy and 3 days, because I think we will all look into the tandem data and maybe see if there's something that we can learn from these one-day interferograms, because this should be very good coherence. There's a chance that something happens in between. If this is also a third option we could throw in, or if this is something that is not reasonable. I also understood like these are the two options. But yeah, maybe, I mean, there's still some time to think about this. But I was also thinking maybe like, yeah, 1 day and 5 days is also not too bad, maybe.
Yeah, something else to think about it if we want it exactly the same time of the day as Sentinel-1, because observing at a different time of the day may give us a better idea, understanding of the tropospheric signal. That's I don't have one way or another, but it's something else that we can explore by looking at different, maybe one is going to be in the morning, the other one in the afternoon, and we'll get, it'll be more noise, but we can learn more about the noise by that.
Any other views on timings? John?
In terms of the orbit mechanics, is it too hard to do a sort of initial commissioning scientific phase as done by other missions of being one minute behind at the start, do that for a number of months and then shift it?
I guess you could do that. I mean, the options are actually, as Henrietta says, infinite, I think. And they say you could have one minute behind and then the other one not. And so you could have kind of 3 separated by 4 days, right? Or is that with one of them? I don't know. That's maybe a compromise option.
If we have all healthy satellites, right?
Yeah, yeah.
Lucky situation.
Yeah, that's true. The satellites may not be healthy. Just in terms of those end members, I think there are 3 categories. Strong view that they should be equally spaced, strong view of the convoy mode or something similar that one day, or no strong view. So should we have a show of hands? Who has a strong view that they should be equally spaced? Right. Okay. Okay. A strong view that they should be in convoy mode. Similar, isn't it? Slightly less. Fewer. And fewer, and then no strong view. I think it's the winner, I suspect. Who hasn't put their hand up? Come on. Yeah. Would it be fair to say this community does not have an extremely strong view? We can see the arguments, and we'd like further investigation.
If we count the strong views, we could have a majority on one of the strong views, even though the majority is undecided.
Yeah, there was. I think I counted slightly more for the evenly spaced.
I agree.
But I am biased. Well, it's the Roselle and Sentinel-1 Next Generation, yeah. But there is some time for this. But I think you're right, John, they can move, because they're moving the existing ones, aren't they? Yeah. Okay. Yeah. There may be
why for a long time, maybe, yeah? So, and maybe why for a long time, and not just for a scientific phase.
Yeah. I think Falk's argument is a good one. Understanding the differences is useful, but yeah, for a while. Yeah, and it's essentially an operational satellite, right? It's not a satellite to do interesting things with. We do interesting things with it, obviously. Falk.
Yeah, so when Sentinel started, okay, so what we were advocating for is also very small baseline. We got it surprisingly good, and the PS people, they were not really happy. Now the last couple of years, okay, they had to make the baseline, the orbit wider, and it turned out also for our community it was good. So I just think if we are a little bit more, yeah, okay. I guess the PS people, they would like to have it at the same time because they can do, or in convoy, because they can see more things. So I think we just should be a little bit, yeah, giving to them.
Yeah, I don't know why it would make it much difference, PS or rather for convoy, would it?
Well, if it's at the same time or almost acquired at the same time, I think that is what the PS, they will understand the differences in the PS between C-band and L-band.
Yeah. I think though you bring up another point, is whether I would like us to, perhaps we should say we would like the baselines to maintain that small tube. Yes. I think probably I'm seeing lots of nods. Is there any, from this community, it feels like that's a strong requirement, or strongly advantageous for us as a community. John?
Yeah, definitely the 100-meter they were aiming for that wasn't quite achieved. Can we push that? Because I think somebody showed an earlier study that even with quite vegetated areas, volume scatterers, with long time spans, that near zero baselines actually was quite good. Was that you, Shimon, earlier?
Yeah.
And actually, if we could get really close to zero, that would help with C-band. Yeah. Is that true? A true statement?
That was the idea.
Yeah.
But about the sampling, I mean, when you do even sampling, it's good for the wavelengths or the time span, but you will miss something that has a shorter time span. So it's good to have randomness or some kind of that you'll be able to pick up any phenomena that has a shorter time span.
What you need for that is a geosynchronous satellite. So come and vote. Not that you get to vote, but vote for Hydroterra.
If it's 3 days, you won't be able to capture anything that is less than 3 days.
Yes, but if you have a geosynchronous SAR, you can do it if it's every hour, and then you'll be fine. Yeah, but only for small areas. But yes, I agree. There is, like they do, I guess with Cosmos SkyMed, they have a sort of mixture, don't they? So you can get some one-day pairs. Yeah, yeah.
So I would like to share a point that is somehow related also to this discussion. So we have seen now in the last 12 years more data, more points, and we will have also in the future different line of sight and more satellites. And so my feeling is that at the moment we still don't have a kind of capacity to interpret all this data, at least from what I see in most of the presentations and most of the scientific publications that we had in the last, let's say, 12 or even 15 years. So I would like to ask you, what do you think was the benefit of having all this new information? What would be the benefit of having more data in the future in the process understanding? And if you can pick at least one example that is telling you, oh, we should do that on Sentinel or on Sentinel Next Generation or in other satellites that will be launched, because we need that. We need that for validating our models. Because if we're still using the Okada model that has been developed in 1980, so it's something that needs 10 points in the end just to have a solution. Yeah. So it's just a little bit provocative, but just to trigger the discussions, how do you feel is the way to decide also in these discussions about which time of day or how many satellites, how many views?
Yeah, I mean, well, maybe we should all have a go at answering that provocative question. I think on the kind of big data side, I think there's been several presentations where people are looking at very large regions and learning a lot about whether it's tectonic processes or if they're looking at lots of volcanoes and learning lots about volcanic processes. I think on the models, it's true that I think for the first part of INSAR, I don't know when that would be, maybe we go for ERS and MVSAT era. I think the models have lagged behind the data. The data have been so transformative and we're learning a lot and the models haven't been there, but I think they're catching up. Certainly we've seen some quite more involved models of the seismic cycle, some presented here, but there's certainly lots in the literature, better models of earthquake sources, better models of volcanic processes. So I think those things are happening. I think I said it after my talk, I think the exciting thing is, well, we've measured the average deformation and now, well, let's look at the deviations from that average, and those transients are really important, and they're telling us about rheology, and that's where we'll need these more sophisticated models. But I'm interested to see what other people on the stage and in the audience think as well.
I would go in the exact same direction, and it's interesting that we saw several studies comparing ERS and VSAT and Sentinel-1, and there will probably be more in the future, but we definitely see the signal-to-noise ratio kind of decreasing sharply, and it changed things in terms of, in terms of geodynamics. When we look at Tibet, I mean, it really points to the faults, and then it gives ideas for models, and these, we couldn't really do it before. And you mentioned the transients. For the transients, it's really crucial to have this new recurrent data, and you were mentioning Cosmos SkyMed before, and this one-day experiments that exist in some places, for example, the North Anatolian Fault. So in some cases, to track these transient events, we are very important for earthquake triggering and things like that. So we do need this new set of data. Yeah.
I'm very excited about the idea of doing full 3D with INSAR on its own. And that could be through doing the burst overlaps. That could be combinations of Sentinel-1 and NISAR, probably all of the above. We will learn a lot more because not everything on Earth happens in the vertical and the east-west directions. And the other thing about transients, the other thing you need, of course, is very long and boring time series, right? You need to know what the steady state is to be able to detect deviations from it. The longer we go with the same mission, with the same geometry, with the same everything, with the same data acquisition plan, the more we are going to learn about how things vary with time, and I think that's going to be fantastic. Is it time for a beer?
Yeah, and I think, well, we should probably go to the post session. I think some.
France, did you raise a hand?
I mean, I was going to add that I think some of the most exciting things that we find with these missions are complete surprises, and so that's another advantage of getting more data. Is actually predicting what you're going to find is sometimes more challenging, but that's hard to sell a mission on.
So maybe a last thought is, so there is, companies around like ISI now that have these fleets of satellites with growing INSAR capabilities, and also, offset observation capabilities. I wonder what role they could play in maybe some, super site locations to sort of understand, how they could be integrated into this kind of space in a meaningful way. I feel like even if you'd have, I would be interested in very high resolution data set up near the places where most of the motion is happening. Technology-wise, what I'm excited about is these missions these days, they have super high bandwidth. So in theory, their offset estimates should be good enough to actually avoid phase unwrapping entirely to sort of estimate the offsets at the fringe rate to sort of support phase unwrapping for interferometry. And so you could get high repeats over localized areas in places where the highest strain rate is happening in some selected supersites. That could be interesting to sort of understand what is, as all the space agencies think about, what is the role of new space to sort of see how they fit into the science as well.
That's great. Written that down as well. Any final points before we go and have a look at the posters? Okay, well, let's give yourselves a round of applause. Thank you. See you in the poster hall. Turn these into some slides.
Good. Very nice talk. Thank you.